On a shipyard floor that stretches farther than the eye can follow, a machine nearly a third of a mile long takes shape, tall as a skyscraper, built to carry an entire small city sealed inside metal boxes. The modern container ship is one of the most complex and staggering objects heavy industry has ever produced. It does not merely move cargo between continents, it carries the weight of global trade itself. Electronics, clothing, spare parts, appliances, the machinery of everyday life, all of it can at some point cross the deck of a giant like this. Yet the most extraordinary part of the story begins long before the hull ever touches water. Building a container ship is not simply the welding of steel. It is a project measured in years, where shipbuilding, heavy metallurgy, digital modeling, immense logistics, power plants of colossal output, and a precision without which no floating city of thousands of separate parts could ever be assembled, all converge into a single effort. What follows is how these giants are built, why their assembly ranks among the hardest industrial tasks on Earth, and how flat sheets of steel are transformed into a true ocean titan. It all begins long before the first piece of steel is ever cut. The creation of a container ship starts with design, and it is here that the fate of the future vessel is sealed. Engineers and naval architects calculate cargo capacity, stability, speed, fuel consumption, the behavior of the hull in a heavy sea, the arrangement of the containers, the operation of the engine, the trade routes, and compliance with international rules of safety. A modern container ship is not simply a large vessel. It is a balanced system in which a single change ripples through dozens of other parameters. Even at the stage of digital design, the loads on the hull are modeled, along with the methods of lifting the blocks, the order of assembly, the distortions that welding will introduce, and the way the ship will one day operate at sea. This work can stretch across many months. In a very real sense, the ship is first built in its entirety inside a computer, and only then begun in steel. The approach reduces the risk of errors that, on a real shipyard, would cost millions of dollars. That is why modern shipbuilding begins not at the dock, but inside engineering software, where the future giant is assembled before it is ever physically born. After the design comes what can only be called the birth of the ship out of metal. Enormous sheets of shipbuilding steel arrive at the cutting bay, where automatic plasma and gas cutting systems turn them into the future elements of the hull, the decks, the bulkheads, and the structural members that bind it all together. A single sheet can run longer than a city bus, and any error in its geometry will echo through the entire project that follows. But the modern shipyard abandoned hull-by-hull construction long ago. Today, the giants are built on the block principle. From the cut pieces, workers first assemble panels, then sections, and finally large blocks that already represent substantial fragments of the future ship. Such blocks can weigh tens of tons, and at times, a great deal more. At this stage, much of the piping, the cabling, the internal passageways, and the equipment is often installed in advance. This is known as pre-outfitting, and it saves enormous time, because fitting out a single block on the ground is far simpler than carrying out the same work later, deep inside an already assembled hull. It was block assembly that made it possible to build today's ocean giants within any reasonable span of time. Rather than raising a ship piece by piece directly in the dock, the yard builds it like a colossal industrial construction set. Individual blocks are joined into even larger mega sections, which are then moved to the place of final assembly. But the larger the block, the harder the task of lifting and setting it in place. Here, the heavy infrastructure of the shipyard comes into play, the colossal cranes. Among them, the famous Goliaths, capable of raising hundreds of tons in a single lift. With their help, mega sections the size of an apartment building are moved with a precision that seems almost impossible to believe. The slightest tilt, An error in the points of grip, or a single distortion can turn an expensive operation into catastrophe. For that reason, long before the lift, engineers calculate how the structure will behave while in motion, and the assembly itself proceeds in a strictly defined sequence. Here the ship at last begins to take on its true scale, as separate parts gradually become a hull that surpasses in size most of the objects a person ever encounters on land. When the megasections arrive in the dry dock, the moment begins that can rightly be called the true birth of the container ship. It is here that the blocks are welded into a single monolithic hull. A dry dock is an immense protected basin that can be flooded and drained, allowing these giants to be built almost as though on solid ground. Inside the dock, the keel line is laid, the supports are set in place, and then, step by step, the hull takes form. The vast sections are fitted to one another, aligned, locked, and welded. At this stage, precision and the control of distortion become critical, because welding on such a scale always drives stress into the metal. In parallel, the ship continues to fill with its systems, as additional mains, engineering runs, the structures of the superstructure, and the internal compartments are installed. The container ship is, in effect, assembled like a steel organism, where every section has its appointed place and every error accumulates along the entire length of the hull. That is precisely why assembly in the dock is among the most demanding phases of all. For here, the project, drawn from a digital model, is finally transformed into a real and living vessel. But the hull is only the shell. The true heart of a container ship is its power plant and its engineering systems. These giants are driven by enormous marine diesels that are, in their own right, marvels of heavy machinery. Yet the engine alone is not what matters most. It must be correctly tied to the propeller, the cooling system, the air intake, the exhaust, the fuel system, and the entire operating logic of the vessel. Engineers have long understood that a great many failures arise not from the engine itself, but from the poor integration of its supporting systems. A marine engine is, in essence, a giant air pump, one that demands a colossal volume of air and conditions tuned to perfection. If the ventilation of the engine room is poorly calculated, if the load of the propeller does not match the characteristics of the engine, if the logic of the cooling is broken, the entire system begins to wear itself down. The installation of the engine is therefore not the mere mounting of a heavy unit. It is the delicate engineering union of the ship's entire power network, and on it depends the vessel's survival in the open ocean. When the hull is at last watertight and able to float, one of the most spectacular moments of the whole construction arrives: the launch. For giants of this size, the dry dock method is most often used. The dock is simply allowed to fill with water, and a hull weighing many thousands of tons gradually lifts from its supports and begins to float. From the outside, it appears almost serene, but behind that apparent simplicity lies an enormous body of calculation. There must be precise understanding of how the distribution of loads will change, how the hull will behave at the instant it passes from resting on its blocks to being held by water, how the tugs will work, and how swiftly the vessel will reach a position of safety. After the launch, the container ship is still not ready for service. It is moved to the fitting out quay, where the work continues on the cable runs, the pipelines, the navigation equipment, the radars, the communication systems, the internal compartments, the insulation, the automation, and everything else that turns an empty steel shell into a real and working ship. It is at this stage that the future giant receives its brain. The final stage is the sea trials. This is the moment when the container ship first goes out to sea, not as an unfinished hull, but as a complete vessel, one that must prove that all its systems work together as a single whole. Tested are the maneuverability, the operation of the engine, the stability, the vibrations, the safety, the electronics, the navigation complexes, the communications, the power supply, the emergency modes, and a great many other parameters besides. Only after this can the ship be formally handed over to the customer. And it is here that one sees most clearly why the building of a container ship is reckoned among the most difficult assemblies in the world. This is no mere large ship. It is a floating industrial system where thousands of tons of steel, miles of pipe and cable, an immense power plant, digital control systems, demands of safety, economy, endurance, and the capacity to withstand ocean storms for decades, all must be brought together as one. A container ship must be more than gigantic. It must be reliable, because all its power is worth nothing without absolute soundness in the open sea. Seen whole, the birth of a container ship makes one thing clear. Here stands one of the summits of modern heavy industry. First, the vessel exists as a digital design. Then sheets of steel become panels. Panels become blocks. Blocks become megasections. And the megasections become a colossal hull that receives its engine, its systems, its electronics, and at last goes out to sea. All of it demands years, thousands of specialists, immense cranes, dry docks, and shipyards the size of separate industrial cities, together with an engineering precision without which such an object simply could not be built. And in this lies the true magic of shipbuilding. The container ship appears to be nothing more than a carrier of boxes. Yet in truth, it is one of the most complex machines ever made by human hands. It is born of metal, of calculation, and of discipline, only to become a part of the global economy. And every time one of these giants leaves port, behind it stand not only the ocean and the trade it serves, but the colossal industrial machine that proved capable of creating it.
And now imagine what holds enormous suspension bridges in the air, which daily withstand the weight of thousands of cars and hurricane-force wind gusts. Not concrete and not steel in the columns, but an invisible hero, steel cable. From thin, almost fragile wires, they create structures capable of bearing hundreds of tons. The secret lies in technology that transforms a simple metal rod into a sinew that never gives in. American factories have already woven over 800,000 kilometers of cables, and each meter is like a separate artery of civilization. But there's a detail that's not written about in textbooks, and you'll discover it only at the end of this video. Everything begins with selecting raw materials, high-quality steel wire that must possess exceptional strength and flexibility. These wires pass through a cold drawing process where thick steel rods are pulled through special holes, gradually reducing their diameter to thin but extraordinarily strong threads. This process doesn't simply make the wire thinner, it enhances its mechanical properties, making it resistant to breaking. Imagine that each meter of this wire can withstand enormous loads whilst remaining flexible and elastic. After the wire is ready, the most interesting part begins, forming the steel cable. Dozens and sometimes hundreds of such threads are twisted into strands, then woven into complex structures. Each wire layer has its purpose. Internal threads bear the main load, whilst external ones protect against wear and corrosion. The entire process resembles creating living tissue, where each thread is a separate vein that together forms a strong and reliable whole. Particularly impressive is the precision and control with which these cables are manufactured. Each stage is accompanied by strict testing. They check tensile strength, resistance to bending, and impact of weather conditions. Testing is conducted using special equipment that simulates the loads the cable will experience during bridge operation. This is extremely important, as bridges often stand in human environments or in locations with aggressive climates. Thanks to these coatings, cables not only maintain their strength, but also extend the bridge's service life, ensuring safety and reliability. Imagine the production scale. Factories that can manufacture thousands of tons of steel cables annually, unwinding and weaving hundreds of kilometers of wire. American manufacturers, for example, have many years' experience and employ the most modern technologies, allowing them to create cables for the world's most famous bridges. It's known that American Bridge Company has laid over 800,000 kilometers of steel cables for suspension bridges. Another aspect that impressed me is the role of engineers and technologists who constantly improve production processes. They work to make cables even stronger, lighter, and more resistant to extreme loads. Using new alloys, improving twisting and coating methods, all this makes modern steel cables genuine masterpieces of engineering thought. During the tour, I saw how enormous spools of steel wire move smoothly along conveyors, how wire passes through cold drawing, and how craftsmen control every centimeter of this process. American manufacturers, such as American Bridge Company, have enormous experience in manufacturing steel cables for the country's largest and most famous bridges. They produce thousands of tons of cables annually using modern technologies and strict quality control. It's known that for suspension bridges, they use cables with multi-layered structure that can withstand loads of hundreds of tons per square centimeter. During Brooklyn Bridge construction, for example, each of the main cables consisted of 19 separate strands, and each strand of 278 wires. This provided an enormous strength reserve. Steel cable production in the U.S. is a combination of tradition and innovation, where the craftsmanship of engineers and technologists is complemented by automated lines and modern equipment. Each stage, from raw material selection to protective coating application, is controlled with maximum attention, as thousands of people's safety who daily use bridges depends on this. European enterprises, particularly in countries like Germany, France, Italy, as well as Ukraine, Romania, and Poland, play an important role in supplying steel cables for bridge construction of various scales. Modern bridges are the result of millennia of engineering thought development, where traditions, innovations, and the most modern materials combine. They not only perform the function of connecting shores, but also become city symbols, cultural monuments, and technical masterpieces. Modern engineering marvels include the Falkirk Wheel in Scotland, a unique rotating boat lift that connects two canals and allows lifting boats through 180 degrees. This structure is not only functional, but also impresses with its futuristic design. Cable-stayed bridges, such as the Golden Gate in San Francisco, demonstrate the application of steel cables that withstand enormous loads and ensure structure longevity.
A poisonous metal that saves lives. Sounds paradoxical, but it's true. Lead, one of the most toxic elements on Earth. It poisoned Roman emperors, killed thousands of workers, got banned from paint and gasoline. But without it, not a single car on the planet would start. Every second, the world produces 2 tons of lead. 85% goes into batteries, the heart of every vehicle. Lead shields doctors from X-rays and stops radiation at nuclear plants. The heaviest common metal you can hold in your hands, 11 grams per cubic centimeter. How do you get a bluish metal that kills and saves at the same time from silver ore? You'll find out why the Roman Empire fell because of lead pipes, how a lead-acid battery works, and why this ancient poison is still irreplaceable today. Watch till the end. The finale reveals the dark side of progress. This is the story of a metal humanity can neither embrace nor let go.
Lead's story begins deep in ancient times. About 7,000 years ago, people learned to smelt lead from ore. It was one of the first metals humans extracted from stone. Lead melts at a low temperature, just 627 degrees Fahrenheit. Even a campfire can melt lead ore. The ancient Egyptians used lead to make statuettes and cosmetics. Yes, women lined their eyes with lead-based white paint. The Roman Empire took lead use to absurd levels. Lead water pipes stretched throughout Rome. Wine was stored in lead amphorae. The metal made the drink sweeter. Wealthy Romans ate from lead dishes. Aristocracy sweetened wine with lead sugar, lead acetate, which actually tastes sweet. The result? Mass poisonings. Roman nobility suffered from gout, insanity, infertility. Many historians believe lead poisoning of the elite became one of the causes of Rome's fall. Emperor Nero, known for his madness, may have been poisoned by lead since childhood. In the Middle Ages, lead was used to make cathedral roofs, stained glass windows, and printing type. Alchemists considered lead the basest of metals and tried to turn it into gold. The 19th century brought a boom in the lead industry. Lead white became the foundation for paints, bright, durable, cheap. Lead coated toys, furniture, house walls. Children gnawed on lead toys and died from poisoning. Workers at lead plants perished by the dozens. Metal dust destroyed their nervous systems. In the 20th century, lead was added to gasoline as an anti-knock additive. Tetraethyl lead boosted octane ratings. Engines ran smoother. But exhaust fumes poisoned cities. By century's end, leaded gasoline was banned almost everywhere. Lead paints were banned too. Lead pipes replaced with plastic. It seemed the age of lead was over. But no, lead production kept growing because a new massive application emerged: car batteries. Where does lead come from today? The primary lead mineral is galena, lead sulfide, cube-shaped crystals, silvery gray with a metallic luster, extremely heavy, density of about 0.27 pounds per cubic inch. Galena often occurs alongside silver, zinc, copper. The largest deposits are found in China, Australia, the USA, Peru, Mexico. China produces half the world's lead, around 6 million tons per year. Lead is extracted through open-pit mining in quarries or underground mines. They blast the rock, crush it, grind it. The result is ore containing 3 to 10% lead. That's enough for industrial processing. The ore is enriched through flotation. Crushed ore is mixed with water and special reagents. Galena particles stick to air bubbles and float up, forming foam. Waste rock gets washed away. The concentrate contains up to 70. Lead concentrate gets roasted in massive furnaces at around 1800 degrees Fahrenheit. Lead sulfide transforms into lead oxide, releasing sulfur dioxide gas. They capture this gas and use it to make sulfuric acid. Nothing goes to waste.
Lead oxide gets mixed with coke and fluxes, limestone or quartz. Loaded into a shaft furnace. Hot air blasts in from below. Temperature climbs to 2200 degrees. Carbon reduces the lead oxide back to metal. Molten lead pools at the bottom of the furnace, a heavy gray-blue liquid. Lead is 11 times denser than water. Drop a steel ball into molten lead and it'll float right on the surface. They tap the melt from the furnace into ladles. The melt's still impure, contains copper, zinc, silver, gold. Yeah, lead ore often carries precious metals. Extracting them pays for part of production. Lead gets refined, purified. Heat it to 900 degrees and add zinc. Silver and gold dissolve in the zinc and float up. They skim them off.
The purified lead gets poured into ingots. A standard ingot weighs about 55 pounds and is the size of a brick, but it weighs like a bag of cement. Try lifting it. Lead is heavy and soft. You can cut it with a knife, scratch it with your fingernail. At room temperature, lead develops a dull oxide film, loses its shine. A fresh cut is silvery blue, beautiful, but goes dull within a minute. Lead doesn't rust in the usual sense. The oxide film protects the metal from further corrosion. That's why Roman lead pipes have survived 2,000 years. But the key property of lead is its toxicity. Lead and its compounds are poisonous. Once it enters the body, lead accumulates in bones, replacing calcium. It destroys the nervous system, causes anemia, damages kidneys and brain. Especially dangerous for children. Even tiny doses disrupt nervous system development. There is no safe level of lead in blood. Any amount is harmful. That's why working with lead demands the strictest safety measures: respirators, protective clothing, showers after every shift.
But if lead is so toxic, why do they keep producing it in such massive quantities? Because lead has properties that simply can't be replaced. First, its weight. Lead is 1.5 times heavier than iron. Second, it's soft and easy to work with. Third, it blocks radiation. Gamma rays and X-rays are absorbed by lead better than any other affordable metal. Only gold and tungsten are better, but they're way too expensive. So lead gets used for radiation protection. X-ray room walls are lined with lead sheets. Doctors and technicians wear lead aprons, weigh about 10 pounds, uncomfortable, but they protect. Containers for transporting radioactive materials are made from lead several inches thick. At nuclear power plants, lead is used in shielding systems. Viewing windows for observing reactors are made from leaded glass, transparent, but contains up to 70% lead oxide. This glass stops radiation while letting light through. Without lead, nuclear medicine and power wouldn't be possible.
But the main use of lead? Batteries. 85% of global lead production goes into lead-acid batteries. These are the most common type of battery on the planet. Every car with an internal combustion engine has one. 1 billion cars means 1 billion lead batteries. How does it work? Inside a plastic case, there are plates made of lead and lead dioxide submerged in sulfuric acid. During discharge, the lead and lead dioxide react with the acid, forming lead sulfate and water. Electrical energy is released. During charging, the process reverses. Electricity converts the lead sulfate back into metal and dioxide. This cycle can repeat hundreds of times. Lead-acid batteries are reliable, cheap, and can handle high currents. Perfect for starting an engine. A starter motor draws hundreds of amps. Lithium-ion batteries can't compete in this application yet. One car battery contains between 22 and 33 pounds of lead. It lasts 3 to 5 years, then gets recycled. Lead is the recycling champion among all materials. Up to 99% of lead from old batteries makes it back into production. An old battery gets dropped off at a collection point where it's disassembled and crushed. Lead plates are melted down, purified, and cast into ingots. A new battery contains up to 80% recycled lead. This makes economic sense. Secondary lead costs less than primary. And it's environmentally sound. No need to dig new mines. Global lead production runs about 12 million tons per year. Roughly half comes from recycled material. Lead prices hover around $2,000 per ton, cheap compared to other metals. Beyond batteries and radiation shielding, lead shows up in cable sheathing, ammunition, fishing weights, and wheel balancing weights, in construction for soundproofing and waterproofing. But these uses are gradually declining as manufacturers hunt for less toxic alternatives. Lead's future lies in batteries and radiation protection. Until someone invents a replacement, lead remains irreplaceable.
And just like that, traveling from silvery galena crystals through the inferno of furnaces at 1200 degrees and complex purification from impurities, lead emerges, the most contradictory metal in human history. A metal that poisoned Roman emperors and saves lives in hospitals. Banned in paints and toys, yet no car starts without it. Heavy, soft, toxic, but irreplaceable. This is the story of progress's dark side, how a poisonous element became the foundation of modern civilization. Every time you turn your ignition key, get an X-ray, or have a chest scan, know this: lead is working for you, shielding you from radiation, storing energy, starting engines. The paradox of a metal that kills when mishandled and saves when used right. 7,000 years alongside humanity, from ancient figurines to modern batteries. Lead is a reminder that progress always has a price, and that price is sometimes written on the periodic table with the symbol Pb, plumbum, from the Latin word meaning heaviness, the weight of choosing between toxicity and necessity. A metal humanity cannot abandon, no matter how hard it tries.
This ship doesn't go around the ice, it goes straight through it. 10 feet of frozen ocean, and it doesn't care. I'm standing in a shipyard where they're assembling the hull of a nuclear-powered icebreaker, and in front of me is a giant steel skeleton that will soon be working where temperatures drop below -50, and ice pressure can crush any ordinary structure like a tin can. You know, I usually go look at things you can touch without risking your cheek freezing to them, but today I slightly overestimated my ambitions. And right now, I'm going to show you how a machine is born that makes even the Arctic itself back down. The first thing that hits you at the shipyard isn't the size, though the future vessel stretches over 500 feet long, and individual hull plates run several inches thick. What stuns you is the steel itself. They don't use ordinary rolled stock here. An icebreaker hull demands special steel grades that stay flexible even in brutal cold. Regular steel turns brittle in the freeze. Strike it and it'll crack like glass. This stuff, though, has to take impacts from ice fields and not fail. The engineers explain it simply. The hull needs to give a little, flex slightly under pressure. Otherwise, the Arctic will just snap it. Massive steel plates arrive at the yard already rough processed from the rolling mill. Each plate weighs dozens of tons, and when the crane lifts one into the air, it looks like a chunk of an apartment building somebody randomly decided to relocate. But the icebreaker's shape doesn't appear all at once. First, these plates pass through giant rollers that slowly, with enormous force, bend them to the required angle, giving the metal that crucial curve without which the hull can't push ice aside. In front of me, steel rollers, each as thick as a decent tree trunk, stacked one above the other. Between them, they slowly feed a flat steel sheet. Heavy, rigid, seemingly completely inflexible at first glance. The operator gives the command, and the mechanism starts moving. The rollers rotate at low speed, but with massive force. The sheet gradually gets pulled inside, and at some point, you can see it start to change shape. First, it's a barely noticeable bend. Then the radius increases, and the metal's no longer flat. It curves smoothly, as if obeying someone's will. The sound here is unique, a muffled pressure, grinding, and a slight crackling, like the metal reluctantly gives in. I'm standing nearby and I hear how the steel literally groans under the load, a sound like you're pressing on something really stubborn and it's grudgingly surrendering. They might roll the sheet several times, adjusting the roller positions each time until they get the exact angle or curvature. And there in front of you is no longer just a piece of steel, but part of a future hull that perfectly matches its contours. By the way, if you're into stories about how seriously complex and powerful machines are built, hit subscribe so you don't miss the next episode. Now, let's keep going. Next comes the assembly of sections, and this looks like a giant construction set, except each block weighs as much as a small locomotive. Individual hull blocks are assembled in the shop. These can be sections 60 or even 100 feet long. Inside each block, there are already bulkheads, cable routes, and even foundations for future decks. In other words, the hull isn't built from scratch in one spot. It's assembled in pieces, like a puzzle, just really heavy and really hot to produce. I walk into the shop and there are finished sections already standing there. These aren't just sheets of metal, they're entire fragments of the future ship. Inside each one, you can see passageways, openings for cables, spots where pipes, wires, and entire life support systems will run later. Then these blocks are transported to the slipway and joined together. The cranes move in. They lift the section into the air slowly, smoothly, no sudden movements, and transport it to the slipway. There, they carefully lower it and fit it against the already installed parts of the hull. At this moment, you literally see separate pieces starting to come together as one. The future icebreaker takes shape right before your eyes. Welding is a whole different story. You can't just run a bead and go grab coffee. Every joint goes through multiple levels of inspection. First, the welder lays the main seam. Then they check it with ultrasound to make sure there are no voids or cracks inside. If something's off, they cut it out and do it over. I watched them redo one seam 3 times, and nobody even got stressed. That's standard practice here, because the price of a mistake in the Arctic isn't just a breakdown, it's a potential catastrophe. And that's how it goes. Every seam, every joint, along the entire length of the hull. We should talk about the hull shape. An icebreaker doesn't just have a strong bow, it's specifically designed to climb up onto the ice and break it with its own weight. That's why the bow section has that distinctive slope, and they reinforce it with extra layers of steel. In some spots, the thickness multiplies several times over, and inside they add ribs that distribute the load along the entire length of the ship. While I'm walking around here, there's constant movement everywhere. Cranes, platforms, people in hard hats, for whom all this is just another workday. Though honestly, when they're moving a whole section weighing dozens of tons right over your head, you kind of rethink the word ordinary. One of the engineers jokes that the scariest thing here isn't the cold or the metal, it's when someone forgets their lunch in the shop, because finding it among all this scale is practically impossible. When all the sections are connected, the hull starts taking its final shape. Its length becomes physically tangible. You walk alongside and catch yourself thinking it's like strolling past an apartment building, only horizontal. The height of the hull is impressive too. Several levels that will eventually become decks, engine rooms, and crew quarters. After that comes surface treatment. The metal gets cleaned, anti-corrosion coatings applied, painted with special compounds that reduce water friction and protect the hull from salt and ice. It looks like cosmetics for a giant, but in reality, this coating determines how many years the ship can operate without major repairs. And that's not an exaggeration. Arctic saltwater and constant ice friction can destroy unprotected metal in just a few seasons. Modern nuclear icebreakers can ram through ice up to 9 feet thick while underway, and the newest designs are rated for ice up to nearly 15 feet thick. Power, that's a whole other story. Heavy icebreakers can pump out over 75,000 horsepower, and without that, they simply wouldn't budge the ice. I'm standing here staring at this hull, and it hits me. This isn't a finished vessel yet. There's no reactor in here, no propellers, no control systems. But even now, the main thing is crystal clear. This is a structure built to battle the elements, where every millimeter of steel serves a purpose. And when she heads out to sea, she won't just sail. She'll carve a path where other ships wouldn't even dare to go. I'm gonna stick around here a bit longer. Listen to that metal grinding. Watch these machines come to life. Then head out to prep your next adventure. Because after something like this, you want to find something just as massive, just as complex, just as beautifully insane. When you stand next to a structure like this, you start seeing what humans can actually build differently. Not on a computer, not in theory, but right here, with hands, steel, and fire. And I think I've already got a couple ideas where to head next, so stick around. It's gonna be good.
Every second, 30 million microchips are manufactured worldwide. Smartphones, computers, cars, satellites, everything runs on one element. It's hiding in ordinary sand beneath your feet, but after an incredible transformation, it becomes the brain of digital civilization. That's silicon, the second most abundant element on Earth. Yet getting it pure is harder than extracting gold. You'll discover how sand is melted at temperatures hotter than the sun's surface, why a single gram of impurities can destroy a million chips, and how they create a material that's 99.999999999% pure. Watch till the end, because the finale reveals how a handful of sand gives birth to humanity's future. The story of silicon began in 1824 when Swedish chemist Jöns Jacob Berzelius first isolated this element from silica. He named it silicium, from the Latin silex, meaning flint. But back then, no one could have imagined that this gray steel metal would become the foundation of the 20th century's technological revolution. Pure silicon doesn't exist in nature. It's always bonded with oxygen, forming silicon dioxide, ordinary sand, quartz, rock crystal. The Earth's crust is 27% silicon. It's the second most abundant element after oxygen. Every rock, every grain of sand contains it. But turning this ubiquitous element into pure metal, that's a titanic task. The breakthrough came in the mid-20th century when scientists realized silicon could be a semiconductor. This meant it could conduct electricity better than an insulator, but worse than a metal, and that property could be controlled. That's how the idea of the transistor was born, and then the microchip. The first silicon transistor was created in 1954 at Bell Labs. From that moment on, Silicon Valley began, not just a place on the map, but an entire era. Today, global production of metallic silicon hits 9 million tons a year. China produces around 65% of all silicon, Russia about 8%, and Norway, Brazil, and the US split the rest. But this entire journey starts with one thing: sand. Not just any sand, but quartz sand, nearly pure silicon dioxide. It's mined in specialized quarries where silicon dioxide content exceeds 98%. The largest deposits of quartz sand are found in Norway, the US, Brazil, and Russia.
Massive excavators scoop up white sand that looks like sugar and load it into dump trucks. This sand heads to a metallurgical plant where modern-day alchemy begins.
Inside a giant industrial hangar sits a furnace that looks like a spaceship, an electric arc furnace. It stands 33 feet tall, 20 feet across. Inside, 3 massive graphite electrodes, each as thick as a telephone pole. When tens of thousands of amps surge through them, an electric arc forms between the electrodes, a miniature lightning bolt that hits temperatures of 3,600 degrees Fahrenheit. That's hotter than volcanic lava, hotter than the surface of some stars. Into the furnace goes quartz sand mixed with carbon, wood chips, coal, or petroleum coke. Carbothermic reduction begins, a chemical reaction where carbon rips oxygen away from silicon dioxide. The formula is simple, but the process? Pure hell. Silicon dioxide plus carbon at 4,000 degrees Fahrenheit turns into liquid silicon and carbon monoxide. The furnace roars like a jet engine. Inside, a fiery inferno rages. Molten silicon's heavier than slag, so it sinks to the furnace floor, forming a silvery lake of liquid metal. Every few hours, workers in fireproof suits open the tap hole, an opening at the bottom of the furnace, and molten silicon pours out in a blinding river of fire into special ladles. The stream's temperature? 2,700 degrees. The air around it shimmers with heat. Silicon gets poured into cast iron molds, where it slowly cools, turning into gray metallic ingots. This isn't pure silicon yet. This is metallurgical-grade silicon, about 98% pure. It contains impurities: iron, aluminum, calcium. For metallurgy or silicone production, that's good enough.
But for electronics, absolutely not. Microchips need silicon that's 99.999999999% pure. That means for every billion silicon atoms, there can be no more than 1 impurity atom. Reaching that level of purity is a task that borders on magic. Metallurgical-grade silicon heads to a chemical plant where the purification process begins. The silicon is crushed into powder and mixed with hydrogen chloride at temperatures of 600 degrees Fahrenheit. This creates trichlorosilane, a volatile, toxic liquid that boils at 90 degrees. It's an intermediate compound, but it's critically important. Trichlorosilane passes through a series of distillation columns, giant towers as tall as a 10-story building. The liquid boils, evaporates, condenses, boils again, and with each cycle, impurities get left behind.
After 100 cycles, you get trichlorosilane that's 99.9% pure. Now you need to turn it back into pure silicon. That's where the Siemens process comes in, one of the most beautiful and complex in metallurgy. Inside a sealed reactor, they install thin silicon seed rods. Purified trichlorosilane is fed in along with hydrogen and heated to 2,000 degrees Fahrenheit. At that temperature, the trichlorosilane breaks down and pure silicon deposits onto the seeds, building them up layer by layer, atom by atom. The process runs for several days. In that time, those thin rods grow into thick cylinders up to 8 inches in diameter and weighing up to 660 pounds. They look like giant gray icicles. This is polycrystalline silicon, the purest material humans have ever made. Purity reaches 11 nines, 99.999999999%. A single kilogram of this silicon costs anywhere from $20 to $50, tens of times expensive than metallurgical grade. The polycrystalline silicon gets chopped into chunks and shipped off to single crystal manufacturing plants. Here's where an even more remarkable process begins: growing a crystal. Yeah, growing it, like a plant. Chunks of polysilicon get loaded into a quartz crucible and melted at 2,592 degrees Fahrenheit, silicon's melting point. What you get is a mirror-smooth lake of molten metal. Then they slowly lower a seed crystal into the melt, a perfectly oriented piece of single crystal silicon. And they start slowly rotating it while simultaneously pulling it upward at a rate of a few millimeters per hour. The molten silicon crystallizes onto the seed, atoms locking into a perfect crystal lattice, copying the seed structure. The process is like pulling a giant sugar thread from syrup, except instead of syrup, it's molten metal at nearly 3,000 degrees Fahrenheit. After several days, a cylindrical single crystal grows from the melt, an ingot up to 6.5 feet long and about a foot across. It weighs up to 660 pounds. This is one continuous crystal where all trillions upon trillions of atoms are arranged in perfect order. This cylinder is called a boule or ingot. It's gray, smooth, with a metallic sheen. One of these ingots costs tens of thousands of dollars. The boules are sent for cutting. They're clamped into special machines and sliced by diamond saws into thin discs, wafers. Each wafer is about 700 micrometers thick, less than a millimeter. Cutting moves at a few centimeters per hour because the slightest vibration will shatter the fragile crystal. A single boule yields several thousand wafers. Each wafer gets ground and polished to a mirror finish. The surface must be absolutely flat, deviation no more than 1 nanometer across an area of 12 inches. That's like leveling a football field to within the thickness of a human hair. These finished silicon wafers are the foundation of all microelectronics. Photolithography imprints circuits onto them, billions of transistors just a few nanometers in size. A single 12-inch wafer can hold up to 1,000 processors or tens of thousands of memory chips. After etching, doping, and depositing metal contacts, the wafer gets diced into individual chips. Each chip is a complete microprocessor, ready to become the brain of a smartphone, computer, or car. The entire journey from sand to processor takes several months and passes through dozens of factories across different continents. This entire incredible journey, from a handful of sand in a quarry to a microscopic chip in your phone, shows how far humanity has come in understanding matter. Silicon gave us computers, the internet, artificial intelligence, spacecraft. Every day, 7 billion people hold devices in their hands that work because of this element. The global silicon wafer market exceeds $15 billion a year, and the microchip market, over $500 billion. All of it built on that same gray metal that was once ordinary sand. Silicon became the foundation of the digital era. Without it, there'd be no computers, no smartphones, no internet. We live in a silicon civilization without even thinking about it. And every time you touch your phone's screen, remember, beneath the glass, billions of transistors are working, made from that very same sand you walk on every day.
Every year, humanity discards more than 10 million tons of electronic waste. Of this, hundreds of thousands of tons are televisions, packed with precious metals, complex plastics, and even deadly toxic substances. But what happens to them after they leave our homes? Did you know that inside one old, bulky television set lies pure gold, silver, and components that could become the heart of new gadgets? This isn't just recycling. This is a high-tech treasure hunt. Today, we'll show you how the most advanced recycling facilities operate and why this process matters more than you might think. It all starts not at the factory, but in our homes and offices. Old, outdated devices are collected at specialized reception stations. In developed countries, this is a well-oiled system, from dedicated containers in supermarkets to trade-in programs run by major retailers. Modern recycling centers aren't grim rubbish tips, but gleaming high-tech facilities. Their primary goal is to extract all reusable materials as efficiently as possible, while safely neutralizing the toxic components hidden inside. At large-scale operations, television recycling is organized along automated production lines, where most processes are carried out by machines rather than people. The first stage at the facility is the medical examination and sorting. Televisions are separated into three main categories: bulky cathode ray tube monsters from the past, slimmer plasma panels, and modern liquid crystal displays. Each type requires its own entirely unique approach. Then the undressing begins. Robotic manipulators or workers strip away the plastic casings. This plastic is immediately sent to giant shredders where it's ground into tiny fragments which, after remelting, will become parts for new motor cars or casings for other electronics. Metal frames and fixings are also separated and sent to their own recycling line. Once the casing is removed, the defenseless innards of the television move on to the dismantling line. Old cathode ray tube televisions receive particular attention. They can genuinely be described as environmental dirty bombs. The most hazardous component is the cathode ray tube itself. It contains up to several kilograms of lead, which was used to prevent X-ray radiation, whilst the internal surface is coated with a layer of phosphor containing toxic rare earth metals. Consequently, they're dismantled with exceptional care, often by hand, within sealed chambers. First, a specialized heated wire or laser carefully separates the front clean glass from the rear lead-laden funnel. The glass is then cleaned, crushed, and sent for recycling, whilst the lead is extracted for manufacturing new batteries. Modern liquid crystal displays are no less hazardous. Hidden along the edges of the panel, thin as spaghetti, are fluorescent backlight tubes. Each of these tubes contains a small but highly dangerous amount of mercury. That's why LCD panels are dismantled in specially sealed boxes with powerful ventilation systems. Robotic arms or workers in protective suits carefully extract these tubes. They're placed in hermetically sealed containers and sent to specialized facilities where the mercury is safely extracted and purified for reuse. The liquid crystals sandwiched between the glass layers present another challenging component. They're extracted using chemical solvents. Plasma panels require their own approach. Unlike LCD displays, they don't contain mercury, but their cells use inert gases such as xenon and neon. The panels are dismantled, the gases are collected in special containers for reuse, whilst the high-quality glass that makes up the screen is crushed and purified. Once the screens and casings have been neutralized and sent on their separate ways, the most valuable parts remain on the conveyor belt, the circuit boards. This is where the precious metals are hidden. Copper wires, aluminum heat sinks, and other metallic components are separated and sent off for smelting. The most important and complex part is processing the printed circuit boards. It's in these boards, within the microchips and connectors, that you'll find microscopic yet incredibly valuable quantities of gold, silver, palladium, and other precious metals. First, the boards are shredded into fine particles. These particles are then sent to the chemical workshops. The most common extraction method is chemical leaching. The shredded boards are immersed in special acid solutions. To extract gold, they often use aqua regia, a mixture of concentrated hydrochloric and nitric acids, which can dissolve even this noble metal. After the precious metals have dissolved into the solution, the precipitation process begins. Special chemical substances are added to the liquid, which cause the pure metals to fall out as sediment. For instance, ferrous sulfate is used to precipitate gold. This gold sediment is then thoroughly washed, dried, and remelted into small but incredibly valuable ingots. Similar methods are employed to extract copper and silver, though using different, less aggressive acids or the electrolysis method. In the final stage, all the recovered materials, gold, copper, aluminum, glass, and plastic, are compressed into compact blocks. Each year, millions upon millions of televisions are discarded worldwide, with their combined weight running into millions of tons. In Europe alone, for instance, electronic waste exceeds 10 million tons annually, and a substantial portion of that comprises televisions and monitors. This staggering figure isn't merely a statistic, it's testament to our rapid technological advancement and its darker consequences. But there is encouraging news. Year on year, growing numbers of people are recognizing the importance of proper disposal. Hundreds of thousands of tons of old televisions now find their way to recycling facilities each year, helping us preserve our air, water, and finite natural resources. Here's what the real secret we mentioned at the beginning is all about. Your old television isn't rubbish, it's a genuine urban mine. A single ton of old circuit boards contains 40 to 50 times more gold than a ton of gold ore extracted from a traditional mine. Electronics recycling isn't simply about caring for the environment, it's an incredibly profitable business of the future. We've learned to extract the most valuable resources not from beneath the ground, but from what we ourselves have created and discarded. And every time you take an old television for recycling, you're not just getting rid of clutter. You're returning precious metals to the economy and helping to make our world a bit cleaner.
Take up a stone. Bright red, heavy, looking like dried blood. It doesn't smell, doesn't burn, doesn't radiate. Just a beautiful mineral. Now throw it into a furnace at 1300 degrees Fahrenheit and liquid metal flows out. Silvery, heavy, cold to the touch. The only metal on Earth that stays liquid at room temperature. Mercury. A substance that has mesmerized alchemists for millennia, poisoned kings, and powered industry. And it's extracted from a stone that looks like a gemstone, but is actually just ordinary sulfide. Today, we're at a mine and processing plant where red rock turns into liquid silver. If you're into deep dives like this, subscribe and hit the bell so you don't miss new episodes. This red rock is called cinnabar, mercury sulfide, one of the few natural compounds where mercury shows up in Earth's crust. The chemical formula is simple: one mercury atom, one sulfur atom. Basically, nature locked liquid metal inside a sulfur cage, and to get it out, you've got to break that cage with heat. If you crack a chunk of cinnabar, the fracture surface reveals crystals with a diamond-like shine. The beauty's deceptive because the powder from this mineral is poisonous. Cinnabar was known even in ancient times. Egyptians used it as pigment, Romans painted palace walls with it, and Chinese alchemists believed the red ore was the key to immortality. Deposits are scattered across the planet, but the main ones are in Spain, Slovenia, China, and Kyrgyzstan. The Spanish mine at Almaden operated for nearly 2,000 years and gave the world more than a third of all mercury ever extracted. The ore sits in volcanic activity zones because mercury rises with hot solutions from deep within Earth's crust and settles in rock fractures as bright red veins. Sometimes cinnabar is so rich that the rock looks like someone painted it with scarlet dye. Mining starts underground. Miners drill into the rock with pneumatic jackhammers, place charges, and blast, bringing the whole face down. They load the ore into mine cars and haul it to the surface. It's hard, dangerous work. Even down in the mine, mercury vapor seeps from the rock, so ventilation runs at full blast. Mercury content in the ore is usually low, 1 to 12%. The rest is waste rock, sandstone, clay, quartz. But even 1% is worth going after because mercury fetches a high price. At the surface, the ore gets crushed in jaw crushers. 2 steel jaws squeeze the rock, breaking it down to gravel size. Then, vibrating screens sort the pieces by size. The fines go straight to the furnace. Oversized chunks loop back for another round of crushing. Dust is a whole other problem. It carries mercury, and breathing it is dangerous. So the crushing plant runs heavy exhaust and wet dust suppression. Workers wear respirators, and at the entrance, there's a mercury vapor monitor. If the needle swings into the red, they shut down the plant and air it out. Now comes the most critical step, roasting. The principle is simple yet brilliant. Heat cinnabar to 1100 to 1300 degrees Fahrenheit in air, and the sulfur bonds with oxygen and escapes as sulfur dioxide gas, while the mercury vaporizes. 2 substances locked in stone for millions of years part ways forever, one into the air, the other into a pipe. Roasting furnaces come in different designs, but the classic is a rotary kiln. Picture a massive steel drum, 60 to 100 feet long, set at a slight angle. Ore gets fed in from the upper end, burners fire from the lower. The heat inside is so intense, the furnace walls glow a dull cherry red. The kiln rotates slowly, tumbling the ore, gradually pushing it downward as it heats up more and more. When the temperature hits the sweet spot, the cinnabar breaks down. Sulfur burns with a bluish flame, and mercury vapor, invisible and deadly, rises and travels with the flue gases into the condensation system. The spent rock, now stripped of mercury, spills out the lower end of the furnace into a waste pile, gray, lifeless, having surrendered everything valuable to the fire. Condensation is the moment when invisible vapor transforms into that actual liquid metal. Gases from the furnace pass through a long system of pipes and chambers that gradually cool down, usually with water fed through jackets on the outside. Mercury condenses first. Its boiling point is only 675 degrees Fahrenheit, so when the gases cool below that mark, silvery droplets start settling on the condenser walls. They trickle downward and collect in receivers, steel or ceramic containers. The sight is mesmerizing. From the pipe, as if from nowhere, heavy silvery liquid drips down, falling into the collector with a distinctive, soft sound. Not a clang, not a thud, but something in between. Because mercury is viscous and heavy, 13.5 times heavier than water. A quart of mercury weighs more than 28 pounds. Try picturing a quart of milk that weighs as much as a bucket of cement. The raw mercury from the condenser isn't ready for sale yet. It's swimming with impurities. Soot particles, water droplets, traces of other metals. It's cleaned in several stages. First, they filter it through chamois leather or special fabric. Mercury passes through the pores while the dirt stays behind. Then, they wash it with diluted nitric acid, which dissolves impurities like zinc, lead, and tin, leaving the mercury itself untouched. The final purification is vacuum distillation. Mercury gets heated in a vacuum, where it evaporates at a lower temperature, while impurities with higher boiling points remain at the bottom. They collect the condensate, and now you've got mercury at 99.9% purity. It's poured into standard steel flasks holding 76 pounds. That's the international standard called a flask. The container's small, about the size of a thermos, but lifting it one-handed? Not easy. All because of that incredible density. Safety at a mercury plant is a world unto itself. Mercury vapor has no color and no smell, but it's extremely toxic. Just a few hours of breathing it can give you serious poisoning. Chronic exposure destroys the nervous system. That's why hatters in the 19th century went mad. They used mercury to treat felt and inhaled the fumes for years, hence the phrase, mad as a hatter. In a modern plant, the entire facility operates under negative pressure. Air is constantly pulled inward, not pushed outward, so vapors don't escape into the atmosphere. Floors are coated with a special non-porous covering. If mercury spills, the droplets won't roll into cracks, but stay on the surface where they can be collected with a specialized vacuum or a sulfur trap. Sulfur powder binds mercury into harmless sulfide. Every worker carries a personal dosimeter that measures accumulated vapor exposure per shift. Exceed the limit, and you're pulled off the floor until your levels normalize. Where does all this mercury go? Historically, the biggest consumer was gold mining. Mercury dissolves gold, forming an amalgam. You then heat it up, and the gold evaporates out. Conquistadors in South America used this method, and it's exactly why the Spanish crown exploited almaden for centuries. Today, amalgamation is officially banned in most countries because of the catastrophic environmental damage. But in artisanal mining across Africa and Southeast Asia, millions of prospectors still use it. Poisoning rivers, poisoning soil. Other applications? Chlor-alkali industry, thermometers, barometers, mercury lamps, electrical switches, catalysts. But the world is slowly moving away from mercury. In 2013, the Minamata Convention was signed, named after a Japanese city where, in the 1950s, thousands of people suffered devastating poisoning. Mercury leaked into the bay from a chemical plant. It built up in fish. And the people who ate that fish started losing their sight, their hearing, their coordination. The Minamata tragedy became a symbol of mercury pollution for decades to come. Mercury production worldwide is plummeting. Back in the mid-20th century, mines pulled out up to 10,000 tons a year. Now, less than 2,000. Most mines have shut down. The famous Almadine in Spain stopped operations and turned into a museum. These days, mercury increasingly comes from recycling, old thermometers, lamps, industrial waste. But humanity can't completely abandon it yet. Some chemical and electrochemical processes simply have no substitute. When you stand next to a flask where this heavy, silvery liquid sloshes around, it's hard to believe that an hour ago it was part of a red rock that sat underground for millions of years. Cinnabar guarded mercury like a safe guards valuables, and only fire could pick that lock. An ancient process, simple at its core, dangerous in execution, and still without an alternative. Picture this, a sheet of aluminum, 4 millimeters thick. You can bend it with your bare hands, scratch it with a key, punch through it with a hammer. Now imagine that exact same material is what makes up the wing you're sitting on at 36,000 feet. That wing's carrying 300 tons at 550 miles per hour, and it doesn't break, doesn't bend, doesn't crack. For decades. How does a 4 millimeter sheet transform into a structure you trust with your life? Today we're going behind the scenes at an aircraft manufacturing plant where they press wings and fuselages for passenger jets, and I'm going to show you every single step of that journey. If you're into deep dives like this, hit subscribe and ring that bell so you don't miss new episodes. It all starts in the raw materials warehouse. And the first thing that hits you is the scale. Aluminum sheets and plates are stacked several meters high, each sheet marked with its alloy designation. Aviation doesn't use regular aluminum. They use 2000 and 7000 series alloys, enhanced with copper, zinc, and magnesium. These additions make the metal several times stronger than pure aluminum, while keeping its light weight. Every batch arrives with a passport, chemical composition, mechanical properties, ultrasonic inspection results. If even one parameter falls outside tolerance, the entire roll goes back to the supplier. There's no such thing as good enough here. The cost of a mistake is measured in human lives. From the warehouse, sheets travel to the cutting shop on special carts, with soft padding to prevent surface scratches. Laser and water jet cutters slice blanks from digital templates, each part cut to within tenths of a millimeter. A single wing skin set comprises hundreds of parts in different shapes and thicknesses, and each one has its own unique number in the engineering documentation. Now for the most spectacular part, forming. That flat sheet needs to become a panel with precise curvature, matching the aerodynamic profile of a wing or the roundness of a fuselage. For this, they've got presses that'll take your breath away. The hydraulic stretch press for skin forming. This machine stands as tall as a 3-story building, with force measuring tens of thousands of tons. The aluminum sheet gets clamped along the edges by special grips. A massive steel die, the punch, rises from below with the exact shape of the future panel, and the press slowly, inch by inch, stretches the sheet around this form. The metal stretches, takes on the curvature, and stays that way forever. The sound, a deep, heavy groan of metal that makes the floor vibrate under your feet. The entire pressing cycle takes several minutes, but prepping for one cycle? Hours. Setting up the die, calibrating the force, checking the sheet temperature, because cold aluminum behaves completely differently than warm. For fuselage panels, they use a different method, shot peen forming. It looks almost absurd. They lay a flat sheet on a table and blast it with steel balls about a millimeter in diameter from special nozzles under pressure. The balls hammer the surface at enormous speed, creating thousands of microscopic dents. The top layer of metal stretches while the bottom stays the same, and the sheet starts to curve on its own, like running scissors along a ribbon and watching it curl into a spiral. By controlling the intensity of the bombardment and the impact zone, you can achieve precisely the curvature you need, that signature fuselage roundness. The method seems crude, but the precision is stunning, within tenths of a millimeter on panels several meters long. After forming, each panel gets checked with a laser scanner. The beam sweeps across the entire surface, building a three-dimensional model of the part that's overlaid on the digital reference. The computer highlights deviation zones, and if even a single point falls outside tolerance, the panel goes to scrap or rework. The formed panels aren't wings or fuselage yet. They're just skin, a thin shell that can't handle anything serious on its own. To make it withstand flight loads, internal structural elements are attached from the inside, stringers and frames. Stringers are long profiles running along the structure. They handle tension and compression. Frames are cross-sectional rings that maintain the shape. Together, they form a skeleton to which the skin gets riveted. And this sandwich of shell and framework can now bear enormous loads. And here begins the most painstaking work, riveting. A single wing on a passenger jet has several 100,000 rivets. Each one is made from a special aviation alloy. Each one goes into a drilled hole with precision down to a few thousandths of an inch. Automated riveting machines place up to several thousand rivets an hour. The robot drills the hole, inserts the rivet, bucks it, and immediately checks the force. But there are places the robot can't reach. That's where people work. A riveter with a pneumatic hammer and bucking bar is one of the most respected workers on the aircraft factory floor. While the skin is being made, they fabricate the spars, the main load-bearing beams of the wing. These are the most heavily stressed parts in the entire aircraft. The whole fuselage hangs from them, along with passengers, fuel, and cargo. A spar for a large airliner is a single piece up to 115 feet long, milled from a solid aluminum plate several inches thick. A 5-axis machine removes up to 90% of the original metal, leaving behind a complex landscape of ribs, webs, and flanges. Milling a single spar takes up to 24 hours of continuous operation. The cutting tool follows its programmed path inch by inch, and you can't stop the process because any pause will leave a mark on the surface. From a plate weighing several tons, you get a part that weighs 10 times less but can carry loads of hundreds of tons. The chips don't go to waste. They're collected, pressed into briquettes, and sent back for remelting. When all the parts are ready, assembly begins. The wing is assembled in a special jig, a massive steel frame as long as the wing itself, holding every component in its exact position. First, they install the spars, then the ribs, transverse frames that define the aerodynamic profile, followed by the stringers, and finally, the skin. Panels are fitted and riveted one after another. At every stage, inspectors check gaps, alignment, and rivet tension. The tolerance for panel fit-up is 0.3 of a millimeter. If the gap is larger, the panel comes off and gets refitted. Assembling one wing takes about 2 weeks. The fuselage is built in sections: nose, center, tail, and each is finished completely on its own. Then they're joined into a single tube. The moment of joining is an incredible sight. 2 enormous cylinders, several meters in diameter, slowly approach each other on rails, slide together with a gap measured in fractions of a millimeter, and lock in place with thousands of bolts and rivets. After assembly comes sealing. Every seam, every rivet hole in the fuselage gets coated with a special sealant that turns flexible and waterproof when it cures. Without it, at 36,000 feet, where pressure is 4 times lower than at sea level, air would leak through microscopic gaps, making it impossible to keep the cabin pressurized. After sealing, they close up the fuselage and pump in pressure, simulating flight conditions. Sensors all over the body track leaks. If air's seeping out somewhere, they hunt it down, find it, fix it. Only after passing that test does the section get cleared. The wing goes through its own trials. They mount it in a test rig and bend it upward with hydraulic cylinders, slowly, carefully, measuring deflection at hundreds of points simultaneously. The wing has to withstand bending several feet upward without breaking. It flexes like a bow, but doesn't snap. During certification tests, they bend the wings until they actually break to know the exact failure limit and confirm it exceeds the design spec with margin to spare. Once the wing and fuselage pass every inspection, they're hauled to final assembly. That massive hangar the size of several football fields, where ceilings soar 10 stories high. Here, wings mate with the fuselage through the central keel beam. Landing gear gets installed, engines hang beneath, cockpit and systems go in. From separate sections, an airplane is born. The entire journey from flat sheet aluminum to finished wing, that's months of work, hundreds of operations, millions of control points. Every rivet recorded in a passport, every seam documented, every panel with its own story, from metal smelting to the machine number that formed it. Next time you sit by the window and look at that wing, remember, This structure started as a flat sheet barely a sixth of an inch thick, and every fraction of that journey, someone's work, someone's inspection, someone's craft.
Every year, the world extracts over 8 million tons of gray, unremarkable ore, but only a tiny fraction of it undergoes an incredibly complex, almost alchemical journey to become a metal capable of withstanding even spaceflight. Titanium isn't just a metal. It's a substance born in hell from fire, chlorine, and magnesium at temperatures exceeding 1,000 degrees Celsius. Its first form looks like light ash, but from it they create the invisible skeleton of aircraft, eternal implants, and rocket engines. How does a chunk of dirty rock transform into a material stronger than steel yet lighter than aluminium? Watch to the end, and you'll see how an ordinary stone passes through chemical purgatory to become the heart of modern civilization. The history of titanium is the story of a ghost metal that remained hidden in plain sight for decades. In 1791, British clergyman and amateur geologist William Gregor, while studying black sand on the Cornish coast, discovered traces of an unknown element within it. But only 4 years later, in 1795, the great German chemist Martin Klaproth independently discovered the same element and named it titanium, after the mighty Titans from ancient Greek mythology. However, despite its thunderous name, the metal remained elusive. For nearly a century and a half, it slumbered in chemistry textbooks, resisting attempts to isolate it in pure form. Only in the 20th century, thanks to breakthroughs by American chemist Matthew Hunter and Dutch scientists, did humanity finally manage to touch pure titanium. From the mid-20th century, with the onset of the Cold War and the space race, titanium transformed from a laboratory curiosity into a strategic material. The United States, recognizing its colossal potential, invested enormous sums into its production. Titanium became the foundation for the legendary spy plane SR-71 Blackbird, capable of flying at the edge of space, and found its place in the construction of Apollo spacecraft. Titanium production begins with mining its ores, ilmenite and rutile. These minerals are found in the sands of Australia, Canada, and South Africa. After extraction, the ore undergoes multi-stage enrichment. It's washed, screened, separated from waste rock using magnets and gravity, yielding a dark, heavy concentrate. But this still isn't metal. This is merely titanium oxide, where it's firmly bound to oxygen. To break these molecular shackles, the concentrate is sent to chemical hell, into fluidized bed reactors. Here, at temperatures of 1,000 degrees Celsius, gaseous chlorine is blown into a boiling layer of ore and coal. A fierce chemical reaction begins. Chlorine tears titanium away from oxygen, forming a volatile compound, titanium tetrachloride. This caustic, toxic substance is then repeatedly distilled, purifying it from impurities to near-perfect purity. The next stage is the heart of the entire process, named after its creator, William Kroll. Into a sealed steel sarcophagus filled with inert argon gas, molten magnesium is placed. Then purified titanium tetrachloride is slowly fed in. A chemical duel begins. Magnesium, being a more reactive metal, literally rips chlorine atoms away from titanium. As a result of this battle, pure titanium settles at the reactor's bottom, but in the strangest and most unremarkable form imaginable. This is sponge titanium, a porous, lightweight gray mass that looks like frozen foam or pumice. It's brittle and utterly unlike strong metal. But inside this ugly porous sponge lies all the future might. This sponge is extracted, crushed, and then pressed under enormous pressure into dense briquettes. and only then is it sent to its final transformation, into the melting furnace. To transform sponge briquettes into a monolithic ingot, they're melted in vacuum arc furnaces. This is necessary because at high temperatures, titanium absorbs oxygen and nitrogen from the air with incredible greed, instantly making it brittle. Inside a sealed chamber, a powerful electric arc, like lightning, melts the briquettes, and liquid titanium flows into a copper, water-cooled mold. To achieve perfect uniformity, this process is repeated twice, sometimes even thrice. The result is a gleaming, silvery ingot of pure titanium, ready for further processing. Just look at this incredible transformation, from porous, lightweight sponge to dense, shining metal. But pure titanium is merely the beginning. To create materials for aviation and space, it's transformed into alloys. To molten titanium, like spices in a chef's dish, other metals are added: aluminium for lightness, vanadium for strength, molybdenum for heat resistance. Thus is born, for example, the most famous titanium alloy, T6Al4V, which became the workhorse of the aerospace industry. These alloys are remelted several times to achieve perfect uniformity. The next stage is mechanical processing. Giant ingots are heated red hot to make them malleable and sent under presses or rolling mills. With incredible force, machines bend the metal to their will, transforming it into sheets, rods, beams, and wire. From these semi-finished products, the most complex parts are then cut, turned, and milled. But that's not all. In recent years, additive technologies, or three-dimensional printing, have entered the game. Special printers sinter the finest titanium powder layer by layer with lasers, growing parts of such complex geometry that traditional methods cannot achieve. This allows creation of lighter and stronger components for aircraft and rockets, saving up to 40% of weight. Every finished part undergoes the strictest control. It's X-rayed, scanned with ultrasound, checking for the slightest internal defects. In aviation, titanium has become indispensable. From it, they make up to 15% of a modern passenger airliner's weight, landing gear, wing elements, and of course, engine components. This significantly reduces the aircraft's overall mass and increases its fuel efficiency. In the medical field, roughly 70% of all implants, such as artificial hip joints or dental prosthetics, are made from titanium. Its unique biocompatibility means the human body doesn't reject it, allowing bone tissue to literally grow into the implant surface. This is a metal that becomes part of a person. Thus, having passed through fire and chemistry, an unremarkable stone transforms into high-tech material that pierces the heavens, explores space, and restores people's ability to move. But titanium conquered not only the sky, but also the darkest ocean depths. At the height of the Cold War, Soviet engineers created something unthinkable: submarines of Project Lyra, known to NATO as Alpha. Their hulls were made entirely from titanium. This allowed them to dive to depths unreachable by the enemy and develop underwater speeds exceeding those of torpedoes. These goldfish, as they were nicknamed for their incredible cost, became underwater phantoms, invulnerable to magnetic detectors and capable of escaping any pursuit. Titanium is the only material capable of withstanding the colossal pressure at depths of 800 meters whilst remaining sufficiently light. Moreover, its absolute resistance to corrosion in salt water makes it an eternal material for the marine element. So what's titanium's main secret, promised at the beginning? It's not just its strength or lightness. Its true magic lies in its ability to self-heal. Every time titanium's surface is scratched, it instantly reacts with oxygen from the air or water and covers itself with the thinnest, invisible, yet incredibly strong film of titanium oxide. This is a sort of invisible armor that instantly regenerates when damaged. It's precisely this film that makes it absolutely inert, preventing it from reacting with the human body or aggressive environments. But this superpower has another side, another secret. During mechanical processing, if proper technique isn't followed, fine titanium swarf can spontaneously ignite. This white fire burns at such high temperatures that it's impossible to extinguish with water or sand. Taming titanium is playing with fire in the literal sense. And only those who've mastered this art can make this mythical metal serve humanity.
Every year, humanity throws away more than 50 billion batteries. That's enough to build a tower all the way to the moon. Mountains of toxic metal and chemicals that could become raw material for new life instead of poisoning the planet. But what happens next to all these power sources? Where do they end up after the charge dies in your phone, laptop, or electric car? Behind the plain doors of an ordinary collection point hides an entire industry of the future. This is a world of giant shredders that grind metal into dust, magnetic separators that sort the invisible, and furnaces reaching temperatures of 3,000 degrees Fahrenheit, hotter than the mouth of a volcano. And here's the best part. By the end of this video, you'll find out what actually happens to the lithium that once lived inside your battery and why this process is called urban mining for 21st century treasures. The path to rebirth doesn't start at the factory, it starts in our hands. Collecting used batteries is a massive logistical operation spanning the entire country. Regular people drop off tiny batteries from phones and laptops into special bins installed at electronics stores and supermarkets. Auto shops, like hospitals for cars, pull out massive battery packs from electric vehicles, hundreds of pounds each. Industrial facilities running heavy machinery turn in their spent power sources by the ton. It's like thousands of streams flowing into one big river. Old batteries from factories and auto shops get hauled in armored trucks to regional collection centers. Here's what's interesting. Modern smart collection containers have sensors that track fill levels in real time. When a container's almost full, it automatically sends a signal to the logistics company, which plans a pickup route. When mountains of collected batteries arrive at the sorting facility, one of the most complex and critical stages begins. Batteries come in dozens of different types. Lithium-ion, like the one in your smartphone, nickel metal hydride from old toys, lead acid from cars. Mixing them during recycling is like mixing sand with sugar. At small collection centers, workers sort batteries by hand, like jewelers, relying on markings and appearance. But at large-scale facilities, technology takes over. Batteries move along conveyor belts under the watch of artificial intelligence. Computer vision systems equipped with X-ray and spectroscopic scanners identify the chemical composition of each battery in fractions of a second. Robotic arms snatch the right types from the stream at lightning speed and sort them into different containers. Despite automation, human oversight remains irreplaceable. Operators, like air traffic controllers, monitor the machines and step in when things get complicated. If a battery has a damaged casing or missing labels, only a human can make the right call. This is especially true for the massive batteries from electric vehicles. These giant blocks, weighing up to half a ton, are dismantled into smaller modules using specialized robots, but the final cell sorting is often done by hand. It's painstaking and dangerous work that demands total focus. At the end of the day, every properly sorted battery isn't just a piece of metal. It's a chance to return the most valuable rare earth elements, like cobalt and lithium, back into the economy, and to reduce the enormous damage caused by mining them in the first place. After sorting, the batteries head to their execution, the shredding floor.
they fall into the steel jaws of a giant shredder. This is a true industrial monster, whose hardened steel blades can grind up even the armored casing of an electric vehicle battery. Inside the protected chamber, total metallic chaos unfolds. Deafening roars, grinding, and cracking. Batteries literally torn into tiny pieces. But this process is extremely dangerous. Any energy left in a battery can lead to fire or explosion. To prevent this, engineers developed several brilliant solutions. Before shredding, batteries are often subjected to cryogenic freezing in liquid nitrogen at temperatures of -320 degrees Fahrenheit. This not only makes the metals more brittle, but also completely neutralizes any chemical activity. Some shredders operate in sealed chambers filled with inert gases to eliminate contact with oxygen.
The shredded pieces pass through a system of magnetic separators that pull steel, nickel, and cobalt from the stream with incredible precision. But the most valuable thing is the fine black powder that settles in specialized dust collectors. It's known as black mass. Right here in this unremarkable-looking dust lie the real treasures of the 21st century: lithium, cobalt, manganese, and graphite. Plastic residue and traces of electrolytes get washed away with special solutions. Engineers in armored control rooms monitor the process through thick glass, controlling temperature and pressure. If a battery does explode, the system instantly snuffs out the flash, and the process doesn't stop for a second. Once the precious black mass has been extracted from the chaos of shredded batteries, the real alchemy begins. Metals that seemed forever locked inside old batteries are recovered using two main methods: hydrometallurgy and pyrometallurgy. Hydrometallurgy is a process similar to cooking up a complex chemical soup. The black mass is plunged into massive reactors filled with acid solutions, typically sulfuric or hydrochloric acid. With constant stirring and heating, metals, lithium, cobalt, nickel, literally dissolve, transitioning into liquid form. To extract a specific metal from this soup, an ion extraction process is used. Special reagents are added to the solution that selectively bind to only one metal, like a key to a lock. As a result, each metal settles into a separate layer. If hydrometallurgy is delicate chemistry, then pyrometallurgy is the primal force of fire. Here, everything literally burns and melts. The black mass gets loaded into a massive arc furnace, where temperatures reach nearly 3,000 degrees Fahrenheit. At that kind of heat, metals melt, and plastic and other organic remnants simply burn away. The molten mass separates under gravity, like oil and water. Heavier metals, such as cobalt, nickel, and copper, sink to the bottom, forming a valuable alloy. The lighter lithium stays in the top layer, in what's called slag. Then this slag is extracted and processed separately to obtain pure lithium. This method is faster and handles larger volumes, but it's also more energy intensive. After cooling, the extracted metals emerge as the purest ingots, shiny, smooth, and ready for their second life. Cooling after the pyrometallurgical process is just as critical a stage. If you simply let molten metals cool in open air, it can take several days and lead to uneven crystal structure formation, which degrades quality. That's why cooling is always controlled. Ingots might move slowly along a conveyor beneath powerful fans. It's like a giant hairdryer that quickly yet evenly cools the surface. For an even faster process, red-hot ingots can be plunged into massive tanks of water or special cooling fluids. It's an incredible sight, glowing metal hitting water instantly shrouded in clouds of hissing steam. Sometimes they use combined cooling too, air cooling first, then water cooling, to reduce internal stress in the metal. Controlled cooling ensures a uniform metal structure, which is critical for reuse, especially in manufacturing new high-tech batteries. The recovered lithium, now in the form of ultra-pure lithium carbonate, heads back to factories to become the heart of new batteries that'll power electric cars or even your phones. Nickel can become part of super strong alloys for turbines that generate energy from wind, and cobalt becomes an irreplaceable component in complex medical equipment. We're literally closing the loop. Old, discarded batteries give life to new, cutting-edge technologies. Tossed batteries, they can become a full-blown environmental disaster. First, they're packed with toxic heavy metals that seep into landfills, contaminate soil, poison groundwater, and wreck everything around them. Second, mining new rare earth metals is an incredibly dirty, destructive process that drains natural resources and devastates ecosystems on a massive scale. Recycling tackles both problems at once. And here's the real power move. The more batteries we recycle, the less we depend on unstable raw material supplies from other countries, strengthening our technological independence. Despite lithium's critical importance, only about 1% of this metal gets recycled globally today. The main reason? High costs and complex processes. But right now, researchers around the world are developing new, cheaper technologies that could dramatically change the game in the coming years.
A plane that looks like a whale flies through European skies. It doesn't carry passengers, it carries other planes. Wings 100 feet long, fuselage sections as tall as a house. This is the Airbus Beluga XL, Europe's biggest cargo plane, 112 tons of freight, a cargo hold 29 feet across. Inside, it can fit 2 Airbus A350 wings at once. Without the Beluga, Airbus production would stop in a week. Today, we'll see how this giant is born, from an aluminum sheet to the first roar of its turbines. The Beluga XL is a puzzle made from parts created at 5 points across Europe. The base, an Airbus A330. Its lower fuselage, wings, and landing gear are assembled in Toulouse. But the nose section? That's made by Stelia at their plant in Mayotte, France. 40 feet long, 18 tons. Inside, the cockpit, avionics, hydraulics. All on a plug-and-fly principle. Panels from aluminum alloy 2024 with copper and magnesium are formed on presses capable of 1,300 tons of force. The frame is assembled from bulkheads and stringers, then the skin is riveted on top. 12,000 rivets, each about 1/6 of an inch in diameter for a single nose. The upper expanded fuselage, the heart of the Beluga, is produced by Premium Aerotech and Dehard. 3 sections, 2 side panels and a roof. 29 feet in diameter, nearly 6 feet wider than the previous Beluga. Sheet thickness ranges from 1/10 to 1/4 inch. Each panel is reinforced with 30 stringers. Bulkheads are placed every 20 inches. Everything's riveted and bolted with titanium bolts, torqued to 90 foot-pounds. The cargo door, an engineering marvel. Stelia Rochefort, France. 33 feet long, 26 feet high. Area nearly 1,500 square feet, like a basketball court standing vertical. Weight 3.1 tons. Frame made from titanium alloy, Ti6Al4V. Titanium handles the loads. 24 latches hold the door, 12 on each side. Each latch clamps down with 3 tons of force. The door opens with 4 hydraulic cylinders, piston diameter 4.7 inches, pressure 4,000 psi. 3 minutes to open, 4 to close. Inside the door, hundreds of yards of wiring and hydraulic lines. They shipped the door from Rochefort to Toulouse on a barge, the same one that carried A380 sections. By sea to Bordeaux, by river to Langon, then 125 miles by road. The tail section, modified by Spain's Aeronova in the Basque Country. The vertical stabilizer increases by 50%, from 33 to 50 square feet. The massive bloated fuselage creates serious drag. You need stability. They add vertical end plates to the horizontal stabilizer, plus 2 ventral fins under the tail. 5 vertical surfaces total instead of 1. Everything's made from composites, carbon fiber, layers of carbon fabric soaked in epoxy resin, laid in a mold and into the autoclave. 360 degrees Fahrenheit, 100 pounds per square inch, 8 hours. The composite fin weighs 1,300 pounds instead of 2,000 aluminum. December 2016, Toulouse. Line L34, a hangar spanning 130,000 square feet. Final assembly of the first Beluga. Lower fuselage with wings from an A330 goes on the jig. From above, a 50-ton crane lowers the expanded upper fuselage. They mate the perimeter. Hundreds of bolted connections. They drill quarter-inch holes through both sections at once, tolerance plus or minus 0.04 of an inch. Bolts get torqued with computer-controlled wrenches. The joint sealed with polysulfide compound works from -76 to +250 Fahrenheit. They mount the nose section, tail, vertical stabilizer. 3 months of work. Meanwhile, the guts. 50 miles of wiring in bundles of 50 to 100. 2,000 feet of stainless hydraulic lines. Pressure 4,000 pounds per square inch. 12 fuel tanks. 37,000 gallons of kerosene. March 2018. Engine installation. 2 Rolls-Royce Trent 700s. Each one weighs 12.3 tons. Thrust? 320 kilonewtons, 72,000 pounds of force. Fan diameter, 9 feet. 24 composite blades with titanium leading edges. The engine mounts to the wing through a titanium pylon with 4 bolts, each 1.9 inches in diameter. Torque, 2,950 pound-feet. 37 connections to each engine. Fuel, electrical, hydraulic, pneumatic. April through June, ground testing. 200,000 checkpoint inspections. Every sensor checked, every actuator verified. Flight control checks. Elevators deflect 25 degrees up, 15 down. Ailerons, 25 up, 15 down. Laser sensors monitoring. Accuracy to within 0.5 degrees. July 19, 2018, Blagnac, Toulouse. First flight, crew of 6, 150 sensors recording 200 parameters 1,000 times per second. Takeoff thrust 96%. Turbine exit temperature 2,700 degrees. Fuel burn 12 tons per hour. 120 knots, 222 kilometers per hour. Nose wheel liftoff. 140 knots, main gear liftoff. Climb rate 1,000 feet per minute. Flight level 350, 35,000 feet. Cruise speed 0.69 Mach, 466 miles per hour. 4 hours, 20 minutes airborne. Landing nominal. Next up, flight test program. 200 flights, 700 hours. Maximum weight with ballast, 51 tons. Single engine flight. Crosswind landing at 30 knots. -22 in Sweden, plus 113 in Spain. Everything works. November 13, 2019. Type certificate. The Beluga cleared for flight. January 9, 2020. First commercial flight. Toulouse, Bremen, Toulouse. Cargo, 2 A350 wings, each 105 feet long, 21,000 pounds. Before, 2 flights with the old Beluga. Now, 1. Loading 70 minutes. Wings roll in on a trolley along floor tracks. 24 tie-down points with straps. Flight 1 hour 40 minutes. In Bremen, they unload the wings, load A320 fuselage sections, fly to Toulouse. 3 to 4 flights a day, 6 days a week. 1,000 flights a year across 6 aircraft. Without the Beluga, Airbus wouldn't build a single plane. Wings made in Great Britain, tails in Spain. Fuselages in Germany. Final assembly in Toulouse and Hamburg. The Beluga, a flying assembly line. Europe's industrial artery. 1 billion euros program cost, 167 million per aircraft, 30 years of service, 60,000 flight hours. If this was interesting, hit like. Did you know about the Beluga? Write in the comments. Subscribe. Here we show you factories you never knew existed.
Every year, Japan produces millions of tons of steel, but only a fraction of it becomes the heart of what is considered a modern engineering miracle, the rails for the Shinkansen bullet trains. Imagine a furnace larger than a 5-story building, heated to over 1,500 degrees Celsius, where iron and carbon boil. This ocean of fire is transformed into rails the length of a football pitch, so perfectly straight that the smooth glide of a train at 320 kilometers per hour depends on them. But the real secret lies in how Japanese engineers fuse these rails into a continuous ribbon, up to 1.5 kilometers long. Do you want to know how they created the illusion of an endless rail without a single click-clack? Watch until the end. We are inside a vast Japanese steelworks. The atmosphere is heavy, thick with a mixture of intense heat, the smell of steel, and the deep hum of powerful machinery. Before us stands the main character of this scene, a steel-making furnace the size of a 5-story building. It resembles the mouth of a volcano, glowing a blinding white. Inside, a boiling mixture of iron and carbon churns at over 1,500 degrees Celsius. With a roar, the molten metal is poured into special molds, like a brilliant orange river of lava flowing down a mountainside. Against the scale of these immense machines, the workers look tiny. After the steel is cast, it begins to cool, transforming from a liquid into a solid, yet still intensely hot block of metal. The rolling mill is a colossal machine, something like a giant meat grinder, but instead of blades, it has heavy steel rollers that crush and stretch the metal. The deep rumble intensifies as the machine grips a red-hot billet. With a sound like a low groan, the hot steel begins to elongate, like dough for pasta, but dense and heavy. Gradually, this billet becomes longer and straighter until it finally emerges as a single continuous rail, almost 100 meters long, the length of a football pitch. The surface of such a rail must be absolutely flawless, without the slightest ripple. Because if it is even minutely uneven, a Shinkansen train will not glide smoothly over it. After rolling, the rail is still incredibly hot. Steam rises from it, and you can hear a crackling sound like water hitting a scorching hot plate. But this is its almost finished form: long, heavy, smooth, ready for inspection, grinding, and its future life. To reduce the number of joints, Japan uses a method of continuous welding, where several rails are fused into one extremely long ribbon. The welding of rails for high-speed trains like the Shinkansen is a high-precision process, with the goal of turning individual sections into a seamless track up to 1.5 kilometers long. It is this type of joint that eliminates the traditional click-clack sound as the train passes over it. The welding process occurs in several stages. The most common method is thermite welding, a reliable and visually spectacular technique. 2 rails are positioned end to end, with a gap of just a few millimeters between them. The surfaces of the future joint are meticulously cleaned of any rust or contaminants. A special mold made of a heat-resistant material is then clamped around the joint. A small crucible above the joint is filled with the thermite mixture, a powder of aluminum and iron oxide. When it is ignited, a chemical reaction occurs, generating a temperature of over 2,500 degrees. The result is molten iron, which flows down and fills the gap between the rails, fusing them at a molecular level. The reaction lasts several minutes, accompanied by a hissing, crackling sound as a brilliant flame erupts above the joint. It looks like a miniature volcanic eruption. After the metal solidifies, which takes about 10 minutes, the mold is removed and the excess metal is sheared off. The joint is then ground down to a perfectly smooth surface so that the train wheel feels no transition. The finished weld is inspected with laser measurements and ultrasonic sensors which search for any potential micro cracks. In a world where every second counts, Shinkansen engineers discovered the secret to permanence, the slab track. Instead of traditional stone ballast, they created monolithic giants from concrete. These Titan slabs can reach a thickness of 66 centimeters, the height of 2 footballs stacked on top of each other. Japanese masters also invented an ingenious solution: encapsulation units. Imagine a metal cradle that embraces the rail like a mother holds a child. These cradles not only secure the steel tracks, but also isolate them from vibration and electricity. But the most brilliant part of the system is what you cannot see. Between the concrete slabs and the foundation, the Japanese placed resilient layers that act as giant shock absorbers. Transporting the sleepers to the installation site is done in several ways. For short distances, special crane-equipped lorries are used. For longer routes, railway flatbeds. Safety during transport is critical. A single concrete sleeper must be lifted by 4 workers, highlighting their significant weight, roughly 75 kilograms per worker. For mechanized lifting, special grabs and cranes are used. On the construction site, the installation process begins with the preparation of the base. For the slab track, which is predominantly used on the Shinkansen, the sleepers are installed onto precast concrete slabs. Each sleeper is positioned with an accuracy of 6 millimeters, as even the slightest deviation can cause problems at speeds of 320 kilometers per hour. The installation is carried out by specialized crews using precision equipment. First, support points are set every 60 centimeters, the standard interval for high-speed lines. Each sleeper is then fixed to the base with special anchor bolts, 2.5 centimeters in diameter, which are driven 15 centimeters deep into the concrete slab. The process is further complicated by the need to integrate with the power supply and signaling systems. The final stage involves installing vibration insulating pads between the sleepers and the base. These rubber steel elements significantly reduce the transmission of vibrations from the trains to the surrounding structures. After the installation is complete, the entire section is tested by a special inspection train. Despite more than 120,000 trains running on the line annually, the average delay is just 36 seconds. Over half a century, the top speed has increased from 210 to 320 kilometers per hour, and the line now carries 1 million passengers a day. A new line is expected to operate at 500 kilometers per hour, with a projected journey time between Tokyo and Osaka of just 67 minutes.
Every year, over 27 billion square feet of drywall are produced in the United States. That's enough to build a road from the Earth to the Moon and almost halfway back, or to cover the entire state of Delaware twice. But how does an ordinary stone, formed millions of years ago at the bottom of ancient seas, turn into the smooth sheets that become the walls of our homes today? In this video, we'll take a look behind the factory doors, where tons of stone pass through furnaces, mills, and conveyors to become the symbol of modern American construction. Watch until the end, and you'll see secrets that are rarely shown publicly. The numbers behind drywall production in the United States are not just big, they are astronomical. And they tell a story of how the country builds, renovates, and breathes. In a recent year, factories in the US produced approximately 27 billion square feet of gypsum board panels. This number is so colossal that it's hard to comprehend. Try to imagine, if you were to lay out all this amount of drywall, you could create a continuous 3-foot wide path that would stretch from the Earth to the Moon and almost halfway back. Or, with this number of sheets, you could completely cover the entire state of Delaware twice and still have some left over. This endless stream of building material is not only a physical product, but also a powerful economic indicator. The market for these panels in the US is valued in the tens of billions of dollars, reflecting not just the cost of the material itself, but also thousands of jobs in mines and factories, in logistics and in construction. It all begins not in the workshop, but much earlier, in a quarry where gypsum is mined. This is a natural mineral, a stone that was formed millions of years ago from ancient seas. It can be white, grayish, sometimes with pink veins. Huge excavators dig into the gypsum deposits and load dump trucks with boulders of this stone. These trucks bring tons of gypsum to the factory and dump it onto the raw material yard, creating entire mountains waiting for their transformation. The first stage inside the factory is coarse crushing. The gypsum boulders fall into the giant steel jaws of the primary crusher. With a deafening roar and grinding, the machine breaks the large stones into smaller pieces, the size of a fist. This is just the beginning. Then, this crushed gypsum is fed by a conveyor belt to secondary mills. Here, dozens of steel hammers, rotating at an insane speed, break these pieces into even smaller fractions, turning them into something resembling coarse gravel. But even this is not enough. The final stage of grinding turns the gypsum into a fine, powder-like dust. It becomes so fine that it resembles flour or dust. This powder is the main raw material, but it still hides a secret that needs to be revealed. The next step is one of the most important and interesting. It's a process called calcination, and essentially, it's the controlled drying of gypsum. The fact is that in the crystal structure of natural gypsum, water molecules are locked in. For drywall to harden, this water must be temporarily driven out. To do this, the white powder is fed into a huge, slowly rotating kiln. It looks like a giant drum tilted at a slight angle. Inside this kiln, a very precise temperature of about 300 degrees Fahrenheit is maintained. The gypsum powder, slowly tumbling inside the drum, heats up and the water bound to it turns into steam and evaporates. Chemically speaking, gypsum turns into calcium sulfate hemihydrate. But to put it simply, it becomes thirsty. Now this powder, which is already called building plaster or stucco, has a unique property. If you add water to it again, it will greedily absorb it and turn back into a hard gypsum stone. It is this property that is the basis of the entire production. The resulting hot powder is cooled and stored in giant silos, resembling towers, from where it will be fed to the main production line.
And now the most spectacular part begins, the creation of the sheet itself. In the workshop is a huge conveyor, hundreds of feet long. At its beginning stand 2 giant rolls of special dense paper, or paperboard. One roll for the face side, it's perfectly smooth white. The other for the back side. It can be a bit darker, grayish. The ribbon from the bottom roll, the face side, is unwound and lays on the conveyor, forming an endless track. In parallel with this, in a giant mixer, resembling an industrial food processor, the core is prepared. Our thirsty gypsum powder, water, and a whole cocktail of various additives are continuously fed into it.
Each additive plays its role. Foaming agents make the gypsum mass lighter and more porous, like whipped cream, to reduce the weight of the sheet. Plasticizers make the mixture more fluid, so it spreads evenly. Accelerators or retarders allow engineers to perfectly control the time it takes for the gypsum to set. Starch helps the gypsum core to stick better to the paper liner, and fiberglass adds strength. This mixture, called slurry, resembles a thick gray porridge. It is poured in a continuous stream directly onto the paper ribbon moving on the conveyor. Special devices evenly distribute this mass across the entire width of the paper. The edges of the bottom sheet of paper are neatly folded up, forming the sides of the future sheet. And at this moment, the second ribbon of paper, from the back roll, is laid on top like a lid. The result is an endless, perfectly even sandwich. Paper, gypsum mass, paper. This sandwich immediately passes between 2 rollers or under a forming plate, which compress it to a precisely specified thickness, for example, ½ an inch. The newly formed, still soft and damp sheet of drywall continues its journey on a very long conveyor called the setting line. Its length can reach several hundred feet. While the sheet slowly moves, a real miracle is happening inside it. The gypsum powder reacts with water, the same rehydration reaction occurs. The gypsum turns back into a hard stone, releasing heat in the process. If you touch the sheet at this stage, it will be warm. In a few minutes, the loose mass becomes hard enough to hold its shape. At the end of this long line stands a flying knife. This is a huge blade that moves in sync with the belt, and at the right moment makes a quick, precise cut, slicing the endless sandwich into sheets of standard length, for example, 8 or 12 feet. This happens so quickly that the conveyor doesn't stop for a second. The cut sheets are now hard, but still very damp. They contain excess water that did not participate in the chemical reaction. It needs to be removed. Therefore, a special device flips the sheets and feeds them into the most massive structure in the factory, a multi-deck drying kiln. This is a giant labyrinth consisting of several levels, each of which is a conveyor. The drywall sheets slowly move along these levels back and forth, traveling a path of several hundred feet inside this huge furnace. Hot air circulating inside gently evaporates the excess moisture from them. The temperature here is very carefully controlled. Only the free water needs to be removed without damaging the crystal structure of the gypsum itself. This process can take about an hour. At the exit of the dryer appears a product we are familiar with, a perfectly dry, light, and strong sheet of drywall. But this is not the end. The final stage is finishing. 2 finished sheets are stacked face to face, their edges are perfectly trimmed to be straight and clean. A paper tape with information about the manufacturer and product type is glued to the end. After this, robotic manipulators with superhuman precision and grace lift the finished sheets and stack them in perfectly even stacks on pallets.
Each stack is wrapped in protective film, labeled, and sent to the warehouse. From there, it will go to construction sites to become part of someone's home, transforming from a simple gray stone mined from the earth into a smooth and cozy wall. Drywall production is like a barometer of the construction industry's health. When the economy is booming, people actively build new houses and renovate old ones, and the demand for drywall soars. The factories that produce this product operate at full capacity, and the stream of trucks delivering the finished sheets across the country becomes endless. The heart of this production beats in unison with the rhythm of the real estate market. Geographically, this industry also has its centers. Although drywall factories are located throughout the country to be closer to large construction markets, the extraction of the main raw material, gypsum, is concentrated in certain states. The leaders here are states like Texas, Oklahoma, Kansas, Nevada, and Iowa.
Every knife in your kitchen, every spoon in your drawer, every sink, every pot, every bolt in a skyscraper. All of it exists because of one gray-green rock lying hundreds of feet underground, nickel ore. Without it, stainless steel wouldn't exist at all. Nickel is what transforms ordinary iron into metal that won't rust for decades. Add 8% nickel to steel, and it withstands seawater, acids, extreme temperatures. Every year, humanity mines 3 million tons of this metal. Value: $50 billion. But the journey from rock in the ground to shiny stainless steel sheet? It's technological hell. Explosions in quarries. Smelting at 2,700 degrees Fahrenheit. Chemical baths with sulfuric acid. Electrolysis under thousands of volts. How do you get metal that's 99.9% pure from gray rock that looks like an ordinary stone? Watch till the end. You'll see how the foundation of modern civilization is born. Planet Earth holds 300 million tons of nickel, but it's buried deep. The biggest deposits are in Indonesia, the Philippines, Russia, Canada, Australia, China, and the US. Not miners, processors and consumers. America uses it for aerospace and nuclear reactors, but it all starts in the pits. Open pit mines in Indonesia are wounds in the jungle the size of a city. A pit 1,000 feet deep, 3 miles wide. Excavators with 700 cubic foot buckets gnaw at the earth around the clock. The ore here is called laterite. It's a reddish-brown rock that looks like clay. Just 1 to 2% nickel. The rest? Iron, silicon, magnesium. But even these scraps of nickel make mining profitable. One Belazi haul truck carries 300 tons of ore out of the pit. 500 trips like that a day. 150,000 tons of rock daily. That's an entire mountain of material you need to squeeze metal from. The ore heads to primary processing. Here it's crushed and sorted. Massive jaw crushers grind car-sized chunks down to 4-inch pieces. The noise is so intense workers wear noise-canceling headphones. Then cone crushers pulverize the rock to gravel size. Mills with hardened steel balls turn the gravel into powder. Inside a 65-foot rotating drum, 4-inch steel balls hammer the ore. After 6 hours of spinning, the rock becomes dust. This dust gets mixed with water. You get a liquid slurry. It runs through magnetic separators. Nickel ore is weakly magnetic, but the iron in it magnetizes stronger. Some of the waste rock gets filtered out. Nickel concentration in the slurry jumps from 2 to 4%. Still not much, but better. The slurry thickens in huge settling tanks. Water drains away, leaving wet paste. It dries in drum dryers at 400 degrees. What comes out is dry concentrate, ready for smelting. From 1,000 tons of ore, you get 300 tons of concentrate. (1751). Swedish chemist Axel Kronstedt is studying a strange mineral from the Los Mine. The rock's reddish, looks like copper ore. Cronstedt tries to smelt copper from it, but gets a white metal unlike anything known. Hard, heavy, doesn't rust. He names it nickel, after Nickel the mountain spirit from German folklore who tricked miners by slipping them worthless rocks instead of copper. But nickel turned out to be anything but worthless. In the 19th century, they start adding it to steel. The British discover that 5% nickel makes battleship armor twice as strong. The Germans use nickel steel for artillery. World War I turns nickel into a strategic resource. Whoever controls nickel controls military production. In the 30s, metallurgist Harry Brearley invents stainless steel. The formula is simple: 18% chromium, 8% nickel, the rest iron. This steel never rusts. Revolution in kitchens, hospitals, factories. Demand for nickel explodes. The hunt for new deposits begins worldwide. The 1960s. Discovery of massive deposits in New Caledonia and Indonesia. Laterite ores containing billions of tons of nickel. But there's a problem. These ores can't be smelted the conventional way. Too many impurities, compositions too complex. New technology is needed. The Canadians invent the Sherritt-Gordon process. The Chinese develop a pyrometallurgical method called RKEF. Rotary kiln, electric furnace, ferrochrome. Every country creates its own nickel extraction methods. By the 2000s, China becomes the dominant processor. They build dozens of plants in Indonesia and the Philippines. Strategy's simple: control the processing, control the market. The US took a different path. Americans focus on high-purity nickel for EV batteries and reactors. Smaller volumes, but the highest quality. A plant in Ontario processes Canadian ore using flash smelting technology. Temperatures above 2,900 degrees Fahrenheit. Metal purity, 99.999%. This nickel goes into Teslas and nuclear submarines. Two approaches, two philosophies. China wins through volume, America through quality. The smelting shop is the hottest place in the plant. In the center of the hall stands an electric furnace as tall as a 5-story building. Power output, 100 megawatts. That's like 10,000 homes running simultaneously. Nickel ore concentrate is loaded from the top along with coke and fluxes. Coke is pure carbon, the heat source. Fluxes, limestone and quartz, they bind the waste rock. Through graphite electrodes, they run a current of 100,000 amps. Voltage, 200 volts. Temperature inside the furnace climbs to 1,500 degrees in an hour. The ore melts. Heavy metals, nickel, iron, cobalt, settle to the bottom. Light slag floats to the top. This separation is critical. After 8 hours of smelting, the furnace is ready for tapping. A tap hole opens at the bottom. Molten metal flows through a channel into a ladle. It glows white-hot. Temperature 1,400 degrees. Workers in silver suits control the process remotely. One ladle holds 50 tons of metal. This is matte, an alloy of nickel, iron, and sulfur. Nickel content, 20%. That's not enough. Further refining is needed. They pour the matte into a converter, a massive horizontal barrel 50 feet long. Oxygen gets added too. The blow begins. Oxygen at 150 psi blasts into the molten mix through tuyères. The reaction's exothermic, releases so much heat the temperature shoots up to 3,000 degrees without any external heating. Sulfur and iron oxidize, burn off. New slag forms, gets drained away. After 6 hours of blowing, what's left in the converter is fine matte, an alloy with 50% nickel. But even that's not pure enough for high-tech applications. Next stage, electrolysis. The fine matte gets ground into powder and dissolved in sulfuric acid at 180 degrees. You get a green solution of nickel sulfate. This solution goes into electrolytic cells. Each cell, a tank 10 feet by 7, 3 feet deep. Inside hang titanium anodes and nickel cathodes. Between them, the solution. They run a current at 2 volts, current strength, 20,000 amps per cell. Nickel from the solution plates onto the cathodes. Over a week, each cathode builds up a layer of pure nickel about an inch thick. They pull the cathodes out, scrape off the nickel. Purity, 99.95%. And just like that, after passing through explosions, crushing, smelting at temperatures above 2,700 degrees Fahrenheit, oxidation, dissolving in acids and electrolysis, a dull gray rock transforms into a shining metal that changed the world. Without nickel, there'd be no skyscrapers, their steel frames would rust away in years. No submarines. Seawater would eat through their hulls. No nuclear reactors. Their pipes couldn't handle the corrosive environment. Every component that needs to last decades in conditions where ordinary steel surrenders contains nickel. 3 million tons per year. 200 consumer nations. Thousands of factories, millions of jobs. Indonesia digs the ore, China smelts the metal, America turns it into superalloys for space. Europe stamps out stainless steel for hospitals. A closed loop that keeps civilization afloat. Nickel isn't just a metal. It's a guarantee of durability for everything we build. Proof that humans learn to take nature's dull rocks and turn them into eternity. Every time you wash your hands in a sink that gleams like new after 20 years of service, remember, that's nickel at work. The metal that conquered time and corrosion. Every year, shipyards launch massive icebreakers and cruise liners. Vessels weighing tens of thousands of tons, capable of operating for months in the planet's harshest seas. But few realize their engines are no longer inside the hull. Engineers took a radical step. They moved a power plant generating over 22 megawatts. That's more than 30,000 horsepower. And dropped it directly beneath the ship's bottom in a sealed steel pod weighing 320 tons. That's the weight of 2 fully loaded Boeing 747s. Inside that pod, a rotor misalignment by a fraction of a millimeter can shred bearings and destroy the entire drive system in just days. Watch this video to the end, and you'll discover how this underwater power plant is built, what installation mistake gets permanently hidden beneath the waves, and why this invisible enemy can obliterate a ship weighing thousands of tons in a matter of days. At first glance, it looks like a massive metal tail bolted to the ship's bottom. But inside, a full-blown electric motor. They don't mount it in the engine room like they did for decades. Here, it's the opposite. They drop the motor straight into the water, seal it tight in a steel shell, and make it work right there in the ocean. For years, no repairs, under constant seawater pressure. That's exactly why this thing's treated almost like a submarine. The idea of moving the engine outside the hull showed up relatively recently, even though engineers had been thinking about it for decades. Back in the mid-20th century, shipbuilders were trying to ditch the long shafts, gearboxes, and complex mechanical drives that ate up massive space inside the ship and bled power at every connection. The real breakthrough came in the late 1980s when Finnish engineers working on icebreakers for northern seas proposed a radical solution. Move the electric motor directly into the rotating pod under the hull. If engineering stories like this grab you the way they grab me, subscribe to the channel right now so you don't miss the next episode. Hit that bell and every new video will show up for you immediately. The work was carried out by specialists from a shipbuilding company looking for a way to make vessels more maneuverable in ice. The first experiments looked risky. The engine had to be completely isolated from seawater and made to run for years without any access to it. In 1990, the first working units appeared, and just a few years later, the technology began being installed on actual icebreakers. It turned out that this design didn't just work, it worked better than any traditional setup. When it became clear that the azimuth thruster allowed a ship to move in practically any direction without turning the hull, the system was quickly adopted by cruise liner builders. This thruster can rotate 360 degrees, making conventional stern rudders and separate bow thrusters simply unnecessary. Maneuverability increases so much that a huge liner can pull up to a dock nearly sideways without tugboat assistance. Since then, this design has gradually changed the very concept of where a ship's heart should be. Not inside it, but right beneath it. I walk past hull sections that were still separate steel plates just hours ago, each one several inches thick and weighing several tons. These are already curved metal sheets, pre-rolled, so the future capsule has a smooth, streamlined shape with no abrupt transitions. No right angles here, no unnecessary joints. The form is dictated by water, not manufacturing convenience. Overhead cranes slowly lift these elements and bring them together like assembling an underwater projectile. Between the parts, they leave a narrow gap where the weld seam will go. During welding, sparks fly everywhere, and the metal glows orange. Workers move slowly, passing over every inch of the joint multiple times. No rushing, no wasted motion. First comes the inner seam, then the outer, and after that the surface gets carefully ground down so there's not a single protrusion left to create extra drag in the water. When the hull finally closes up, it already looks like a smooth steel torpedo. Tight, solid, without a single flaw on the outside. After that, the inspection begins. Welds are scanned with ultrasound and X-rays searching for even the tiniest pores inside the metal. Any suspicious section gets cut out and re-welded, no compromises. Then they seal the capsule and pressurize it far beyond what it'll face underwater in actual conditions. If there's a weak spot anywhere, it'll show up immediately. Only after passing all tests is the hull declared ready to withstand years of service in cold seawater and constant ice impacts. Once the steel capsule is fully welded and tested, the moment arrives in the shop that the entire hull was essentially built for. They need to install the electric motor, the main power source for the future vessel. And this is where you realize just how massive everything is in marine engineering. Before installation, the motor sits on a special platform looking more like part of a power plant than ship machinery. Its diameter, nearly 10 feet, and its weight is such that regular lifting equipment isn't even considered an option. Only heavy overhead cranes work here, with every movement pre-calculated and coordinated. The rotor, the spinning part of the engine, gets lifted separately. It's a massive metal ring with copper conductors that weighs more than a fully loaded semi-truck. The crane starts moving so slowly it's almost invisible to the eye. The operator works on commands from several engineers stationed around the housing, constantly monitoring the component's position. There's no room for sudden movement and no room for error. Even a shift of a fraction of a millimeter can mean misalignment that'll show up during operation as severe vibrations. And vibrations at this power level aren't just an inconvenience, they're a disaster. When the rotor hangs over the open capsule, the most nerve-wracking phase begins. They literally lower it millimeter by millimeter, constantly measuring clearances with laser instruments. Inside the housing, bearings and support elements are already installed, and everything has to align to within thousandths of a millimeter. If the engine shaft is even slightly off from the geometric center of the capsule, a spinning imbalance will develop that the entire ship will feel. At operating speed, this imbalance turns into a constant hammering that can destroy bearings or damage the housing from the inside in a matter of weeks. After the rotor is seated, engineers won't allow the crane to be removed for a long time. A series of checks begins. They measure alignment, manually rotate the shaft several times, listen carefully to the sound of metal. The slightest unusual noise and the part gets lifted back up. Sometimes they raise the motor again and adjust its position, spending hours for just a few millimeters of correction. Everyone here understands. Once the capsule is sealed, there will never be access inside again, so perfect precision matters more than any installation speed. When the motor finally settles into place, the entire structure suddenly looks complete. An empty steel shell transforms into a real propulsion system. This is the moment you can consider the birth of a system that will later spin the propeller, turn a multi-thousand-ton vessel, and operate for years underwater, where no human will ever see it again. Modern units can pump out up to 22 megawatts of power. That's the equivalent of more than 30,000 horsepower. To put that in perspective, a single engine like this could supply electricity to a small town of 25,000 people. And this is a mechanism that operates completely underwater, hidden from view, impossible to service in the open ocean. It's designed with reliability margins years into the future because scheduled maintenance is only possible in dry dock. A fully assembled unit with engine and propeller can weigh over 320 tons. The propeller that attaches to the pod often exceeds 23 feet in diameter. Each blade on a propeller like that weighs as much as an adult African elephant. Yet this entire system has to run absolutely smooth. Any vibration at these power levels instantly transfers to the hull and gets felt by passengers on every deck. Once the engine is safely tucked inside its steel housing, the final stage begins, installing the propeller. If the pod itself is the muscle, then the propeller is the hands that push against the water and drive the ship forward. Each blade is manufactured from a special alloy of bronze, aluminum, and nickel. This metal needs to be strong enough not to bend under the pressure of thousands of tons of water, yet smooth enough not to create unnecessary turbulence. The blades arrive at the pod on special pallets, each wrapped in protective film like a piece of jewelry. Installation is carried out using hydraulic rams. The propeller is mounted onto the engine shaft protruding from the pod, and here precision is once again measured in thousandths of a millimeter. Any misalignment will cause the propeller to vibrate at operating speed, and that vibration will destroy the engine bearings within days. When the propeller finally locks into place, it's secured with a massive nut, tightened with several thousand Newton meters of torque. After that, a streamlined cap is installed on the hub to ensure the water flow past the propeller is perfectly smooth. The entire assembly is coated with special paint that marine organisms and barnacles won't stick to. Because even a few centimeters of buildup on the blades can reduce engine efficiency by 5 to 7%, translating to losses of hundreds of thousands of euros per year. Every second, the world produces 28 million tons of stainless steel. And behind the shine of every spoon, every faucet, every surgical instrument stands one metal: chromium. But here's what's mind-blowing. Chromium melts at 3,375 degrees Fahrenheit, and in the electric arc furnaces that produce it, temperatures hit 5,000 degrees, hotter than the surface of the sun. A single furnace consumes 4,000 kilowatt hours of electricity per ton of alloy. That's as much as the average apartment uses in 4 months. 80% of all chromium in the world goes into making stainless steel. But where does this metal come from? Why are 99% of the world's chromite reserves concentrated in just a handful of countries? And what happens in that hellish zone beneath the electrodes, where ore transforms into molten ferrochrome? Stick around. You'll discover how black rock gives birth to the metal that makes steel immortal. Picture a massive electric arc furnace as tall as a 3-story building. 3 carbon electrodes up to 6 feet across plunge into a churning mass of glowing ore, coke, and fluxes. Between the electrode tips and the furnace floor, electric arcs crack and snap. Temperatures in this zone hit 5,000 degrees Fahrenheit. That's hotter than the surface of the sun. The air above the furnace shimmers with heat. Clouds of smoke and gas blast out from beneath the half-closed roof. Inside, real alchemy unfolds. Chromium ore mixed with coke melts down, oxygen escapes as carbon monoxide, and molten ferrochrome, an alloy of chromium and iron, flows to the bottom. This is a submerged arc furnace, and this is where most of the world's ferrochrome is born. The process runs non-stop. Fresh batches of ore and coke pour in from the top, molten metal and slag tap out from the bottom. A single furnace like this can pack 25 to 45 megavolt amperes of power. This is a monstrous amount of energy. An entire power plant runs just to melt the ore. When enough molten ferrochrome accumulates in the furnace, workers punch open the tap hole, a special opening in the furnace's side. And then the mesmerizing spectacle begins. A stream of white-hot metal and slag bursts out, flowing down a channel into an enormous ladle. The stream's temperature around 3,000 degrees Fahrenheit. The metal glows bright orange, almost white. The heat radiating from it is so intense that workers stand dozens of yards away, protected by special screens and fireproof clothing. Slag floats to the top and is drained off separately. The ferrochrome cools in massive molds, transforming into solid ingots weighing hundreds of pounds. These ingots are later crushed into pieces of the right size for sale to steel mills. But the process of obtaining ferrochrome, that's only the middle of the journey. It all begins with ore, mined deep in the earth. Chromite, the only industrial ore of chromium. It's a dark brown, almost black mineral with a metallic luster. The chemical formula? Iron and chromium oxide. Pure chromite contains 68% chromium oxide and 32% iron oxide. But in nature, perfect ores like that barely exist. Real deposits contain anywhere from 40 to 50% chromium oxide. Chromite forms in igneous rocks, in massive molten masses rising up from the Earth's mantle. The largest deposits are found in South Africa, Kazakhstan, India, and Turkey. These 4 countries account for roughly 80% of global production. South Africa is the absolute leader. Its deposits in the Bushveld complex contain 200 million tons of chromite. We're talking ore seams stretching for hundreds of miles and plunging thousands of feet deep. Kazakhstan holds reserves of 230 million tons. India? 54 million tons. Now the story. French chemist Louis-Nicolas Vauquelin discovered chromium in 1797. He isolated it from croquat, a bright red lead chromate mineral. The mineral's vivid color inspired Vauquelin to name the metal after the Greek word chromos, color. Because chromium compounds produce stunning colors: greens, yellows, oranges, reds. A year later, in 1798, Vauquelin isolated pure chromium by reducing the oxide with carbon. Iron with added chromium was first produced in the mid-1800s, and the first use of chromium as an alloying element in steel production happened in France in the 1860s. The revolution came in 1893 when Henri Moisson smelted chromium ore with carbon in an electric furnace and produced ferrochrome. This became the foundation of the modern industrial method, which has evolved but at its core remained the same. Chromite gets mined both through open-pit operations and underground mines. Open-pit mining gets used when the ore sits close to the surface. Giant excavators strip away the soil and overburden, exposing the chromite layers. Then they blast the ore, load it into haul trucks with capacities up to 300 tons, and transport it to the processing plant. Underground mining gets deployed for deep deposits. Tunnels get driven hundreds of feet down, sometimes miles. They blast the ore, load it into mine cars, and haul it to the surface. The extracted ore? It's not pure chromite yet. It comes mixed with waste rock and other minerals. That's why the ore needs processing. First, they crush it in massive jaw crushers. Chunks the size of a car get reduced to fist-sized pieces. Then they grind it in ball mills down to the size of sand or even dust. After that comes separation, isolating the chromite from the waste rock. The main method for enriching chromite is gravity separation. Chromite is heavier than waste rock. Its density is 4.5 to 4.8 grams per cubic centimeter, while the rock is 2 to 3 grams. The crushed ore is mixed with water, creating a slurry. The slurry passes through jig machines, concentrating tables, spiral classifiers, centrifugal separators. Under the force of gravity, the heavier chromite grains settle faster, while the lighter waste rock is carried away by the water flow. Magnetic separation is also used. Chromite is weakly magnetic, but modern high-intensity magnetic separators can attract it and separate it from non-magnetic impurities. After enrichment, they obtain chromite concentrate containing 46% or more chromium oxide. This is ready-made raw material for metallurgy. The concentrate is dewatered, dried, and sent to ferroalloy plants. Lump ore is needed for ferrochrome production. Fine powder doesn't melt well in the furnace. So the fine particles get agglomerated, sintered into large chunks. They mix the concentrate with fluxes and coke breeze, moisten it, and form pellets. Then they heat it to about 2,200 degrees Fahrenheit. The pellets sinter into solid lumps a couple inches across. Now the ore is ready for smelting. At the ferroalloy plant, chromite concentrate gets mixed with coke and fluxes in specific proportions. Coke is the carbon source that'll reduce the oxides down to metal. Fluxes, quartzite, dolomite, limestone, are needed to form slag with the right composition and melting point. The charge, the mix of ore, coke, and fluxes, gets loaded into the electric arc furnace from the top through special hoppers. Loading happens continuously or in batches depending on the furnace type. The electrodes, massive carbon cylinders, are submerged in the charge layer. When they switch on the current, an electric arc forms between the electrodes and the material beneath them. Temperature in the arc zone? 5,000 degrees Fahrenheit and higher. That's enough to melt any ore. Inside the furnace, complex chemical reactions take place. Carbon from the coke combines with oxygen from chromium and iron oxides, forming carbon monoxide that rises upward. Chromium and iron are reduced to their metallic state and fused together, forming ferrochrome. Some of the carbon dissolves into the metal, producing high-carbon ferrochrome with a carbon content of 4 to 8%. Typical South African ferrochrome contains 52 to 54% chromium, 6 to 7% carbon, and 2 to 4% silicon. Ores from Zimbabwe with a higher chromium to iron ratio yield a product with 63 to 67% chromium. The molten ferrochrome and slag accumulate in the lower part of the furnace, the hearth. When enough metal has built up, they open the tap hole. Metal and slag flow into a ladle. The slag floats to the top and is poured off or skimmed away. The metal is poured into molds or cooled in special forms. Once solidified, the massive ingots are broken down by hydraulic presses or hammers into pieces of the required size. Ferrochrome production is incredibly energy intensive. A single ton of high-carbon ferrochrome burns through 2,000 to 4,000 kilowatt-hours of electricity. That's why ferrochrome plants get built in countries with cheap power, often right next to hydroelectric dams. Chromium recovery from ore hits about 90% under good conditions. The remaining 10% it goes into slag. Slag isn't just waste. Metal particles get extracted from it using mineral processing methods, and what's left goes into construction. Ferrochrome isn't the end product. It gets shipped to steel mills where it's added to molten steel for alloying. Chromium gives steel corrosion resistance, hardness, heat resistance. Stainless steel contains 10 to 20% chromium. Average, 18%. It's chromium that forms a thin, invisible oxide film on the steel's surface, protecting the metal from rust. And so, having traveled from black rock in the Earth's depths, through quarry explosions, crushing and processing, through the inferno of an electric arc furnace at 5,000 degrees Fahrenheit, ferrochrome is born. An alloy that gives steel eternal life and shine, resistant to time and corrosion.
Every year, thousands of quarries crush millions of tons of rock. The biggest dragline in history, Big Muskie, weighed 13,500 tons. That's like 10,000 cars. But the real star isn't the machine itself, it's the teeth. Parts weighing up to 150 pounds that bite into granite every single day. How does ordinary steel transform into nearly impenetrable armor? Today you'll see the complete cycle, from molten metal to a tooth that survives 50,000 impacts. If you want to see how they make the fangs of giants, subscribe to the channel. Here we show you the operations that tear into the earth. Big Muskie weighed 29,779,800 pounds. The bucket could fit 2 buses side by side. Bucket capacity, 4,300 cubic feet. 60 teeth on the bucket. Each tooth weighs 50 to 150 pounds. A tooth isn't just a chunk of iron, it's an engineering marvel that bites into granite day after day without wearing down. Teeth are made using 2 methods, casting and forging. Right now, you're seeing casting. Material, alloy steel with nickel and molybdenum. Molybdenum improves hardening, nickel provides toughness and corrosion resistance. Carbon content from 0.33 to 0.5%. That's high carbon steel. It's hard after quenching. Steel melts in an electric arc furnace. Temperature, 2,692 degrees Fahrenheit. 3 graphite electrodes. Arc between electrodes and metal. Power, 10 megawatts. Furnace holds 20 tons. Melting time, 2 hours. Steel gets purified. Sulfur removed with lime. Phosphorus by oxidation. Then the metal stirred in an argon-oxygen deoxidizer. Argon blown in from below. Pressure, 73 psi. Flow rate, 79 gallons per minute. Argon bubbles rise. Mix the melt. Carry gases to the surface. Hydrogen content drops from 10 to 2 parts per million. Oxygen from 80 to 20. Low gas content is critical. Gas bubbles become cracks. Finished steel pours into a ladle. Ladle lined with refractory. Melt temperature, 2,649 degrees Fahrenheit. Ladle holds 2,000 pounds, enough for 20 to 30 teeth. Investment casting. First, they make a wax model. Wax melts at 158 degrees Fahrenheit. Pour it into the die. Cool it down. You get a wax copy of the tooth. Accuracy down to a few thousandths of an inch. Models are assembled onto a sprue tree, 5 to 10 teeth per tree. The tree gets dipped in ceramic slurry. The slurry is fine zirconium powder in colloidal silica, particle size about 2 ten-thousandths of an inch. Dip the tree. Pull it out. Coat with coarse zirconium sand, grit size about 1/100th of an inch. Dry it. Repeat 7 to 10 times. Each layer about 1/16 inch thick. Final shell thickness roughly ½ an inch. The shell withstands 2,800 degrees Fahrenheit. That's the steel pouring temperature. They melt out the wax. Heat the mold to 1,500 degrees. Wax melts, flows out through openings, leaves behind a cavity that's the exact shape of the tooth. Pouring. The mold heats up to 1800 degrees Fahrenheit. A hot mold means less thermal shock during the pour. A crane brings the steel ladle into position. The steel's at 2650 degrees. It glows bright orange. They pour fast but carefully. Pour rate is 4 pounds per second. Air bubbles will kill the part. Metal fills the mold from bottom to top, pushes air out through the top. After pouring, they don't touch the mold. Cooling is slow, 8 to 12 hours to reach room temperature. Fast cooling means cracks. Slow means proper structure. Once it cools down, they break the shell. Sandblasting machine. Pressure at 120 psi. The sand is corundum, grit size 20 micrometers. The ceramic cracks and crumbles away. Underneath, a gray cast tooth. Surface is rough, ceramic remnants in the recesses. But the form is precise. Deviation from the blueprint is less than a millimeter. Heat treatment. First stage, normalizing. The teeth get loaded into the furnace. Temperature, 1920 to 2070 degrees Fahrenheit. Hold time, 10 hours. At this temperature, the steel recrystallizes. Large grains break down into smaller ones. The structure becomes uniform. It's like muscle recovery after a workout. The metal gets stronger and more flexible. Air cooling. Cooling rate, 90 degrees per hour. Second stage, hardening. Heat to 1870 degrees. Hold time, 2 hours. Then rapid cooling in oil. Oil temperature, 140 degrees. Cooling rate, 540 degrees per second. The structure transforms into martensite. That's a needle-like crystal lattice, extremely hard. Hardness after quenching, 59 to 63 on the Rockwell C scale. That's harder than a file. But hardened steel is brittle as glass. One strike, crack. That's why there's a third stage, tempering. Heat to 400 to 500 degrees Fahrenheit. Hold for 4 hours. This relieves internal stresses, adds flexibility. Hardness drops to 48 to 52 units. Perfect balance. Hard enough not to wear down, flexible enough not to break. Some manufacturers use induction hardening. The tooth gets placed in an inductor. Current frequency 400 kHz. Power 100 kilowatts. The surface heats up in 3 seconds to 2700 degrees Fahrenheit. Heating depth 0.04 to 0.08 inches. Immediately cooled with water. Pressure 145 pounds per square inch. Flow rate 26 gallons per minute. The surface hardens. The core stays soft. Surface hardness 58 to 63 units. Hardened layer depth 0.05 inches. Quality control. Every tooth gets checked with ultrasound. The probe generates waves at 5 MHz. Waves pass through the metal, bounce back off defects. A crack just 0.2 inches wide? Rejected. They check hardness with a Rockwell tester. A diamond cone presses down with 330 pounds of force. They measure the depth of the indent. Below 48 or above 52? Rejected. Too soft, it'll wear out fast. Too hard, it'll crack. The teeth get ground down. Grinding wheel made of aluminum oxide. 80 grit. Speed of 67 miles per hour. Takes off the rough spots from casting. Surface roughness drops from 0.001 inches to 0.00012 inches. Smooth surface holds up better against wear. Rough spots wear down faster. Marking. Every tooth gets a number. Laser engraving. Laser power 50 watts. Engraving depth 0.004 inches. The number shows the batch, date, and specs. Testing. One tooth from the batch gets sent to destruction. A hydraulic hammer strikes with a force of 1,000 pounds. Impact every 2 seconds. They count cycles until failure. A quality tooth withstands 50,000 strikes. Wear test. The tooth gets abraded. Quartz sand with 500 micrometer grain size. 5-bar pressure. 100 hours. That's equivalent to 1,000 hours of operation. The best teeth lose less than 0.5% of their weight. Production numbers. A big drag line, bucket holds 4,300 cubic feet, 60 teeth on the bucket. Each weighs 66 to 150 pounds. Teeth get replaced every 3 to 6 months. One drag line wears through 80 to 120 teeth per year. Hundreds of drag lines operate worldwide. 50 large machines in U.S. coal mines alone. Tens of thousands of teeth produced annually. One tooth costs $1,000 to $3,000. 60 teeth per bucket, $180,000 just for consumables. Replace twice a year. That's why every tooth must be perfect. The economics of mining depend on the reliability of these steel fangs. That's how dragline teeth are made. From molten steel to a part that chews through granite. If this was interesting, hit that like button. Write which quarries you've seen. Subscribe. We show how giants are made.
Imagine a river of white-hot metal as bright as the sun, born inside a giant furnace, melting everything in its path. But did you know that to create 1 ton of iron, you need almost 2 tons of rock and coal? It seems like alchemy. Hundreds of kilograms of oxygen and impurities vanish from dirty ore, leaving only pure metal behind. In the U.S., just a handful of these furnaces produce over 25 million tons a year, enough to build 250 aircraft carriers. And yet, there is a secret hidden within this story, one that will only be revealed to those who watch until the very end. It all begins deep in a quarry, where iron ore is mined. This isn't metal, but reddish-brown rock that looks like rusty earth. The iron is tightly bonded with oxygen, and the primary mission is to break that bond, liberating the metal within. Along with the ore, 2 other key ingredients for this infernal recipe arrive at the plant. The first is coke, a specially processed form of coal. It's baked in an oxygen-free oven to remove all impurities, resulting in pure, porous carbon that burns with incredible heat. In our process, coke is both the fuel and the main chemical agent. The third ingredient is limestone, a common rock. Its role? It's the cleaner. When heated, the limestone will act as a magnet for all the waste, collecting it into a separate mass. Now, let's go to the plant to meet the hero of our story, the blast furnace. It's a tower over 30 meters high, lined entirely with fireproof brick and wrapped in a network of pipes. This tower never sleeps. It runs continuously 24 hours a day, sometimes for years without stopping. It is a giant stomach that must be constantly fed. From the top, using a special skip hoist that looks like a small rail car, our ingredients are charged into the furnace. Not just thrown in, but layered like an industrial lasagna. A layer of coke, then a layer of iron ore and limestone, another layer of coke, and so on. To get 1 ton of liquid iron, you need to load almost 2 tons of raw material into the furnace. This figure includes the iron ore, the coke, and the limestone. It shows just how efficiently a blast furnace works as a giant filter. It takes nearly 2 tons of rock and coal, burns away everything unnecessary, and yields 1 ton of pure, concentrated metal. This is true industrial alchemy. Once the furnace is fed, the heat is turned up. At the bottom of the furnace are special nozzles called tuyères. Through them, air is blasted in under immense pressure, superheated to 1100 degrees Celsius. This hot blast ignites the coke, causing it to burn with incredible ferocity. The entire mass of materials loaded from the top begins its long journey down through zones of increasing temperature. First, in the upper section, hot gases rising from below dry and preheat the ore. A little further down, the chemistry begins. The burning coke reacts with oxygen to form carbon monoxide. And this carbon monoxide is our master thief. It greedily rises, meets the iron ore, and starts stripping away the oxygen atoms, leaving pure iron behind. About halfway down, the temperature becomes so intense that both the iron and the impurities begin to melt. This is where our cleaner, the limestone, comes into play. It decomposes and starts to bind with all the unwanted elements, forming a light molten mass called slag. At the very bottom of the furnace, in its heart, known as the hearth, a lake of two unmixable liquids forms. At the very bottom, being heavier, lies the pure molten iron, and floating on top, like oil on water, is the lighter molten slag. Every few hours, it's time for the tapping. A special machine, like a huge drill, pierces a hole in the fireproof lining of the furnace, first for the slag. A thick, bright orange river of molten rock erupts with a hiss. Once the slag is drained, the main event begins. The drill opens another hole slightly lower down, the iron notch. And from there, with a roar and a blinding glare, a torrent of molten metal is unleashed. It isn't orange, it's a brilliant white gold, so bright it's painful to look at without special glasses. The heat radiates from it, a physical force you can feel on your skin from dozens of meters away. This dazzling river of metal, throwing off fountains of sparks, flows down a long refractory channel into a huge mobile ladle shaped like a giant cigar on wheels, known as a torpedo car. This torpedo can hold several hundred tons of liquid metal and, like a thermos flask, keeps it hot while it's transported to the next stage. What we have created in the blast furnace is called pig iron. It contains a lot of carbon, which makes it very brittle. When the metal cools in the molds, it solidifies. After the mold is broken, a finished cast iron product is revealed. And so, from a cold, red rock through the fiery stomach of the blast furnace where chemistry and heat work their magic, this heavy, reliable, and durable material is born, ready to serve us in our daily lives. Each year, blast furnaces in the United States produce roughly 30 million tons of iron. It's a number so vast, it's hard to comprehend. Let's try. The average Nimitz-class aircraft carrier weighs about 100,000 tons. This means that in 1 year, American plants produce enough iron to build a fleet of 250 of them. Or to put it in more grounded terms, if we take the weight of an average passenger car, that's enough metal to make over 12 million vehicles. An entire automotive nation born in the fire of the blast furnaces in a single year. There are only about 15 blast furnaces currently operating in the entire country. We are not talking about thousands of small plants, but a small number of true titans. This means each of these towers is an incredibly productive monster. The average blast furnace in the U.S. produces over 5,000 tons of iron every single day. Over 90% of all pig iron produced in blast furnaces is not the final product. It is just the first step. This hot, carbon-rich metal is essentially the raw material for making steel. It is transported in torpedo cars to the next plant, where, in oxygen converters or electric furnaces, the excess carbon will be burned off, turning brittle iron into strong, ductile steel. So these 25 million tons of iron are the foundation from which skyscrapers will rise, bridges will be built, and cars, ships, and even simple tools will be made.
There's something almost poetic about watching a massive steel plate, thick as your fist, transform into a perfect cylinder. What we're seeing here is one of Central Europe's finest engineering firms working with a steel plate 4 3/4 inches thick, nearly 10 feet wide, destined to become a cylinder with a 55-inch diameter. For those of us who remember when heavy industry was the backbone of manufacturing, this is the kind of craftsmanship that built the world we know. The star of this operation? The plate rolling machine. And let me tell you, this Italian marvel is about as perfect as metalworking equipment gets. The company's been perfecting this craft since 1946, right after World War II, when Europe needed reliable machinery to shape the infrastructure of the modern age. The machine operates on a 3-roller pyramid principle, which has been the gold standard for rolling heavy plates since the Industrial Revolution, though the precision we're seeing here would have blown the minds of craftsmen from that era. Here's how this beautiful process unfolds. A steel plate, which has been preheated to reduce brittleness, gets positioned between 3 massive cylindrical rollers arranged in a triangular configuration. The 2 bottom rollers are the driving force, rotating in synchronized harmony to pull the plate through, while the top roller, which can be hydraulically adjusted to within fractions of a millimeter, applies downward pressure, creating the curvature. Think of it like rolling out dough, except this dough weighs several tons and could support a building. The operator, working from a computerized control panel, inputs the desired diameter and thickness parameters. The machine's sophisticated sensors continuously monitor the bend radius, making real-time adjustments through hundreds of hydraulic cylinders. Remarkably, despite working with such massive forces, the machine achieves tolerances that would make a Swiss watchmaker proud. The plate makes multiple passes through the rollers, bending a little more each time, gradually approaching that perfect cylindrical form. This incremental approach prevents stress fractures and ensures uniform curvature along the entire length. As the plate begins its transformation, you can actually see physics at work. The outer surface of the bend stretches while the inner surface compresses, and the metal flows like frozen honey, maintaining its structural integrity while taking on this new shape. Now, let's step into the world of heavy forging, where tradition stretches back to the blacksmiths of ancient Rome. Except now we're working with hammers that make Thor's hammer look like a toy. What's especially mesmerizing is the combination of raw power and surgical precision. We're watching parts being forged that can weigh up to 250 tons. The process begins long before the hammer ever strikes. Steel ingots, fresh from the mill, are slowly heated in gas furnaces to temperatures around 2,200 degrees Fahrenheit. This isn't a rushed process. Depending on size, heating can take anywhere from 8 to 24 hours. Once the steel reaches that perfect forging temperature, glowing that unmistakable orange-yellow color that means it's ready to flow, the real dance begins. Massive manipulators, essentially industrial robotic arms that can rotate and position these multi-ton pieces with remarkable delicacy, move the workpiece under the forging press. Both hydraulic presses and mechanical hammers are used, depending on what the job demands. A hydraulic press applies slow, steady pressure, ideal for ensuring the force penetrates deep into the heart of the piece, eliminating any internal voids or inconsistencies. The mechanical hammer, on the other hand, delivers rapid blows that shape the surface and create specific forms. The forge master, a craftsman whose skills require decades to develop, orchestrates this symphony of heat and pressure. Between each strike or pressing, the piece rotates, gets repositioned, and sometimes reheated. This is called open die forging, because unlike closed die forging, where metal is compressed into a specific shape, here the masters are literally sculpting the metal through repeated strikes and pressure applications, gradually drawing it into the desired form. Each strike refines the grain structure, making the steel stronger and more reliable than anything achievable through casting or machining alone. Now let's move on to modern precision forging, which has adapted traditional forging techniques to produce complex automotive and industrial components at volumes that would have been unthinkable in the old days of small batch artisan forging. The process starts with steel bars, often supplied in coils, which are cut to precise lengths and then fed into induction heating systems. Induction heating is one of those technologies that seems almost magical when you first encounter it. No flame, no combustion, but within seconds a steel billet placed inside an induction coil glows cherry red, then orange, then that brilliant yellow-white that tells you it's ready for forging. The secret lies in electromagnetic induction, discovered by Michael Faraday way back in 1831, but only practically applied to industrial heating in the early 20th century. Alternating current flowing through the coil creates a rapidly changing magnetic field, which induces electrical currents in the steel itself, and these currents generate heat through resistance. After heating to the optimal forging temperature, typically between 2000 and 2300 degrees Fahrenheit, depending on the steel grade, the billet moves to the forging press. Sophisticated closed die forging is used, where the hot steel is placed between two die halves that contain the negative impression of the desired part. When these dies come together with thousands of tons of force, the steel has nowhere to go but to fill every contour of that cavity. What's remarkable is the speed and precision of modern forging presses. We're talking about machines that can complete a forging cycle in just a few seconds, yet achieve dimensional tolerances that would have required extensive machining in the past. There's something deeply satisfying about watching skilled craftsmen build storage tanks. The process begins with selecting and cutting steel plates. Modern fabrication shops use CNC cutting tables, plasma or laser, that can slice through thick steel plate with remarkable precision, following computerized patterns that ensure minimal waste. But before any cutting happens, there's meticulous layout work, figuring out how to arrange different components to get the most from each plate. It's a puzzle that combines geometry, efficiency, and materials science. After cutting, the components move to rolling and forming operations. Tank shells typically need to be cylindrical, which means flat plates must be rolled into curves using 3-roll bending machines like the ones we saw earlier. The edges of these rolled sections are then prepped for welding, usually with beveled cuts that let the weld penetrate completely through the material's thickness. The welding process, that's where the craftsmanship really shines. Tank fabrication typically uses submerged arc welding for the main seams, a process where the arc works under a blanket of granular flux, protecting the weld from atmospheric contamination while allowing deep penetration and high deposition rates. End caps, whether they're flat, dished, or hemispherical, get fitted and welded on, and then comes the real test, hydrostatic testing. The completed tank gets filled with water and pressurized above its operating pressure to verify integrity. Any leaks or weaknesses show up here, not during service, which could be catastrophic. Let's wrap up with the 3-roll plate bending operation, because there's something fundamentally impressive about watching these machines transform flat steel into curves with such apparent ease. The 3-roll bending machine is one of those elegant engineering solutions that's remained fundamentally unchanged for over a century because, simply put, it works beautifully. The machine consists of 3 essential rollers arranged in a pyramidal or triangular configuration. The 2 bottom rollers are drive rollers that grip and feed the plate through the machine, while the top roller, which can be adjusted up or down hydraulically, provides the bending force. The beauty of this setup is in its simplicity and efficiency. By varying the top roller pressure and making multiple passes, you can achieve a wide range of diameters and even create nearly perfect circles. The process itself is mesmerizing to watch. The plate enters between the rollers, and as they rotate, you can literally see the flat material take on curvature. For thicker plates or tighter radii, multiple passes are necessary, with each pass increasing the curvature incrementally. Modern machines can handle impressive specs. Plates several inches thick and many feet wide, bending them into cylinders or cones with remarkable precision. The rollers themselves are precision-ground, hardened steel, designed to maintain their shape under enormous loads. This technology represents a perfect marriage of time-tested mechanical principles with modern control systems, creating tools that are simultaneously powerful and precise, capable of forming the steel that builds our world.
Picture a chunk of metal weighing 130 tons, the size of a 3-story building, spinning at 100 revolutions per minute. This is a supertanker's propeller, the most powerful driving force ever created by humans. Every second, this propeller pushes 200,000 tons of cargo forward. A single sweep of its blade generates the power of 50 cars. But here's the most incredible part. This giant is cast as a single monolith. No welding, no bolts. One solid piece of bronze or steel. How did humanity learn to cast metal structures the size of a house? You'll discover why a propeller like this takes 2 weeks to cool, how it's machined for 3 weeks, and why the tiniest crack could send a ship to the bottom. Watch until the end. The finale reveals the scale of engineering madness that moves the oceans. This is the story of how titans of the seas are born.
The history of the propeller began in the early 19th century. Before that, ships moved either under sail, by oars, or using paddle wheels. Paddle wheels were inefficient. Half the energy was wasted. In 1836, British farmer and inventor Francis Pettit Smith patented the screw propeller. The idea was simple. Rotating blades screw into the water like a corkscrew into a cork, pushing the ship forward. Early propellers were small, 4 to 5 feet in diameter, made from wood or cast iron. But as ships grew larger, so did the propellers. By the early 20th century, steel steamships over 300 feet long appeared. They required propellers 10 to 13 feet in diameter. And with the arrival of supertankers and container ships in the mid-20th century, propeller sizes reached incredible proportions. Modern ocean giants stretching 1,300 feet need propellers 26 to 33 feet in diameter. That's the height of a 3-story building.
The world's largest propeller was built for the Emma Maersk container ship, one of the biggest vessels on the planet. The propeller's diameter? 31.5 feet. Weight? 131 tons. That's 2 tanks combined, or 17 elephants. The propeller has 6 blades, each the size of a car. Total blade surface area? About 750 square feet, like a big apartment. The ship's engine produces 109,000 horsepower. All that power flows through a single propeller. At full speed, the blade tips slice through water at 125 miles per hour. Water pressure on the blades? Dozens of tons per square foot. Any crack, any casting flaw, and centrifugal force rips the propeller apart. The ship's dead in the middle of the ocean. That's why manufacturing these propellers is the pinnacle of metallurgy and engineering. The slightest mistake is unacceptable.
Where and how do they make these monsters? The largest propeller manufacturers are in Japan, South Korea, China, Germany, and the Netherlands. The most famous include Japan's Nakashima, Germany's Mecklenburg Metallgas, and the Dutch Worksfor. They have foundries the size of a football field and cranes that can lift 200 tons. The process starts with design. Engineers calculate blade shapes on supercomputers. Angle of attack, curvature, thickness, everything affects efficiency. The propeller needs to create maximum thrust with minimal cavitation, the formation of water bubbles that destroy metal. The tiniest miscalculation and the propeller becomes inefficient or wears out fast. After the calculations, they create a full-size wooden model of the propeller. Yes, wood, 31 feet in diameter. Master craftsmen carve it for weeks using blueprints and templates, precision down to a millimeter. This wooden model becomes the foundation for creating the casting mold.
They coat the wooden pattern with a special compound and place it in a massive flask, a steel box the size of a room. Around the pattern, they pack in molding sand, sand mixed with binding agents. The mixture gets packed layer by layer. Each layer is compacted through vibration and pressure. The process takes several days. Once the flask is full, they split the mold into 2 halves and carefully remove the wooden pattern. What remains is a cavity shaped like the propeller, a negative. They coat the interior surface of the mold with a refractory compound so the molten metal won't damage the sand. Then they bolt both halves back together. The mold has to withstand the pressure of 130 tons of liquid metal. They install the gating system, channels that'll feed metal into the mold. It's calculated so the fill happens evenly, without air pockets or cold joints. The mold is ready. Now comes the really impressive part, melting the metal. In the foundry, there's a massive induction furnace, a steel crucible holding 40 cubic meters wrapped in electromagnetic coils. They load it with bronze or alloyed steel stock, bars, ingots, scrap. 140 tons of metal. That's with a buffer. Some will stay in the gates and risers. They flip the switch. Powerful electromagnets induce eddy currents in the metal. The metal starts heating from the inside. Temperature climbs to 1600 degrees Celsius. The metal melts, glows orange, then white. The surface churns. The crew skims off slag, oxides and impurities floating to the top. They add alloying elements, manganese, nickel, aluminum, for strength and corrosion resistance. They pull a sample of the melt, analyze the composition. When everything's ready, they start the pour. The furnace tilts with a special mechanism. Molten metal flows into a massive ladle suspended from an overhead crane. The ladle holds 140 tons. This is the most critical operation. The metal has to be uniform in composition and temperature. The crane moves the ladle toward the mold. The metal glows a blinding white, so bright you can't look at it without dark glasses. The temperature around it climbs to 140 degrees, even though the ladle's 30 feet away. Workers in silvery heat-resistant suits control the pour. They open the ladle gate. Molten metal flows into the gating system. First as a thin stream to preheat the channels. Then the flow gets stronger. The metal fills the mold from bottom to top, pushing air out through special ventilation channels. The pouring process takes about an hour. 300,000 pounds of liquid metal transfer from ladle to mold. When the mold is full, they close the ladle gate. The metal surface in the mold forms a crust of oxides. They dust it with a special powder that creates a protective layer. Now the waiting begins. The metal has to cool and solidify. But at this size, that's not quick. 260,000 pounds of bronze or steel cool slowly, very slowly. "2 weeks, 14 days the mold sits untouched. Inside, crystallization slowly occurs. Molten metal transforms into solid. Temperature drops at a rate of a few degrees per hour. Cooling too fast leads to cracks from uneven shrinkage. Too slow, large metal grains form, reducing strength. Engineers monitor the process with thermocouples, temperature sensors embedded in the mold. After 2 weeks, they break open the mold.
A crane lifts the flask, opens it up. The molding sand pours away, revealing the casting. Before their eyes, a giant propeller covered in black scale. Weighs 150 tons, 20 tons more than the finished product. Excess metal has solidified in the gates, risers, and allowances. The propeller moves to a special stand. Machining begins, transforming the rough casting into a perfect ship's propeller. And that's another 3 weeks of work. First, they cut off the sprues and risers, solidified metal feed channels. They use gas torches and heavy-duty bandsaws. The cut-off chunks weigh several tons each. They'll go back to the melt shop too. Then rough machining begins on turning and milling machines. These are giant machines, a bed 20 meters long, a milling head weighing 10 tons. The propeller is clamped on a rotating table. Cutters remove the stock, excess metal left for machining. Chips fly off in spirals as thick as a finger. Tons of metal are removed per shift. They mill the hub, the central part of the propeller that fits onto the shaft. A hole about 3 to 5 feet in diameter has to be perfectly round and concentric, precision tenths of a millimeter. Then they machine the blades. Each blade is milled to a complex profile, leading edge, trailing edge, face, back. The profile changes from root to tip. It's a three-dimensional, doubly curved surface. The machine runs on computer control from a program based on design data. After roughing comes finishing. Fine-toothed cutters pass over the blade surfaces, removing fractions of a millimeter. The surface becomes smooth. Then polishing. Abrasive wheels buff the blades to a shine. This is critically important. Surface roughness increases water resistance and promotes cavitation. A perfect surface cuts a ship's fuel consumption by percentage points. For a supertanker, that's millions of dollars in savings per year. After machining, the propeller is weighed and balanced. The center of mass must lie exactly on the rotation axis. Otherwise, vibrations will develop during operation, destroying bearings and potentially damaging the ship's hull. Balancing is done by drilling small cavities in specific locations. The final operation, non-destructive testing. The propeller is X-rayed, checked with ultrasound, examined using magnetic particle inspection. They're looking for internal defects, voids, cracks, inclusions. If they find a critical defect, the propeller is scrapped. 287,000 pounds of metal and a month of work go to waste. The cost of such a propeller, $1 to $3 million. And just like that, making the journey from a wooden model through the hellish heat of 1600 degrees and 140 tons of molten metal, through 2 weeks of cooling and 3 weeks of machining on giant lathes, a propeller is born, the heart of a supertanker, the pulse of an ocean giant. A solid piece of metal the size of a house, weighing 130 tons, capable of transmitting 100,000 horsepower. It's a triumph of engineering brilliance and metallurgical mastery. Every time you spot a container ship on the horizon or an oil tanker in port, know this: beneath the water spins a titan, born in fire and honed to perfection. A monolith of bronze or steel, every square inch of which withstands tons of pressure. A propeller that drives forward half the world's trade. 90% of all cargo moves by sea. This is a story about giants created by humans, about how humanity learned to cast metal the size of a house and machine it with precision down to a millimeter. A propeller isn't just a chunk of metal. It's a symbol of man's dominion over the oceans, a symbol of the technology that connected continents. From wooden model to steel reality, a journey spanning 5 weeks and millions of dollars. A journey repeated hundreds of times a year in foundries across the world, so the planet's fleet keeps pushing forward.
186 miles per hour, 60 tons of metal hurtling down the tracks faster than a race car, and it all rides on 4 wheels, each one heating up from friction to over 1800 degrees Fahrenheit at this very moment. That's hotter than red-hot iron in a blacksmith's forge. One micro crack just 8 thousandths of an inch wide, and you've got a catastrophe at 186 miles per hour. How did they build wheels that can withstand this hell? What kind of steel doesn't crumble under repeated heating cycles? Why can't the metal contain more than 2 parts hydrogen per million? You'll discover how the world's strongest wheels are born, what brutal tests they endure, and why defects here are simply impossible. Stick around till the end. The finale reveals what's behind every second of safe travel at 186 miles per hour. The story of high-speed rail began in 1964 when Japan launched the legendary Shinkansen train. A speed of 130 miles per hour was revolutionary, but conventional wheels couldn't handle that kind of stress. The metal would crack, the surface would fail from overheating. Engineers faced a problem. At 185 miles per hour, a wheel heats up from friction against the rail to over 1800 degrees Fahrenheit. That's a temperature where ordinary steel loses its strength and starts to deform. Every braking, a thermal shock. Every acceleration, a new cycle of heating and cooling. The metal fatigues. Microcracks form. And remember, each pair of wheels carries tens of tons, an entire car weighing around 50 to 60 tons. They needed fundamentally new steel and a completely new manufacturing process. Metallurgists developed a special alloy capable of withstanding the extreme operating conditions of a high-speed wheel. This isn't just steel. It's a precision material with strict requirements for every element. Harmful impurities are reduced to the absolute minimum. Hydrogen gets special attention. This tiny atom can penetrate steel's crystalline lattice and make it brittle. That's why hydrogen content can't exceed 2 parts per million. 2 parts per million, that's like 2 grains of sand in a ton of metal. Only special steelmaking furnaces with vacuum degassing can achieve this purity. Molten steel is held under vacuum so hydrogen leaves the metal. Dozens of sensors monitor every heat. The slightest deviation and the entire batch gets remelted. There are no compromises here. Once the steel is ready, the really impressive part begins. Multi-stage forging of the wheel center. A massive ingot of red-hot metal weighing several tons is fed under a giant hammer. First strike, and the metal starts taking shape. The blank's temperature? Around 2,200 degrees Fahrenheit. The metal glows bright orange, radiating unbearable heat. A forging hammer weighing hundreds of tons slams down on the workpiece with enough force to crush its tank. But here, everything's precise. Every strike calculated by computer. The metal flows, taking the desired shape, while its internal structure densifies. Forging isn't just about shaping, it's about forming the right crystalline structure that'll deliver strength and toughness. After each strike, they rotate the blank, reheat it, hit it again. The process goes on for hours. After forging, the wheel center looks like a rough blank. It's still far from the final wheel, but the metal has already gained internal strength. Now begins the heat treatment, quenching. The wheel is heated to a critical temperature of around 1,600 degrees Fahrenheit and held until the entire structure becomes uniform. Then, rapid cooling in oil or water. The metal freezes in a special state, hard but still too brittle. That's why the next stage is tempering. The wheel is heated again, but to a lower temperature around 900 degrees Fahrenheit and slowly cooled. The metal becomes elastic, tough, capable of absorbing impacts without cracking. It's this combination of hardness and toughness that allows the wheel to withstand hellish working conditions. Heat treatment takes several days, there's no rushing this. Now the wheel heads to machining. Powerful lathes cut away excess metal, shaping perfect geometry. A high-speed train wheel must be perfectly round, accurate to hundredths of a millimeter. The slightest asymmetry? At nearly 200 miles per hour, vibration kicks in. It'll destroy the wheel, the rail, and the car's bearings. The lathe tool peels away metal, layer by layer, revealing a gleaming surface. It's hypnotic. The massive wheel spins, the cutting tool traces the circumference, and long steel shavings curl into spirals before dropping down. Special sensors constantly measure diameter, checking for deviations. After turning, the wheel gets polished to a mirror finish. But the most critical step? Still ahead: quality control. Every wheel goes through a battery of brutal tests. First up, ultrasonic inspection. Ultrasonic waves pass through the metal. If there's even a micropore, void, or crack, just 0.008 of an inch in size, the wave bounces back, and the sensor catches it. A defect that small can become a failure point at high speed. A wheel with that defect? Rejected immediately, no exceptions. Next, magnetic particle inspection. The wheel gets magnetized and dusted with metal powder. If there's a surface crack invisible to the naked eye, the magnetic field distorts at that spot, and the powder gathers into a line. Shows the exact location of the defect. These methods catch flaws you couldn't spot without specialized equipment. But for a high-speed wheel, finding a defect isn't enough. There shouldn't be one at all. After non-destructive testing, samples from each batch are sent for destructive testing. Metal specimens are cut from the wheel and subjected to brutal loads. The specimen is stretched until it breaks to determine ultimate tensile strength. They hammer it at -40 degrees Fahrenheit to test cold toughness. They heat it to 1800 degrees and rapidly cool it hundreds of times in a row, simulating braking and acceleration cycles. If the metal fails even one test, the entire batch is rejected. No compromises. Meanwhile, the wheel is weighed to the nearest gram, balance is measured. If the center of gravity is off by even a fraction of an inch, the wheel is unbalanced and can't be used at high speed. Only wheels that are perfect by every measure get cleared for installation on high-speed trains. Once a wheel passes all inspections, it gets stamped with a special code. This code contains everything: the steel batch number, forging date, craftsman's name, results of every test. If 10 years down the line someone spots even the tiniest defect on that wheel, the code lets them trace back the entire production history and pinpoint the cause. Wheels get mounted on axles in pairs. Each pair has to match perfectly in weight and dimensions. Then the axle with its wheels gets installed into the railcar bogie. The bogie is an incredibly complex piece of machinery with bearings, shock absorbers, and a braking system. And it's the wheels that bear the brunt of it all. Each pair of wheels carries around 15 to 20 tons of railcar weight, plus dynamic loads from acceleration, braking, and taking curves. At speeds of nearly 200 miles per hour, those impact forces multiply several times over. A high-speed train wheel lasts about 600,000 miles. That's circling the Earth at the equator roughly 25 times. During that lifespan, the wheel endures tens of thousands of heating and cooling cycles, millions of impacts against rail joints, constant friction with forces measuring in tons. Every few months, wheels are removed and inspected. They measure the rim thickness, search for cracks, check for wear. If the thickness has decreased beyond acceptable limits, the wheel gets scrapped. If there are signs of metal fatigue, scrapped. Passenger safety doesn't allow for compromise. Only a handful of factories worldwide can produce these wheels. Japan, Germany, France, China, the leaders in this field. Each factory guards its technological secrets, its unique steel composition, its heat treatment methods. This is the highest level of metallurgy and engineering. And just like that, journeying from molten steel through the hellfire of forging, through ultrasonic and magnetic trials, through inspection of every single millimeter, a wheel is born into this world, one capable of carrying 60 tons at speeds of nearly 200 miles per hour. This is a story about how humanity learned to tame force and velocity. Each wheel is a symphony of engineering genius, metallurgical artistry, and ruthless quality control. Contained within it, thousands of hours of labor from hundreds of specialists, dozens of technological operations, and absolute zero tolerance for defects. When you board a high-speed train and landscapes blur past your window at nearly 200 miles per hour, remember this. Beneath you sit 4 wheels, each one having passed through hell itself, all so you can reach your destination safely. This isn't just metal. This is your life guarantee at breakneck speed.
Hey everyone, on this channel we go behind the scenes where cameras usually aren't allowed. If you're into this kind of breakdown, hit subscribe and tap that bell so you don't miss new episodes. Every year, the world recycles over 1.5 billion tons of scrap metal, and hidden within this chaos of rust and mangled iron is something way more valuable than it looks. What seems like trash today could save your life tomorrow at 75 miles per hour. But how exactly does this pile of metal transform into a precision-engineered component trusted by millions of drivers? And why can even a tiny 1% error destroy an entire batch? There's one detail in this process almost nobody talks about, and it's what determines whether your car stops when it really matters. Today, we're breaking down the entire production of brake rotors, from the furnace to final inspection. It all starts with what most people would just call a junkyard. And that's pretty ironic. What will later stop your car at 75 miles per hour, right now looks like a giant pile of rusty junk. Old cast iron radiators, car body fragments, twisted beams, and other metal scrap. It's all stacked in heaps on the lot outside the plant, and rain sends rusty orange streaks running down into the asphalt. But to this factory, it's all treasure. A massive electromagnet hanging from a crane scoops up several tons of this iron and drops it with a crash into the throat of a giant induction furnace. Induction, meaning the metal doesn't melt from fire, but from an electromagnetic field that heats it from the inside out, evenly and fast. If you stand too close, it's kind of terrifying. The furnace hums at such a low frequency that you don't really hear the sound. You feel it deep in your chest, like your heart's trying to sync up with this heavy industrial rhythm. The temperature inside the furnace climbs to 2,700 degrees Fahrenheit. At that kind of heat, even the toughest steel turns into liquid, more like glowing, ridiculously dangerous soup than anything solid or dependable. When the furnace tilts to pour out the molten metal, everything around you floods with bright orange light that makes you want to squint. No artificial beauty here, just brutal physics and an insane amount of heat. Every batch of metal gets tested instantly. Lab techs in special suits grab a small sample, cool it down, and within seconds determine its chemical makeup using a spectrometer. The device breaks the sample down into elements and spits out precise percentages of each component. If the carbon or silicon content deviates from spec by even 1%, The entire massive batch gets sent back for remelting without hesitation. Mistakes aren't tolerated here, because the cost of that kind of error to the end user could be way too high. Next, they pour this liquid fire into molds. They use sand casting technology here. Sand seems like an unreliable material, but at this factory, they mix it with special resins and under enormous pressure, it becomes hard as concrete. The molds are made with jeweler-like precision. The internal relief copies every detail of the future disc, including cooling fins and mounting holes. Metal fills the cavities inside the sand mold, and it's at this exact moment that the rough blank of the future brake disc is born. It doesn't look anything like that shiny part we're used to seeing in auto parts stores yet. Instead, it's something big, heavy, and really dirty. After pouring, the discs need to cool naturally. It's a long process, sometimes taking several hours, and this is critically important. If you try to speed up the cooling, say by splashing water on it, the metal becomes too brittle. A disc like that could just shatter into pieces at the first hard stomp on the brake pedal somewhere out on the highway in the rain. When the blanks cool down to just warm instead of glowing red hot, they head to the machining shop. This is where robot territory begins. They work 24/7, no lunch breaks, no complaints about tough working conditions. Each disc gets grabbed by a manipulator arm that loads it into a CNC machine. Special cutting tools shave off excess metal as easily as if it weren't solid cast iron, but a stick of cold butter. Chips spiral out red hot and drop into a collection tray while a smooth, precisely calibrated surface emerges from under the cutter. At this stage, fanatical precision rules. A deviation of 0.8 of a millimeter means hopeless scrap. A disc like that never makes it to the warehouse because it'll cause vibration that'll just destroy a car's suspension in a few months and force the driver to shell out a ton of cash for repairs. The machine finishes one disc in several minutes, and each one comes out identical to the last. Robots don't get tired and don't lose focus by end of shift. It's fascinating to watch as the perfect, almost mirror-like surface gradually emerges from a rough and ugly form. Then they drill ventilation holes and internal channels into the discs. This isn't done for visual style like some people think. It's a critically necessary cooling system, without which the discs simply wouldn't survive serious loads. During heavy braking, the disc can heat up to 1,300 degrees Fahrenheit. At that temperature, it glows dark cherry red. If this heat isn't removed in time, the metal starts losing its friction properties, and the brakes just disappear at exactly the wrong moment. So these holes and channels, they're the result of extensive engineering calculations, not some design decision for looks. Each channel has a precisely determined diameter and angle, calculated so airflow pulls heat away from the working surface as efficiently as possible. Once all the excess shavings are removed, each rotor gets sent to dynamic balancing. It's a lot like what they do to your wheels at the tire shop, but the precision here is tens of times higher. A special device spins the rotor up to enormous speed and uses sensors to detect the slightest weight imbalance. At these rotational speeds, any imbalance turns into noticeable vibration, and the machine picks it up with gram-level accuracy. If one side turns out to be heavier by even 3 or 4 grams, the machine automatically drills out a tiny, nearly invisible dimple in just the right spot on the face to even out the weight. After that, the rotor is perfectly balanced and ready to perform at any RPM without any extra noise or judder. It's at this stage that the difference is made. whether the driver will feel every imperfection through the pedal or whether braking will stay smooth and silent at any speed. I asked the chief engineer how many of these rotors they produce in a single full workday. He just smiled wearily and said they stopped counting them individually a long time ago. They track output in thousands of tons of finished product per month. Just think about that for a second. This facility supplies parts for nearly half the European automotive market, which means every other car you see on city streets is probably stopping with rotors made right here, in this loud, scorching hot plant. Before packaging, the rotors go through a protective coating process. They're either painted with a special heat-resistant paint or coated with a thin, anti-corrosion, zinc-based layer. The coating gets applied in a chamber, the rotor hangs from a conveyor, and automatic sprayers evenly cover it from all sides. This is done so they don't turn into a rusty chunk of metal during long-term warehouse storage or while crossing the ocean in a shipping container. Sure, after the first few miles of driving, this paint on the working surface will completely wear off under the massive friction from the brake pads, but the edges and internal parts will stay protected from road salt and grime. The final, and arguably most critical stage, is the quality control check. And we're not talking about some tired worker giving it a quick once-over at the end of their shift. They use ultrasonic scanners and X-ray machines. They're hunting for internal defects, air bubbles or micro cracks you couldn't spot even with a magnifying glass. Ultrasound sends a wave through the metal, and if there's a void inside, the signal bounces back distorted. The machine flags the problem zone instantly. Even if the disc looks flawless on the outside, but the X-ray reveals a cavity just 2 millimeters wide somewhere deep in the metal, it gets sent straight to the shredder. Nobody cuts corners on safety here, because everyone knows full well, this part directly determines whether the driver and passengers live or die.
Picture a metal lighter than plastic, burns brighter than the sun itself, and you can pull it straight from seawater. Sound like science fiction? This is magnesium, the metal that revolutionized aviation, space exploration, and even your smartphone. Every year, humanity produces over 1,200,000 tons of this remarkable material. But few people know that behind an ordinary chunk of silvery metal lies technology worthy of science fiction. How does material stronger than steel and lighter than aluminum emerge from ordinary seawater or rock? You'll discover why magnesium burns at temperatures reaching 3,000 degrees, how it's extracted from the ocean floor, and why no modern aircraft can exist without it. Watch until the end. The finale will transform your understanding of what lightness and strength really mean. This is the story of the metal of the future, already here. The story of magnesium began in 1788 in a small English town called Epsom. A local farmer named Henry Wicker noticed something odd. His cows refused to drink water from a particular well. The water was bitter, but it had an amazing property. It healed. People from all around started coming to this spring. That's how a mineral was discovered, later named Epsom salt or magnesia. But this was just the beginning. Pure metallic magnesium was first produced by British chemist Humphrey Davy in 1808 through electrolysis. He passed an electric current through molten magnesium salt and got silvery drops of a previously unknown metal. The metal turned out to be remarkable. It was incredibly light yet strong, and most astonishing, it burned with a blinding white flame, brighter than any material known at the time. In the 19th century, magnesium was rarer than gold. Scientists produced it by the gram in laboratories for experiments. Everything changed when inventors realized something. Magnesium could create brilliant light. Early photographers fell in love with this metal. A flash of magnesium powder delivered such powerful light that you could take pictures even in total darkness. Picture this. The 19th century, a dark studio, a photographer ignites a pinch of magnesium powder and boom! A blinding flash illuminates everything around. That's exactly where the expression magnesium flash came from. But the real breakthrough happened in the 20th century when humanity mastered mass production. Magnesium turned out to be the ideal material for aviation. Lightweight, strong, easy to machine. During World War II, magnesium production skyrocketed tenfold. Military aircraft needed lightweight and durable parts, and magnesium became a strategic material on par with oil and steel. But where does this amazing metal come from? Magnesium is one of the most abundant elements on Earth. It's the 8th most common in the Earth's crust. But you won't find it in pure form. It's too chemically active and always bonded with other elements. The main sources of magnesium are dolomite and magnesite, rocks extracted through open-pit mining. The largest deposits are in China, Russia, Turkey, and North Korea. But there's another source, practically inexhaustible: the ocean. Every cubic mile of seawater contains about 3 million tons of magnesium. Imagine the scale. The world's oceans hold roughly 4 quadrillion tons of magnesium. That's enough to last thousands of years even at current consumption rates. That's exactly why many modern plants are built right on the coast. Why dig in the ground when you can draw from the ocean? Now let's dive into the actual production. There are 2 main methods for obtaining magnesium: thermal and electrolytic. Let's start with the thermal method, which is used when the raw material is dolomite or magnesite from quarries. First, the rock is crushed into small pieces, no bigger than a walnut. Then these pieces go into huge rotating kilns. Picture a steel cylinder the length of a football field, slowly turning. Inside, temperatures hit over 1800 degrees Fahrenheit. At that temperature, carbon dioxide burns off from the dolomite, leaving magnesium oxide, a white powder that looks like chalk. This powder gets mixed with coke and silicon, then pressed into brick-sized briquettes. These briquettes are loaded into special retorts, sealed steel vessels that can withstand extreme conditions. That's where things get really interesting. The retorts are placed into massive furnaces and heated to 2,200 degrees Fahrenheit. At this temperature, the chemical reaction begins. Silicon displaces magnesium from its compounds. But there's a problem. At this temperature, magnesium turns into vapor. Yeah, you heard that right. The metal evaporates, just like water in a kettle. The magnesium vapor rises up through the retort and enters a condenser, a specially cooled chamber. Here, the temperature drops sharply and the magnesium vapor condenses. Crystals of pure metallic magnesium grow on the cold walls. It's like frost on a window, except instead of ice, it's silvery metal. The process happens in a vacuum or in an inert gas atmosphere. Because magnesium is so reactive, it can ignite even in regular air at high temperatures. After several hours, they open the retort. Inside, an ingot of pure magnesium weighing about 22 pounds. It's warm, silvery, covered with a thin oxide film. Now let's break down the electrolytic method. This is exactly what they use when extracting magnesium from seawater. The process starts right on the ocean shore. Seawater gets pumped into massive tanks and treated with lime. The lime reacts with magnesium salts dissolved in the water, forming a white precipitate, magnesium hydroxide. This precipitate settles to the bottom. They collect it and rinse it. You get a white paste that looks like toothpaste. They treat this paste with hydrochloric acid, producing magnesium chloride, a clear solution with a bitter taste. The solution gets evaporated in enormous vats, yielding magnesium chloride crystals, white like coarse salt. These crystals are the key to obtaining pure metal. They load them into electrolytic cells, massive steel containers lined with refractory brick. Inside, molten magnesium chloride at 1300 degrees Fahrenheit glows orange like volcanic lava. A powerful electric current flows through the molten salt, thousands of amps. The magic of electrolysis begins. At the cathode, the negative electrode, droplets of pure magnesium form. They float to the surface because magnesium is lighter than the salt it's extracted from. A layer of liquid metal forms on top, which workers periodically collect with a special ladle. Picture this: a ladle scooping silvery liquid from the surface of a glowing orange melt. It's like skimming cream off milk, except the cream is molten metal at 1200 degrees Fahrenheit. The magnesium is poured into molds and left to cool. You get ingots weighing between 11 and 33 pounds each. They're silvery, lightweight. You can lift a 33-pound ingot with one hand. The surface quickly forms a thin oxide film that protects the metal from further oxidation. Without this film, magnesium would slowly oxidize even in air. Now we've got pure magnesium. But what do we do with it? The applications are vast, and all of them are impressive. Let's start with aviation and aerospace. Magnesium and its alloys are used to make aircraft fuselages, engine components, landing gear. Why? Because weight is everything in aviation. Every pound saved means less fuel and more payload. Magnesium alloys are 40% lighter than aluminum ones with comparable strength. A modern passenger airliner contains several tons of magnesium alloys. Spacecraft and satellites too. When you need to put cargo into orbit, where every pound costs thousands of dollars, magnesium is irreplaceable. The automotive industry has fallen in love with magnesium too. Engine blocks, transmission components, wheel rims, all made from magnesium alloys, especially in sports and racing cars where weight is critical for speed and handling. A single magnesium rim weighs half as much as a steel one with the same strength. Electronics. Another massive area where it shines. Laptop cases, tablets, smartphones, cameras, often made from magnesium alloys. Why? Lightweight plus excellent heat dissipation plus strength. Your smartphone or laptop might be packing magnesium right now. Magnesium is also used to protect other metals from corrosion, so-called sacrificial anodes. They're installed on ship hulls, underwater pipelines, oil rigs. Magnesium oxidizes first, protecting the main steel structure. Global magnesium production sits at around 1.2 million tons per year. China cranks out about 85% of all magnesium. Russia, the US, and Israel, other major producers. Magnesium prices swing from $2,000 to $4,000 per ton, depending on purity and market conditions. That's cheaper than aluminum, but pricier than steel. And so, traveling from bitter water in an English well, through dolomite quarries and endless oceans, through the hellish heat of furnaces at 1200 degrees, and the cold of crystallization, magnesium emerges into the world. A metal lighter than plastic and stronger than many steels. This is the story of how humanity learned to transform rock and seawater into a material that lifts planes into the sky and sends satellites to the stars. Every time you board an aircraft, hold your smartphone or watch fireworks burning with blinding white flame. Remember, behind it all is magnesium, an ancient element we learned to tame just 200 years ago. A metal that taught us lightness and strength can go hand in hand. The metal of the future harvested from an infinite ocean that will serve humanity for thousands of years to come.
Inside, the pressure hits 2,300 pounds per square inch. Temperature, 608 degrees Fahrenheit. Wall thickness, 8 inches of solid steel. This is a nuclear reactor vessel, one of the most complex industrial objects humans have ever built. It weighs 330 tons, stands 36 feet tall. Diameter, more than 15 feet. Service life, 60 years of continuous operation under radiation bombardment. Inside, a controlled chain reaction unfolds. Billions of uranium atoms splitting every single second. And it's all contained by one steel shell that can't develop even the slightest crack over decades of operation. One microscopic manufacturing error, and the price won't be measured in dollars. Today, you'll see how we build a vessel capable of withstanding hell. It all starts at a steel mill, with a massive furnace where the future steel of the hull is melted. This isn't ordinary steel. It's a special low-alloy blend with nickel, manganese, molybdenum, chromium, and vanadium. Carbon content, strictly no more than 0.25%. The slightest trace of sulfur or phosphorus, rejected. For one hull, you need to smelt up to 600 tons of metal. The melting happens in a vacuum induction furnace at 2,900 degrees Fahrenheit. The vacuum removes gases and impurities from the molten metal. Then the metal is poured into a giant ingot, over 8 feet in diameter and weighing up to 400 tons. An ingot like this cools slowly, very slowly, up to 2 weeks under insulation. Any rush, and microcracks appear in the structure, which later lead to catastrophe. Then comes the forging. First, the ingot gets heated in the furnace to 2,200 degrees Fahrenheit. Then it's moved under the press. The press force? 15,000 tons. For comparison, that's the weight of 3 Eiffel Towers concentrated on a single die. The press hammers the red-hot blank again and again, hundreds of strikes per operation. The metal flows like thick honey, changing shape under monstrous pressure. The grain structure densifies. Fibers stretch out, strength multiplies. After forging, the blank looks like a giant steel ring. Outer diameter, 16 feet. Wall thickness, 12 inches. Weight of one ring, 165 tons. For a single vessel, you need 4 to 6 of these rings. They'll be assembled into the top section, the cylindrical shell, and the elliptical bottom head. Each ring takes a week to make. Next up, machining. Each ring goes onto a vertical boring mill as tall as a 3-story building. A faceplate 20 feet across rotates slowly while the cutting tool shaves off layer after layer. The chips pile up so fast, they're collected in containers holding several tons. Machining tolerance, down to 0.004 inches. That's 500 times thinner than a human hair. The surface has to be perfectly smooth. Any imperfection becomes a stress concentrator. And the pressure inside a reactor, 2,300 pounds per square inch, multiplied across an area of hundreds of square feet. One scratch, and years later, a crack forms there. After machining, every ring undergoes ultrasonic testing. Sensors scan straight through the metal, hunting for any internal defects. A crack the size of a pinhead, and the ring gets sent back to the melt. months of work lost. Now comes the most critical stage, welding. The rings are joined together using submerged arc automatic welding. A single weld runs continuously for several days, without a single stop. During that time, up to 2 tons of weld metal gets deposited into the joint. Welders work in shifts, monitoring every millimeter of the weld through cameras and sensors. The welding zone temperature hits 2,700 degrees Fahrenheit. Around the vessel, a constant preheat of 300 degrees is maintained. Otherwise, the steel will crack during cool down from thermal shock. After welding, every seam gets checked with X-ray, ultrasound, and magnetic particle testing. 3 types of inspection. Not a single defect can slip through unnoticed. If you're curious how things get built to withstand decades of extreme conditions, subscribe to the channel. There's a lot more ahead. Processes humanity mastered through enormous effort. Next up is heat treatment. The assembled vessel gets loaded into a massive furnace, 26 feet in diameter and 50 feet long. Temperature climbs to 1,200 degrees Fahrenheit. The vessel stays at this temp for up to 30 hours. Then comes slow cooling, 36 degrees per hour. The entire process takes up to a week of continuous furnace operation. This relieves internal stresses from welding. The metal structure stabilizes. Strength becomes uniform throughout the entire vessel. Skip this step and the vessel will crack within the first year of operation. After heat treatment, the vessel heads back to machining. Now they're finishing the interior surfaces, flanges, and pipe connection points. The vessel has up to 12 openings for primary loop piping, each one machined to micron-level precision. Deviate by 0.004 of an inch, the entire vessel gets scrapped. But bare steel won't survive contact with the coolant. Primary circuit water at 700 degrees Fahrenheit and 2,350 pounds per square inch slowly eats away any carbon steel. Over 60 years, it would corrode straight through the wall. So the vessel's inner surface gets coated with a stainless steel overlay. The coating thickness runs 1/4 to 1/3 of an inch. The overlay goes on automatically. Wire feeds through at several feet per minute. An electric arc melts it and lays down layer after layer. Within days, a continuous corrosion-resistant barrier builds up on the inner walls. Coverage area up to 1,600 square feet. After overlay welding comes grinding again, inspection again, checking every square inch again. Any missed spot means corrosion sneaking in 20 years down the line. The finished vessel weighs 330 tons. It's 36 feet long, over 15 feet in diameter. It travels by rail on a special multi-axle transporter. Speed, no more than 9 miles per hour. Routes are planned months in advance, reinforcing bridges and widening curves. Sometimes they build new roads, just for one load. At the nuclear plant, the vessel is lowered into a concrete shaft 65 feet deep, and the work begins. Work that will last 60 years, 6 decades under constant radiation, pressure, and heat. During that time, the steel atoms change at a subatomic level under neutron bombardment. But the vessel holds, because built into it are months of work by thousands of people, hundreds of quality checks, and absolute precision at every stage. Humanity learned to build vessels that contain a tamed star, and each one is a quiet monument to that ability. Subscribe to the channel.
Ever wonder how you make a material just 6 microns thick? That's 15 times thinner than a human hair. So thin that if you hold it up to the light, you can read a newspaper through it. So fragile that one wrong move and it tears, yet so strong it can withstand temperatures of 570 degrees Fahrenheit and protect your food from light, oxygen, and bacteria better than any plastic. I'm standing at the gates of the Eurofoil plant in Dudelange, Luxembourg, one of the largest aluminum foil manufacturers in Europe. Here, across 50 acres, 100 tons of foil are born every single day. That's over 600 million feet, a ribbon you could wrap around the Earth 5 times at the equator. The air is thick with the smell of hot metal and machine oil. The roar of the rolling mills is so powerful the ground vibrates beneath your feet. Welcome to the place where aluminum makes the journey from crude ingot to an almost invisible film. This isn't just a factory. This is a laboratory of precision at the edge of what's physically possible. The process begins in the foundry where real metallic hell reigns. 4 continuous casting machines run non-stop 24 hours a day, 365 days a year. I put on protective goggles with dark filters. Without them, looking at molten aluminum is just dangerous. The temperature here stays at 1330 degrees Fahrenheit. This is the melting furnace where they load aluminum ingots, massive bars weighing 55 pounds each. But Eurofoil prides itself on being eco-friendly. 70% of the raw material here is recycled aluminum. Foil scraps, production waste, even old soda cans, everything gets used. Aluminum can be melted down infinitely and it doesn't lose its properties. Jean-Pierre, the plant's head metallurgist, shouts in my ear. We're standing on a platform above the furnace, and the heat is so intense that the skin on my face starts tingling. In the enormous crucible, a silvery liquid churns, molten aluminum. But this isn't just pure metal, it's an alloy. Depending on the intended purpose of the future foil, they add magnesium, manganese, silicon. For food-grade foil, alloy 8011. For technical foil, alloy 8079. Each percentage of additive changes the properties: strength, plasticity, corrosion resistance. From the furnace, molten metal flows into the casting machine. 100-foot-long monster. Here's where the magic happens. Liquid metal at 1300 degrees turns solid in seconds. This is continuous casting. Molten aluminum pours between 2 rotating water-cooled rolls, 6 feet across. Inside those rolls, water circulates at 150 pounds per square inch. When scorching aluminum hits cold steel, instant crystallization. The sound? Like dumping a bucket of water on a blazing stovetop. Hissing, crackling, clouds of steam. Out from under the rolls comes an aluminum ribbon, 1/3 of an inch thick, 5 feet wide. It's still glowing dull red, around 750 degrees. The ribbon crawls forward at 10 feet per minute, slowly cooling in the open air. I step closer and watch as a distinctive pattern emerges across the metal surface. That's the crystalline structure of aluminum. Metallurgists call this grain. Everything depends on the size and shape of those grains, how well the foil will stretch, whether it'll tear during winding, how it'll behave under heat. The perfect grain is a labyrinth, Jean-Pierre explains. The crystals need to interlock with each other, creating a strong network. If the grain's too coarse, the metal becomes brittle. Too fine, it loses flexibility. The cooled strip winds into giant coils weighing 12 tons each. These are blanks for the next stage, hot rolling. We move to the adjacent shop, where rolling mills stand as tall as a 2-story building. Here they start rolling the aluminum strip like dough, except instead of a rolling pin, 50-ton steel rollers, and instead of a table, an alloyed steel frame 3 feet thick. They feed the coil into the mill. The rollers spin, grip the strip, and pull it through with monstrous force. Pressure hits 1,200 tons per square meter. The metal resists, springs back, but gradually gives in. After the first pass, thickness drops from 8 millimeters to 4. After the second, down to 2. Speed builds. If at first the strip crawled at 5 meters per minute, after the third pass it's flying at 300 meters per minute. Air whistles. The strip hums like a taut string. Each pass generates massive heat. Metal grinding against steel heats the strip to 250 degrees, so the rollers get continuous cooling emulsion, a water oil mix. It sprays at 30 atmospheres of pressure, forming a white cloud of mist through which the strip shoots like silver lightning. After hot rolling, the strip, now 0.12 inches thick, heads to annealing. This step is critical. Here's why. During rolling, aluminum work hardens. It gets tough and brittle. The metal's crystal lattice deforms. Internal stresses build up. Keep rolling without annealing? The strip just tears. The annealing furnace is a tunnel 260 feet long. The strip travels through at 33 feet per minute. Inside, the temperature hits 930 degrees Fahrenheit in a nitrogen atmosphere. Oxygen is completely excluded. Otherwise, the aluminum oxidizes and gets covered in loose black scale. At that temperature, recrystallization happens. The metal's deformed grains heal. Internal stresses release. The aluminum goes soft and ductile again. This process takes 2 hours. Coming out of the furnace, the strip cools in a water bath, then gets dried with hot air. Now it's ready for the most demanding stage, cold rolling to final thickness. The cold rolling mill, that's the heart of the factory. 3 state-of-the-art rolling stands here, capable of rolling aluminum down to 6 microns thick. That's the limit. Any thinner? Physically impossible without tearing. The process takes 20 passes. Each pass reduces thickness by roughly 30%. 0.12 inches becomes 0.08, then 0.06, then 0.04, and so on, until you hit 0.0024 inches, 6 microns. Rolling speed on the final passes? 67 miles per hour. The foil ribbon flies faster than a car on the highway. The slightest vibration, the tiniest roller deviation, and it tears. A tear at that speed means shutting down the entire line, losing several tons of material and hours of rethreading. That's why laser thickness gauges are installed here, measuring the strip 200 times per second, accurate to 0.4 microns. The computer instantly corrects roller pressure, rolling speed, coolant flow. A human? Couldn't react fast enough. I'm watching the monitor in the control room. The thickness graph runs flat. 6.0 microns, 6.1, 6.0. Deviation within plus or minus 0.8 microns. That's perfection. But there's a problem. You can't roll foil 6 microns thick in a single pass. It sticks to itself, tears, crumples. So they use a clever trick, doubling. 2 layers of foil, each 12 microns thick, are stacked together and rolled as one. The rollers press down, and both layers simultaneously thin to 6 microns. But between them remains the thinnest air gap. After rolling, the layers are separated. And here's where an interesting effect shows up. One side of the foil, the one that contacted the roller, comes out, shiny, mirror-like. The other side, which contacted the neighboring foil layer, stays matte. You've probably noticed this on kitchen foil. Well, it's not a defect and not a special coating. It's the trace of the doubling process. The matte side is the imprint of the microtexture from the adjacent sheet. At the molecular level, it's covered with microscopic irregularities that scatter light. The finished foil gets wound onto huge jumbo rolls, 6.5 feet across and weighing 3 tons. These are the mother rolls. From them, they'll later cut foil to the needed width. For chocolate wrapping, 12 inches; for yogurt lids, 2 inches; for industrial uses, 4 feet. Quality control at Eurofoil borders on paranoia. And that's a good thing. Every jumbo roll goes through a dozen tests. First up, backlighting. The foil passes in front of a powerful lamp. Any microcrack, any pore, and light will shine through. A computer flags the defect, and that section gets marked as scrap. Second, leak testing. A foil sample gets clamped between two chambers. Helium under pressure is fed into one. A highly sensitive detector sits in the other. If even a single helium molecule seeps through the foil, test failed. Third, mechanical testing. The foil is stretched on a specialized machine, measuring tensile strength. Quality foil must withstand a load of at least 15 megapascals. That's roughly 330 pounds per square inch. For a material 6 microns thick, that's a phenomenal number. Fourth, chemical analysis. Every 2 hours, they take a sample and run it through a spectrometer. It shows the exact alloy composition down to hundredths of a percent. Any deviation, and the batch goes back to the smelter. Fifth, corrosion testing. A sample is held in salt fog at 95 degrees Fahrenheit for 72 hours, simulating 3 years of use. If corrosion shows up, it's scrap. The final stage, slitting and packaging. Jumbo rolls feed into slitter rewinders. Disc blades made from hardened steel, sharpened to razor-edge sharpness, cut the 10-foot wide web into narrow strips of the required width. Slitting speed, 1,600 feet per minute. Blades spin at 3,000 revolutions per minute. The slightest wobble, and the foil edge comes out ragged, jagged. That's why blades get swapped every 8 hours. Slit rolls move to winding. Here the foil winds onto cardboard cores 3 inches in diameter. For household foil, the standard, 33 feet per roll. For the food industry, rolls of 1,000 feet, 1,600 feet, 3,000 feet. An automatic system measures the required length, cuts, seals the edge, marks the roll with a barcode. Output, 200 rolls per minute. Finished rolls get packed into cardboard boxes, boxes loaded onto pallets, pallets hauled to the warehouse. From here, Eurofoil foil ships to 70 countries worldwide. To Germany for chocolate wrapping, to France for cheese factories, to Italy for coffee capsules, to Switzerland for pharmaceutical blister packs, to Japan for electrolytic capacitors. I'm standing in a finished goods warehouse. Around me, stacks of pallets tower 13 feet high. Each pallet holds 2,000 rolls of household foil or 50 jumbo rolls of industrial grade. The product stored here is worth around 5 million euros. The plant runs at full capacity, 100 tons of foil per day, 3,000 tons per month, 36,000 tons per year. That's enough material to wrap the entire United Kingdom in a continuous sheet, or package 15 billion chocolate bars, or make 300 billion yogurt lids. This entire foil empire was born from a simple piece of aluminum that passed through the inferno of casting furnaces, the monstrous pressure of rolling mills, the precision of laser measurements, and rigorous quality control. From 8 millimeters down to 6 microns, a journey 1,300 times over. If you found it interesting to learn how a material thinner than a human hair but stronger than many plastics is created, hit the like button on this video. Write in the comments whether you knew that aluminum foil can be recycled infinitely. And subscribe to the channel to keep discovering the technologies that surround us every day but remain invisible.
Every year, over 15 billion tons of ore, coal, and rock are extracted worldwide. And hauling all of it? An army of machines you'll almost never see on regular roads. Mining dump trucks. Giants weighing over 600 tons, with wheels taller than a grown person, and a single bed that can hold several railroad cars worth of rock at once. Next to them, a regular truck looks like a toy. But the most astonishing thing isn't their size. What's astonishing is how, from simple steel sheets, bolts, and cables, emerges a machine capable of working non-stop for decades in the harshest conditions on the planet. One such dump truck can cost over $5 million and only pays for itself through relentless operation day and night. Its engine burns through up to 100 gallons of fuel per hour, and one fully loaded bed can weigh more than a Boeing 747 passenger jet. In this documentary, The Factor-In reveals how one of the most powerful transport machines in the modern world is assembled from scattered metal. The journey of a mining haul truck doesn't start at the factory. It starts at a computer. Engineers design every single part in CAD systems where the 3D model undergoes dozens of simulations for load stress, vibrations, and thermal behavior. A machine weighing over 1,300,000 pounds has to withstand the impact of falling rock, temperature swings from -40 to +120 Fahrenheit, and thousands of hours running non-stop. Every fraction of an inch of the frame, every support point, every weld seam is calculated in advance. Engineers even model how the truck will perform on steep mine inclines when fully loaded. Once the blueprints are approved, material selection begins. The main frame is built from high-strength alloy steel, capable of handling impact loads in the hundreds of tons. Suspension components go through additional heat treatment. Only when all documentation is signed off do tons of steel plate arrive at the plant. Steel sheets up to 4 inches thick arrive at the cutting shop. Here, human labor has been almost entirely replaced by automated systems. Plasma and laser cutting machines with numerical control carve out parts accurate to within a few thousandths of an inch. The plasma jet temperature hits 36,000 degrees Fahrenheit, enough to instantly slice through metal of any thickness. A modern machine can process dozens of tons of steel in a single shift, cutting hundreds of complex shapes. Even a deviation of just a few thousandths of an inch at this stage can later cause deformation in a structure weighing hundreds of tons. After cutting, parts move to bending. Massive hydraulic presses applying thousands of tons of force shape curved surfaces, stiffening ribs, and cabin elements. Metal that seemed unshakable deforms under pressure and takes the required form. Each part at this stage receives its own unique number and enters the plant's unified digital tracking system. The next stage? The welding shop. Here, thousands of individual steel components become one solid structure. The dump truck frame, capable of withstanding impacts from multi-ton chunks of rock, gets assembled on specialized jigs that lock parts in precise position. First, workers tack weld, short welds, temporary holds. Then, the robotic welding arms take over. They move with insane precision, laying down long, deep, continuous beads along massive steel components. But robots can't replace humans entirely. Not yet. In hard-to-reach spots, highly skilled welders work by hand. Every weld gets checked, ultrasound, X-ray, because a hidden crack inside the metal could later tear the whole structure apart under load. Welding the mainframe alone can take several weeks of non-stop work. This is where the skeleton of the future machine is born. After welding, the frame heads to the paint shop. The surface gets cleaned using high-speed shot blasting. Metal beads fired under pressure strip away rust, scale, and leftover weld slag. Then a layer of zinc primer gets applied, seeping into every corner and creating corrosion protection for decades to come. Only after that does the top coat go on, typically yellow, the signature color of heavy machinery visible in any weather. Meanwhile, in other shops, production of key assemblies is underway. The massive diesel engine that'll become the heart of the machine can displace over 20 gallons and pump out more than 4,000 horsepower. Just one of these engines weighs dozens of tons. Nearby, transmissions, electric generators, and hydraulic systems are being prepped. Each one is itself an incredibly complex piece of engineering, developed over years. Hydraulic cylinders that lift dump bodies weighing hundreds of tons get tested under pressure hundreds of times greater than atmospheric. final assembly is the most spectacular stage of the entire process. In a massive assembly hall, the frame is lifted by giant overhead cranes and positioned onto assembly supports. Then, step by step, installation of components begins. The engine is lowered into the central section of the machine with millimeter precision and secured with high-strength bolts. The cooling system, fuel system, and exhaust are connected to it. Next come the electrical generators, since modern mining dump trucks operate on a diesel-electric system. The engine spins the generator, which then powers electric motors built right into the wheels. This setup allows enormous torque to be transmitted without losses through long mechanical shafts. Then the wheels are installed, each one over 13 feet tall and weighing around 5 tons. A single wheel costs as much as a premium car, and replacing one in the field requires specialized equipment and takes an entire workday. The body goes on last, a giant steel basin with a capacity exceeding 12,500 cubic feet. After full assembly, the haul truck undergoes a series of tests. Engineers fire up the engine for the first time, and its roar fills the entire shop floor. They check hydraulic system pressure, coolant temperatures, and generator operation. The machine rolls out to the test grounds where it makes its first moves, raises and lowers the empty bed, and runs through braking and maneuverability tests. Every sensor, every electrical circuit, every safety system gets checked under real-world load. Only after all parameters are confirmed does the haul truck receive its markings, go through final cleaning, and get prepped for shipment. But shipping it the usual way? Impossible. The machine gets broken down into large modules, loaded onto specialized trailers, and hauled to the job site, where the whole assembly process happens again, this time right at the mine. From digital blueprints and tons of steel sheets to a finished machine weighing over 600 tons, the entire process takes months of intense work by hundreds of engineers and workers. A mining haul truck isn't just transportation, it's the living embodiment of engineering genius, where every bolt, every weld, and every hydraulic line is calculated for decades of operation in extreme conditions. These machines rarely appear in the frame of everyday life, but they're the ones driving global mining operations, supplying raw materials to the entire global industry. Without them, modern metallurgy, energy production, and construction would be impossible to imagine. If you want to see more industrial processes like this, subscribe to the Factorin channel and stay tuned for new episodes.
Every hour, somewhere in the world, a metal component weighing over 50 tons is manufactured, and a single microscopic error in its machining can trigger a multi-million-dollar catastrophe. Picture a crankshaft as long as a bus that must survive a billion cycles of explosive force, or a cylinder block where a deviation the thickness of a human hair means scrapping a multi-ton giant entirely. But here's the mystery. How do engineers achieve micron-level precision when machining parts heavier than a tank? What happens in that secret quality control room, where a computer measures thousands of points and can shut down the entire process? And most importantly, stick around until the end, because I'm going to show you the final operation where one tiny slip turns months of work into scrap metal. This is manufacturing where every thousandth of an inch is a matter of engine life and death. Ready to look inside? The first thing that hits you at this facility? The sheer scale. Forget your average car engine. Take this cylinder block, for example. It can weigh dozens of tons. This isn't just a casting, it's a complex, multi-layered masterpiece of foundry art, requiring special grades of steel or cast iron that can withstand unbelievable loads, temperatures, and pressures. And here's the crankshaft. In big engines, this thing can be as long as a small bus and weigh just as much. This component is probably the most critical. It has to endure the explosive force of fuel combustion, converting it into rotational motion. The blanks often arrive as massive forgings where every pound of metal already has its own story. The process starts with incoming inspection. Specialists check the chemical composition, scan for internal defects using ultrasound and X-ray equipment. Because even the tiniest hidden flaw in a part this massive could lead to catastrophe during operation. It's like a health checkup for a steel giant. Only after a thorough inspection does the blank get clearance to enter the machine shop. Moving these blanks takes serious muscle. That's why the shop is equipped with powerful overhead cranes capable of lifting loads that outweigh most ordinary machine tools. Mounting the part onto the machining center is a precision operation requiring coordination and experience. This is the first step in turning metal into might. Now we move to the heart of the shop, the cylinder block machining zone. This is where multi-axis machining reigns supreme. Before you stands a gantry-type milling machining center. It looks more like a small house than a machine tool. Its spindles, fitted with ultra-hard cutting inserts, can remove up to several hundred pounds of metal per hour. The first operation is roughing. The goal, remove excess stock, eliminate surface casting defects, and give the part its basic geometry. The speed and sheer aggression of this cutting process? Absolutely mind-blowing. Those streams of hot chips tell you everything you need to know about the energy being dumped into this transformation. But the real magic happens later, during finishing operations. Remember when we talked about precision? For diesel engines, perfect cylinder geometry isn't just important, it's critical. That's where boring and honing come in. Boring creates the cylinder holes with micron-level accuracy. The slightest geometric error means uneven wear, compression loss, and ultimately engine failure. And honing, that's the final touch. A specialized tool with abrasive stones creates a micro-texture on the cylinder's inner surface, what we call crosshatch. This crosshatch is essential for holding oil and ensuring perfect lubrication of the piston rings. We're talking about polishing at nearly molecular level, guaranteeing engine life measured in decades. These machines operate under strict temperature control. Any temperature fluctuation can cause thermal deformation in a part weighing several tons, which means losing precision. That's why the shop floor maintains a constant microclimate, and the machining itself can run for days. Up next, meet our next hero, the crankshaft. This component works under the most demanding conditions. It needs not only colossal strength, but perfect balance. Manufacturing it, an engineering masterpiece. First up, preliminary journal machining. On specialized CNC turning milling machines, the connecting rod journals and main journals take shape. Given the weight and length of the shaft, unique support systems are used here to prevent sagging and vibration during machining. The critical stage, grinding. The shaft journals must have minimal surface roughness because that's exactly where friction with the bearings occurs. The smoother the surface, the less friction, and the longer the engine lasts. Special cylindrical grinding machines with highly sensitive sensors handle this job. Now, for the critical part, heat treatment and surface hardening. After grinding, the crankshaft journals undergo induction hardening or nitriding. What does this do? It creates a super hard, wear-resistant layer on the journal surface while maintaining the core's toughness and strength. This is essential so the shaft can withstand billions of load cycles. Think of it as armor for the engine's most vital component. Final stage, balancing. Given the massive weight, even a tiny imbalance can destroy the engine. That's why every crankshaft goes through dynamic balancing. If the machine detects a deviation, counterweights are added, or material is removed from the flywheel sections until the shaft achieves perfect balance. It's like tuning a violin, except instead of music, we get harmony of rotation and power. How do you achieve that kind of precision when working with such giants? The answer lies in the tooling and quality control. The tool itself is a high-tech product. Every cutter, every mill is equipped with carbide inserts or even synthetic diamonds. They have to withstand enormous temperatures and cutting pressures. Special coatings extend the life of these tools while keeping machining quality consistently high. In a dedicated tool room, there's constant monitoring of their condition, resharpening, and replacement. But the most important thing is quality control. After every key operation, the part undergoes rigorous measurement. Coordinate measuring machines help us with this. These machines, equipped with high-precision probes and laser scanners, can measure up to 1,000 points on a part's surface with accuracy down to a few micrometers. They create a three-dimensional map of the part and compare it to the perfect computer model. If the error exceeds the tolerance, the process stops, and the part gets sent back for rework or, worst case, scrapped. No part leaves the shop floor until the computer gives the green light on its perfect accuracy. And then, when all the components, the block, crankshaft, cylinder heads, connecting rods, have passed strict inspection and achieved perfect precision, they're ready for the final stage. Assembly. This is a different shop, where sterile cleanliness reigns. Assembling an engine like this is no less precise a process than machining. All parts are thoroughly washed, removing even microscopic traces of metal chips and dirt. Specialists use torque wrenches to tighten thousands of bolts to a precisely defined spec. A mistake in torquing the cylinder head, for example, can lead to a blown gasket and engine failure. Every stage of assembly is tracked and controlled by electronic systems. Not a single bolt gets tightened without computer confirmation. After assembly, the engine heads to the test stand. Here it's fired up and gradually brought to operating conditions. Sensors measure temperature, oil pressure, vibration, power output. Any deviation from the norm, and the engine goes back for rework. Only after successfully passing all tests does the engine receive its quality certificate. These giants get installed on ocean vessels, locomotives, mining dump trucks, power plants. One of these engines can run for decades, churning out thousands of horsepower. And behind every hour of its flawless operation stand months of work by engineers, machine operators, quality inspectors. Manufacturing these engines is the pinnacle of mechanical engineering, where metallurgy, precision mechanics, and computer technology converge. And just like that, starting from a multi-ton forging, through rough and finish machining, through honing with precision down to microns, through heat treatment and balancing, through sterile assembly and rigorous testing, an engine is born, capable of running billions of cycles without a single failure. This is the story of how humanity learned to create steel hearts for the most powerful machines on the planet. Every crankshaft, every cylinder block, it's a symphony of engineering thought where an error of 1 micron means failure, and success means decades of flawless operation. When you see a massive ship crossing the ocean, or a locomotive pulling thousands of tons of cargo, remember, At its heart beats an engine, every part of which has passed through the hands of master craftsmen and the scrutiny of computers. This isn't just metal, it's the embodiment of humanity's drive for perfection, where precision is measured in microns and reliability in decades of impeccable service.
The Caterpillar 3618 engine, 18 cylinders, 88 gallons of displacement, 7,200 kilowatts of power, 9,655 horsepower. One engine weighs 79,000 pounds. The piston in this engine, 11 inches in diameter, 11.8 inches of stroke, 50 pounds in weight. This is Caterpillar's largest piston. How do they make it from liquid aluminum? Today you'll see the complete production cycle of a giant piston, from an aluminum ingot to a part that moves at 33 feet per second and withstands 2,685 psi. If you want to see how they make the heart of a giant engine, subscribe to the channel. Here we show you the factories that move the world. The Caterpillar 3618 engine is designed for high-speed marine vessels, ferries, patrol boats, yachts. A single engine produces 9,655 horsepower at 1,050 revolutions per minute. It's a V18 four-stroke diesel. Cylinder bore is 11 inches. Stroke is 11.8 inches. Displacement per cylinder is 1,130 cubic inches. 18 cylinders total, 20,330 cubic inches. Compression ratio 12.6 to 1. Maximum cylinder pressure 2,680 psi. That's 185 atmospheres. Combustion chamber temperature 3,600 degrees Fahrenheit. Mean piston speed 34.4 feet per second. The piston travels 11.8 inches in 0.028 seconds. Up and down 1,050 times per minute. 70 million cycles over 10,000 hours of operation. The piston material has to withstand all of that. The piston is made from an aluminum alloy. Aluminum is lightweight, density of 169 pounds per cubic foot. That's 3 times lighter than steel. Aluminum conducts heat well. Thermal conductivity of 133 BTU per hour per foot per degree Fahrenheit. That's 5 times better than steel. They use alloy 2618. Composition: 92% aluminum, 4% copper, 1.5% magnesium, 1% nickel, 1% silicon. Copper provides strength at high temperatures. Magnesium increases hardness. Nickel reduces thermal expansion. Silicon improves casting properties. The alloy arrives in ingots. Shape: a cylinder 12 inches in diameter, 3 feet 3 inches long. Ingot weight: 353 pounds. Before forging, the ingot is cut into blanks. Blank length: 12 inches. Weight: 84 pounds. This is the blank for one piston with extra material for machining. The blank gets loaded into an induction furnace. Temperature: 895 degrees Fahrenheit. Heat time: 30 minutes. The aluminum softens. Doesn't melt. Melting happens at 1220 degrees. We need plasticity for forging. The heated blank transfers to a forging press. Hydraulic press. Force: 10,000 tons. That's 100 meganewtons. The blank sits in the lower die. Die made from heat-resistant steel. The upper die descends from above. The press creates pressure. Aluminum flows, fills the die cavity, takes the shape of a piston. The process is called backward extrusion. Metal flows upward around the punch, forms the piston skirt. Pressure climbs to 10,000 tons. Forging time: 12 seconds. Metal densifies. Grains align along stress lines. This makes the piston strong. Forging increases strength 30% compared to casting. After forging, the press opens. Piston extracted. It's hot, 750 degrees. Weight, 66 pounds. Shape's close to final, but machining still needed. Heat treatment. The forged piston goes into the hardening furnace. Temperature, 986 degrees Fahrenheit. Hold time, 8 hours. Copper and magnesium dissolve into the aluminum. The structure becomes uniform. Then, rapid cooling in water. Water temperature, 68 degrees. Cooling rate, 180 degrees per second. Copper and magnesium don't have time to precipitate out. They're trapped in the lattice. Strengthening zones form. After quenching, the piston is soft. Hardness, 60 on the Brinell scale. Artificial aging is needed. The piston is heated again. Temperature, 374 degrees. Time, 16 hours. Copper and magnesium precipitate from the lattice as fine particles. They strengthen the aluminum. Hardness climbs to 135 on the Brinell scale. Strength reaches 65,000 pounds per square inch. Elongation, 10%. The piston is strong and ductile at the same time. Machining begins with the turning operation. The piston gets clamped into the chuck of a CNC lathe. The chuck diameter is 19.7 inches. Spindle speed is 300 revolutions per minute. The cutting tool is carbide, tungsten carbide. They machine the outer surface of the skirt. Final diameter is 11.02 inches. Tolerance, plus or minus 0.0008 inches. Skirt taper, 0.002 inches per inch of length. This compensates for thermal expansion. Cutting speed is 490 feet per minute. Feed rate is 0.008 inches per revolution. Depth of cut is 0.02 inches. They remove 0.28 inches from the diameter. Machining time is 20 minutes. The surface is smooth. Surface roughness is 63 micro-inches. Then they mill the ring grooves. 3 grooves. Width of the first is 0.16 inches. Second is 0.14. Third is 0.2 inches. Depth of the first is 0.31 inches. Milling cutter diameter is 4 inches. Spindle speed is 1200 revolutions per minute. Groove accuracy plus or minus 0.0004 inches. They're drilling the hole for the piston pin. Hole diameter, 4.33 inches. Depth, 7.87 inches. Carbide drill bit. Rotation speed, 500 revolutions per minute. Feed rate, 0.006 inches per revolution. Drilling time, 8 minutes. After drilling, reaming. The reamer brings the diameter to 4.3302 inches. Tolerance, plus 0.0004 inches, minus 0. Surface roughness, 0.315 thousandths of an inch. This is an interference fit for the bronze bushing. The bushing gets press fit with 10 tons of force. Interference, 0.0012 inches. They mill the oil channels. 2 channels, diameter 0.47 inches, running from the crown to the skirt. They carry oil away for cooling. They drill the oil jets. Diameter, 0.079 inches. 8 of them around the crown circumference. Oil sprays through them onto the inner surface. Cooling is critical. Crown temperature hits 662 degrees Fahrenheit. The oil carries the heat away. Machining the combustion chamber. The piston crown gets milled on a 5-axis machine. The combustion chamber has a complex shape. A toroidal cavity, diameter 7.1 inches, depth 2 inches, chamber volume 0.3 gallons. The shape's optimized for mixing fuel with air. Ball nose cutter, diameter 0.8 inches. Spindle speed 3,000 revolutions per minute. Tool path spirals from center to edge. Spiral pitch 0.02 inches. Machining time 40 minutes. Surface roughness, 0.00016 inches. Then chamber polishing. Abrasive paste, 3-micron grit. Polished with a felt wheel. Speed 1,000 revolutions per minute. Time, 5 minutes. The polished surface prevents carbon buildup. Final operation, honing the skirt. Honing creates a crosshatch pattern of micro grooves. Angle 60 degrees. Groove depth, 0.00012 inches. Width, 0.0008 inches. These grooves retain the oil film, reduce friction. Honing time, 10 minutes. Coatings and inspection. The crown gets a ceramic thermal barrier coating. Thickness, 0.3 millimeters. Material, yttria stabilized zirconia. Thermal conductivity, 2 watts per meter Kelvin. That's 100 times less than aluminum. The coating drops the crown temperature by 100 degrees. Applied by plasma spray. Plasma temperature, 10,000 degrees. Particle velocity, 1,000 feet per second. The skirt gets a graphite coating, anti-friction. Thickness, 0.015 millimeters. Cuts friction by 40%. Reduces wear at startup. Ring grooves get hard anodized. Hard anodization. Layer thickness, 0.05 millimeters. Hardness, 500 Vickers. Protection against ring wear. Every piston gets inspected. Diameter measured at 6 points. Laser micrometer. Accuracy, 0.001 millimeters. Weight gets checked. Scale accurate to 1 gram. Tolerance, plus or minus 5 grams. Weight variance in a set, no more than 10 grams. For engine balancing. X-ray checks internal defects, cracks, porosity, inclusions. Rejection rate, 0.5%. Finished piston weighs 51 pounds. Diameter, 11 inches. Height, 13.8 inches. It'll run 10,000 hours, 70 million cycles. Handle temperatures of 350 degrees. Pressure, 185 bar. Speed, 33 feet per second. That's how Caterpillar makes the biggest pistons. From aluminum ingot to a component that holds 9,000 horsepower. If this was interesting, hit that like button. Comment what engines you know. Subscribe. Here we show you how giants get made.
Every minute, thousands of kilometers of old cable vanish from our world. They're torn from the walls of houses, factories, and machines. And all of this scrap is reborn as pure copper, a hidden treasure more vital than gold for our modern world. Imagine it. Coils of wire that yesterday lay forgotten in a scrapyard are today melting in a furnace at over 1,100 degrees Celsius, hotter than a volcano. But the most remarkable part? Copper can be reborn infinitely. So the wire that lit your room 20 years ago might be powering an electric car tomorrow. And stay with me, because at the end, I'll reveal a secret this metal's been hiding, and it will change the way you see copper forever. Every wire you see around you, from old charging cables to industrial coils, has a story. It was part of something, conducting power, carrying signals, bringing things to life. But time moves on, technology is upgraded, machinery replaced, and these cables become waste. But this is where their second life begins. The scrap is gathered from everywhere: homes, offices, demolition sites, even old vehicles. A vast, unseen logistics network of lorries, containers, and depots comes to life. It's a treasure hunt, but the prize is metal and plastic, twisted together in a tangled mess. The first stop, the factory floor. Here, the cables pass through the hands of experienced operators who aren't just sorting, they're industrial archaeologists. This is a critical stage. The quality of the final product depends entirely on the accuracy of this sort. Mix the wrong types of metal and you compromise the purity of the copper, complicating every process that follows. The team here uses a variety of tools: shears, pliers, and specialized stripping machines. The work is fast, but precise. Every coil is unwound and separated into fractions: bare bright wire, plastic sheathed cables, thick industrial lines, copper, and aluminum. The integrity of the copper must be preserved. It's the heart of the operation. Even the smell on the workshop floor, a mix of old plastic, metal, and dust, tells you that this is where the transformation begins.
The coils are separated, the wires untangled, but the real alchemy is yet to come. What were once kilometers of cable are now fed into the heart of the plant. Some call it a shredder, others a dragon with steel teeth. The principle is the same. This beast devours everything. Cable fragments are loaded into a vast hopper. Inside, shafts armed with razor-sharp blades don't cut, they chew. Copper, aluminum, plastic, it's all torn, crushed, and ripped into small pieces. From there, the shredded mix enters a machine where physics takes over. A symphony of centrifugal forces, vibrations, air currents, and magnets goes to work. The light plastic is blown away into one stream. The heavy copper falls into another.
The air is thick with dust. The hum of machinery is constant. Operators watch the metrics on their screens intently. This isn't just noise, it's the sound of rebirth. Just like the alchemists of old who sought to turn lead into gold, there are formulas at work here too. But instead of elixirs, there are weighing systems, calibration tools, and purification technologies. Because in the modern world, magic is just well-engineered technology.
Inside the furnace, fluxes are gradually added, special agents that bind to impurities like oxides, dirt, and residual insulation. They float to the surface, forming a dark crust of slag. This is skimmed off by hand with long ladles, in a heat you can feel through a protective suit. It is one of the most dangerous jobs in the plant, but also one of the most majestic. Here, people witness the purification of old metal with their own eyes. They watch rusty scrap transform into a molten lake that glows like the sun. Even the sound is different here, a deep, guttural, threatening hum. It's the sound of copper saying, "I am returning."
Once the molten copper is cast into solid ingots, it still doesn't know what it will become. Its future lies in the hands of engineers and the rolling mill. The ingots are transported to the mill, reheated, and then forced through a series of giant rollers, like flattening a piece of red-hot dough. With each pass, it gets thinner. With each pass, smoother. This is how copper sheet is formed, or the feedstock for wire. Next comes drawing. This is where the copper is pulled through a series of progressively smaller holes, or dies. It stretches, thins out, but never breaks. Each die brings new precision, measured in microns. All of this to create a thin, flexible, gleaming copper wire. Sometimes, this wire will be insulated and buried in the walls of a new house. The average home requires around 200 kilograms of it. Sometimes it will be wound into the motor of an electric vehicle. And sometimes it becomes the delicate coil in a pair of headphones, carrying music from one heart to another. Every minute, over 17 tons of copper scrap are recycled globally. It's a metal that can be repurposed almost infinitely with no loss of quality. It lives, works, melts, and begins again. Every year, more than 50,000 tons of uranium are mined across the globe. But to extract just a few grams of its energy, mountains of rock must be moved. It's a journey that begins in a desert where the temperature hits 38 degrees Celsius and ends inside a reactor that powers New York City. It involves centrifuges that spin faster than a jet turbine and chemicals that can dissolve metal in seconds. But the most interesting part is something that even the safety manuals don't mention. Watch until the end and you will learn a secret that will change how you think about nuclear power forever. It all begins in the dust, literally. Uranium ore is mined in hot, arid regions: Arizona, Wyoming, Texas, New Mexico. Here, the sun is relentless, reaching 38 degrees Celsius in the shade, if you can find any. There are two main extraction methods: open pit mining, where the topsoil is stripped away, and underground mining, with explosives and hoists. There is also a third, more subtle technique: in situ leaching. Pipes are drilled deep into the earth. Special solutions are pumped down to dissolve the uranium directly from the rock, and the resulting liquid is then pumped back to the surface. The ore itself, a grayish-brown rock, looks unremarkable, but within it, the crucial isotope uranium-235 makes up just 0.7%. The rest is a vast, almost useless mass that is inert in a reactor. And to squeeze the required drop of energy from it, hundreds of tons must be processed. After mining, the ore is crushed, milled into a fine powder, and thrown into a chemical bath of acid or alkaline solutions. This is followed by filtration, precipitation, and drying at 260 degrees. The final product is yellowcake, a bright yellow uranium concentrate. Officially, it's known as uranium ore concentrate, but everyone at the plant just calls it yellowcake. It looks striking, a mustard-colored loose powder like a spice for a barbecue. But this is a substance you must not touch and must never inhale. It emits alpha radiation, has a long half-life, and its dust is dangerously toxic. The yellowcake is sealed in double-walled drums, loaded onto escorted trailers, and plastered with radiation warning signs for the journey to the enrichment facility. This is the start of the path that turns a poisonous dust into the clean white light from a lamp over your kitchen table, or the electricity that powers the tube deep beneath London. Right, the yellowcake has arrived. It's radioactive, dry, and sealed in its drum. The next step? Turn it into a gas. And not just any gas. This is uranium hexafluoride. The uranium concentrate is first dissolved in acid, purified, and converted into uranium dioxide. And here, the alchemy begins. The uranium dioxide is treated with fluorine gas in special reactors at 540 degrees. The reaction creates a volatile, transparent gas that boils at just 56 degrees. A little heat and it turns from solid crystals into a vapor. But it's not that simple. This gas is extraordinarily toxic. It corrodes most metals, destroys human tissue, and on contact with humid air, it instantly transforms into hydrofluoric acid and uranofluoride, a lethal cocktail. That is why this entire process is conducted inside sealed, automated reactors. The substance is stored as solid, whitish crystals, formed by cooling it to room temperature. These crystals are kept in steel cylinders, each engraved with a serial number and a radioactive symbol. A single cylinder weighs almost 14 tons. You think your washing machine spins fast? You haven't seen a nuclear centrifuge. They can reach 70,000 revolutions per minute, more than 10 times faster than a jet engine turbine. And all for one purpose, to separate uranium isotopes. Uranium hexafluoride, that toxic gas we just created, is fed into a tall, narrow cylindrical chamber, which is then spun at an insane speed. Centrifugal force does the work. The heavier uranium-238 atoms are flung towards the outer wall, while the lighter, crucial uranium-235 atoms remain closer to the center. But one centrifuge isn't enough. They are connected in cascades of hundreds, sometimes thousands. Each one slightly enriches the gas and passes it to the next. This process is repeated, cycle after cycle, until the concentration of uranium-235 reaches at least 3 to 5%. This is the standard grade for reactor fuel. Okay, the gas is enriched, but you can't feed a reactor with a gas. So now it is converted back into a solid, this time a ceramic form. After a series of chemical reactions, the gas becomes uranium dioxide powder, a dark gray solid. This powder is pressed under 20 tons of pressure into small cylindrical pellets, just 8 millimeters in diameter. They look almost harmless. Next, the pellets are centered in a furnace at nearly 1,650 degrees, making them as hard as porcelain. They are then polished and ground to precise dimensions. The finished pellets are loaded into long metal tubes known as fuel rods, typically made of a zirconium alloy because it resists corrosion and can withstand intense radiation. Each rod holds over 300 pellets. The rods are hermetically sealed and then bundled together into modules called fuel assemblies. They look like a square frame holding a grid of several dozen rods. A single assembly can weigh over 680 kilograms and will operate inside a reactor for up to 6 years. The finished fuel is packed into armored containers for transport. The journey is made under guard, on a special route with a security escort and GPS tracking. Left over from all of this is the depleted uranium hexafluoride, known as tails. It's a mix of isotopes with a small amount of U-235 remaining, but not enough to be useful. These tails are stored in steel cylinders at designated secure sites. When a fuel assembly has served its 4 to 6 years in the heart of the reactor, it is no longer a shining star. It is removed by a robotic system and moved into a deep pool of water, over 6 meters deep. The water cools the assembly and shields the intense radiation because the fuel is still incredibly hot. It rests there for several years. After that, it has 2 possible futures: long-term dry storage in concrete and steel casks, or reprocessing. This usually happens in other countries, as the US and UK primarily store their waste rather than reprocess it. In a dry storage facility, the assemblies stand for decades, cooled by natural air convection, as if in a nuclear monastery. This isn't the end, but a new phase of life. A slow, controlled existence, but one deeply connected to the future of energy. Because even after its time in a reactor, this fuel remains a source of heat, a lesson in engineering, and a reason for profound respect. 68 million tons. That's exactly how much aluminum humanity consumes in just 1 year. This enormous figure stretches from fizzy drink cans and window frames to the wings of gigantic aircraft. But have you ever wondered how we satisfy such enormous demand without depleting Earth's resources? The answer lies in a revolutionary innovation that's transformed the entire industry: aluminum recycling. Each recycling cycle not only saves up to 95% of the energy required to produce new aluminum, but also allows the metal to be reborn within 60 days, each time retaining its original quality. In this video, you'll witness aluminum's extraordinary journey, from discarded waste to gleaming products that return to everyday life. Unlike many other metals that lose quality with each recycling cycle, aluminum can be used infinitely without losing its original properties. This unique characteristic explains why nearly 75% of all aluminum ever produced is still in use. And the United States has transformed this advantage into industrial might. Thanks to advanced collection and smelting systems, recycled aluminum now comprises over 1/3 of the country's annual supply, saving sufficient energy to power millions of households every year. But the benefits aren't merely economic. Aluminum recycling also plays a critically important environmental role. Each ton of recycled aluminum prevents up to 9 tons of carbon dioxide emissions, representing tens of millions of tons of greenhouse gases that don't enter the atmosphere annually. The recycling journey begins with a step that may seem simple, but ultimately determines the efficiency of the entire subsequent process: collecting aluminum scrap. In the United States, the world leader in aluminum recycling, this system operates on an enormous scale. Every year, tens of millions of tons of aluminum are collected from countless sources, creating a constant stream that feeds the industry. What distinguishes aluminum is its inherent economic value already at the collection stage. A discarded aluminum can is worth many times more than a plastic bottle, giving both individuals and businesses a strong incentive to return aluminum to the production cycle. From collection points across the country, convoys of lorries laden with aluminium scrap steadily roll into enormous sorting yards. Each vehicle is weighed, registered, then its container is tilted to discharge the load onto conveyor belts. Beer cans from supermarkets, food trays from residential areas, and industrial aluminium scrap all converge into towering heaps of shimmering metal resembling silver mountains. Right on site, technicians conduct quick preliminary inspections, promptly rejecting any batches contaminated with excessive impurities or hazardous materials. The atmosphere at the yard is always tense. Thousands of tons of aluminium arrive daily, making this facility the genuine front line of the recycling process. At the recycling facility, streams of aluminum scrap are fed onto long, continuously moving conveyor belts. Optical sensors, acting as electronic eyes, scan thousands of fragments per second, identifying aluminum by its characteristic color and light-reflecting ability. Immediately afterwards, powerful magnets remove any ferrous metals, whilst precisely calculated air jets blow aluminum away from plastic, paper, and lighter rubbish. Through several separation layers, the once chaotic waste mixture gradually transforms into more homogeneous streams of aluminum, neatly collected in gleaming silver heaps. From this point onwards, the aluminum stream becomes chemically homogeneous and strictly controlled, ready to transition deeper into the recycling process. After separation, aluminum scrap is fed into a massive shredding system. Conveyor belts constantly drop beer cans, food trays, and industrial scrap onto counter-rotating steel rollers studded with sharp teeth. With intense crushing force, the metal is instantly destroyed, sending sharp metallic clicks echoing throughout the workshop. In just a few revolutions, hundreds of kilograms of aluminium are drawn inside and shredded into small fragments. A vibrating sieve system controls output size, guaranteeing that all shredded aluminium is reduced to uniform size, creating stable, homogeneous raw material for the next stage. Shredded aluminum fragments are fed directly into industrial furnaces, the heart of the entire recycling process. Depending on scrap type and desired end product, the plant may use reverberatory furnaces, rotary furnaces, or electric arc furnaces. Internal temperature is maintained between 660 and 750 degrees, sufficient to melt aluminum without evaporating valuable alloying components. Aluminum is loaded through an upper hatch or incline chute, then constantly stirred either by mechanical paddles or controlled air injections. Throughout the melting process, thermal sensors and chemical analyzers work continuously, guaranteeing that each batch of molten aluminum meets precise technical specifications.